This is a gamma-ray burst, which is the biggest blast since the Big Bang. There are no signs that something bad is about to happen, and then it strikes. The radiation that is pumped up heats up the high atmosphere. Our layer of ozone heats up. Across the atmosphere, human beings burns to death from radiation 100 times the fatal dose. When the ozone layer gets thinner, temperatures rise all over the world. This makes storms, tsunamis, and hurricanes happen. Most life on the surfaces of land and water incinerates. This may sound like science fiction, but if a gamma ray burst from 100 light years away hit Earth, it could happen. Gamma ray bursts are the most bright blasts in the universe. They must have a huge amount of power because they're so far away and yet still so bright. As much energy as the sun will give off in its full 10 billion year life. We know there are many planets and many stars in the universe, so gamma ray burst could have wiped out a lot of different cultures. In the 1960s, this strange blast of radiation was first seen. At first, because these gamma-ray bursts are so bright, most scientists thought they came from our own galaxy, the Milky Way. There are a few reasons for that. One of them is that if they are outside the galaxy, the energy is almost too much to believe. But back then, even the most powerful telescopes couldn't figure out where they were or how far away they were, because the burst only lasted a few seconds and then went away. But then, scientists started to wonder about their afterglow. Most blasts in space leave a glowing trail behind that can last for days or even weeks. In the late 1990s, satellites with better optics and X-ray monitors were finally able to catch the afterglow of a gamma-ray burst. It became clear that gamma-ray bursts actually came from outside our galaxy, millions and billions of light years away. So, their power had to be really out of this world. The brightness of the gamma-ray burst is the same as that of 1,000,000 trillion suns. This huge explosion could wipe out all life on Earth. But why do they happen? We are very sure that a common gamma-ray burst is caused by the death of a star that is at least 10 times the mass of the Sun. And these kinds of stars aren't very common. When a very big star dies, it falls apart and forms a black hole. Black holes are made when a mass of matter shrinks to a point where it is so dense that light can't get out. But experts think that some of the star resists getting sucked into the center of the black hole. As a result, a high-speed spinning disk of matter forms around it. In a matter of seconds, plasma jets shoot out from the poles where it spins. These beams of energy unleash dangerous gamma rays into space. At the same time, the gamma-ray bursts are ejected, the collapsing star explodes or goes supernova to the extreme. Gamma-ray bursts are so bright because they take a huge amount of power and focus it on a very small area of the sky. Only one of every 300 gamma-ray bursts is directed toward us, so we only see one of those 300. Even if a gamma-ray burst happened not 100 but 1,000 light years away, the Earth could still be destroyed in a way that is similar to the end of the world. If a gamma-ray burst happens within 100 light years off the Earth, then it would be approximately 500 times brighter than the Sun and made in gamma rays. The energy sent to the high atmosphere of Earth would be the same as if 100,000 megatons of nuclear bombs went off. The ozone would be depleted, we'd have acid rain, but we'd also have flash burns, incineration of vegetation, perhaps something resembling nuclear weather. So many species could go extinct all over the world. Now, the other side of the Earth would be a special place to be, because gamma rays don't go through the Earth, so you wouldn't get flash burned if you were there. However, the repercussions of altering the atmospheric composition and ozone depletion would ultimately come to the other side, and there, nobody knows what will happen. This nightmare scenario has a 1 in a trillion probability of occurring once in Earth's history. It's going to be a nasty day if you get caught in the beam, for the reason that this is extremely powerful radiation. You don't want to be in the vicinity of this sort of energy, since it has the potential to break down your own molecules. Currently, there is no way to protect humanity against gamma-ray bursts that occur in close proximity to Earth. They move at the rate of 186,000 miles per second, or the speed of light. By the time we detected them, they would have already struck our planet. Gamma-rays bursts could pose a hazard to the Earth or to anything living that came within their born sight. Astronomers think that gamma-ray bursts could be the cause of some mass extinctions on Earth. The one that happened 450 million years ago and killed off the Ordovician and Silurian species was probably the worst. Creatures that live near the surface of the ocean were hit much harder than those that live deep in the ocean. This is consistent with what would happen during a strong gamma-ray burst. In a galaxy the size of the Milky Way, gamma-ray bursts happen about once every few 100,000 years, according to astronomers. Even though they can be very bad, you have to be pretty close to be hurt by one. A gamma-ray burst happens about once every 5 million years, which is close enough to affect life on Earth. In other words, since the Earth was made 4.6 billion years ago, there have been about 1,000 events. So the chances of a close gamma-ray burst aren't zero, but they're low enough that you don't need to worry about them, unless you want to live for about 5 million years. Humanity obviously made it through the gamma-ray explosion unharmed, but this still demonstrates how far their effects may travel. Don't fret. Threats to Earth from gamma-ray bursts are extremely low. All of the closest contenders for gamma-ray bursts have been studied by astronomers, and none of them are either close enough or orientated in a way that would cause them to strike Earth. Therefore, what do you think? In our solar system, Earth shines like a sapphire jewel. We go about our daily lives without knowing the trouble could be coming from deep space. The routes that Earth and most other things take around the sun can be predicted. Most of the time, things are quiet and easy, but sometimes they get crazy and violent. Earth can be hit by space rocks, zapped by dangerous space weather, jolted, jostled, and threatened by the object's energy and cosmic forces. The Earth is on a wild ride through space that is often very dangerous. When you're moving fast in on a predetermined path, you hope nothing crosses because there's nothing you can do. Rusty Schweickart used to be an astronaut, so he knows how dangerous things in space can be. During the Apollo 9 flight in 1969, he was in charge of the lunar module. He is sending out warnings about the risks of an asteroid named Apophis that is getting too close to be safe. Everyone noticed him right away because the probability of impact was quite high. In fact, it was significantly greater than any effect probability we had seen before. Schweickart has a scary example from real life that shows how bad an asteroid, even one smaller than Apophis, can be when it hits. June 30th, 1908, 7:15 a.m. A half-football field-sized object came hurtling down from space at about 34,000 miles per hour and made a stream of fiery gas behind it. Within minutes, the fireball hit Earth's atmosphere and burst violently near the Tunguska forest in Siberia. As a result, the explosion was the greatest ever recorded in the history of the planet. The explosion split the waves, which then set fire to 8 million trees in an area that was bigger than half of Rhode Island. Because the explosion happened in a place with few people, no one died directly from it. If that asteroid had hit just a few hours later, it would not have hit Siberia, but Europe. And if it had exploded in the air over one of Europe's biggest cities, 1 million people would have died. For the last 100 years, the Tunguska explosion has been shrouded in controversy. Many researchers now think an asteroid was the explosive trigger. Incredibly, it never even impacted the ground. Rather, it exploded 5 miles above Siberia's frozen ground. When it smacks into the lower atmosphere, doing about 50,000 miles an hour, it's like an egg smashing on the concrete. Energy equivalent to 15 megatons of TNT was released in the Siberian explosion, making it 1,000 times greater than Hiroshima. Over a huge city, this would be catastrophic. NEOs, or near-Earth objects, were the name given by scientists to these trespassers. They are comets and asteroids, leftover debris from when the planets formed. The Oort cloud is a part of the Kuiper belt that extends past Neptune and is where comets travel. Between Jupiter and Mars, asteroids take a curved path, but their orbital trip isn't always routine. We don't have to worry too much about asteroids because they circle in a somewhat orderly belt between Mars and Jupiter. But when one gets away and all that mass and energy is going toward Earth, that's when the astronomers start to worry. It's not uncommon for cosmic debris to be jolted out of orbit and headed for Earth. The majority of it is evaporated by our planet's dense atmosphere. A larger object, however, is able to break through Earth's atmosphere and crash to the surface. Asteroids are a real and dangerous threat if you wish to look to the cosmos for the powers that would have us dead. Just like it did previously, it will happen again. 65 million years ago, an asteroid the size of a small city plummeted down from the sky. It exploded in the Yucatan Peninsula, near the town of Chicxulub in Mexico, with a force of 100 million megatons of TNT. Here we see Earth hurling billions of tons of its crust into space, creating a blanket that blocks out sunlight, destroying the food web at its roots, and killing off countless species. The ferocious impact is thought to have been a factor in the extinction of the dinosaurs. We can think of asteroids as being bad things, but if it were not for an asteroid, we wouldn't be here today. Our mammal ancestors were running on their foot trying to avoid being appetizer for T-Rex. T-Rex gets taken out. Well, this opened up an ecological niche that allowed our mammal ancestors to evolve to something more ambitious than a route and outcomes the primates, and among the primates, we have people. But it's strange that the same kind of cosmic boulder that made it possible for humans to live could one day wipe us out. In 1998, Congress asked NASA to find all near-Earth objects that were at least half a mile across, and what they found was unsettling. There are more than 850 NEOs near our vicinity. These asteroids are our nearest and most dangerous space friends. Finding these near-Earth objects is a bit like keeping an eye on storms. As you watch it day after day, you get a better idea of its path and can figure out where it's going, how big it is, and how fast it would hit the Earth if it did. By using telescopic technologies, NASA's Space Guard survey has detected over 90% of all near-Earth objects deemed harmful. These scary things could hit Earth with more power than all of the nuclear weapons on the world right now. Such an impact could trigger mass extinction. We wouldn't expect one to hit every few 100,000 or millions of years, but if one did, it could wipe out different parts of the population. So there are events that happen very rarely but have big effects when they do. If they hit Earth, they would have impacts all over the world. They would not only wipe out a continent with very strong shock waves, but the debris would also be thrown into the air and land all over the planet, heating the air to 1,000 degrees. And all the vegetation all over the world where that happens would flash into flames. Smaller objects could also cause disasters. So Congress has asked NASA to find all NEOs with a diameter of 500 feet, which is as big as the Colosseum in Rome. A big object like that could wipe out a city or even a small state. Scientists are most worried about the asteroids they haven't found yet, not the ones they have found. Well, at the moment, there are about 2,000 objects that we can't say for sure won't hit Earth. We now have the technology to keep near-Earth objects from ever hitting Earth again. We can now literally start to change the local solar system to make it better for our life. The question is whether or not we will end up like the dinosaurs. It's hard to believe that the Earth has been around for more than 4.5 billion years because it's been through a lot since it was born. Asteroids that come into our orbit every year keep hitting our world like a boxer, but one day Earth could be knocked out. We've learned that near-Earth objects fly by us all the time, and we're getting more and more able to change our surroundings to help us stay alive. A rock in space named Apophis. In 2004, this pockmarked rock about 750 feet across came close to Earth. Now, it's scheduled to pass dangerously close to our planet again on Friday the 13th in April 2029. So, in 2029, Apophis will get closer to us than our Rome communication satellites that circle the Earth. If you are in the right place, you will be able to see Apophis pass by the Earth with your own eyes. That's how close that rock is going to get. You won't even need binoculars. Over 99% of the time, Apophis will miss the Earth in 2029. However, if it passes the Earth at an exact distance of 18,893 miles, it may pass through a gravitational keyhole, a small area in space that is only a half-mile wide. If this happens, Apophis could be thrown off by the Earth's gravity, which could change its path. It could make Apophis come back and hit Earth on April 13, 2036, 7 years later. The gravitational effect of the Earth would cause it to bend, cause the Apophis's orbit to enlarge to precisely the size, which 7 years later it will come around and hit the Earth. At the present time, Apophis has 1 in 45,000 chance of delivering a deadly blow in 2036. It's one thing to say that there's a 1 in 45,000 chance that it will hit the Earth, but what you really want to know is if there's a 1 in 100, 1 in 10, or 1 in 1 chance that it will hit the Earth. We have to look at Apophis the same way we look at any natural disaster. You know the date of the hit, when it happened, and the angle of the orbit, so you can make a map. It starts in western Siberia, cuts across and down the Pacific Ocean near California, goes through Central America, and ends in Western Africa. Scientists have come up with a scary idea about where Apophis could strike. With a force of more than 1 million megatons of TNT, the asteroid could hit the Pacific Ocean off the coast of California. Such an impact would make a hole in the water 5 miles wide and 9,000 feet deep. This would cause tsunamis with waves up to 50 feet high to hit the coast, resulting in unimaginable human loss. If a rock 1,000 feet across hits the ocean, that's not a good thing. For that kind of thing, scientists are working on ways to stop such a cosmic strike from happening right now. A possible plan is to blow up an asteroid. But some people worry that this could make the problem worse by sending more pieces of the asteroid our way instead of just one. So, the new goal for experts is to change the path of asteroids that could hit Earth. Change its velocity by a 10,000th of a mile per hour so that it will miss the Earth instead of hitting it. If we know about an asteroid far enough in advance, we can change its path. Although a space probe has landed on an asteroid in the past, the most challenging idea is launching a manned mission. Once landing on the rock, astronauts could mount a radio transponder to track its whereabouts. Now the United Nations plans to draft a treaty which will include who will be responsible for deflecting killer asteroids. If we are so careless that we keep doing nothing even though we know this is going to happen, that will be a real crime. Any asteroid hitting the Earth will require international disaster response. In addition, training is required in disaster and emergency management institutions and the public regarding the asteroid threat. It is important that everyone is aware of the level of threats and the potential to eliminate this threat. Apart from all these, amateur astronomers can work together with scientists to defend our planet. Amateur astronomers can help identify smaller and potentially destructive asteroids hidden in the universe. So would you like to be an amateur astronomer? Who knows? Maybe you can be one of the guards of our home. On a night in early September 1859, people all over America could see the aurora. It was blood red and so bright that when miners in the Rockies came out of their tunnels, they thought the sun was coming up. So bright, in fact, that even at midnight you could read a newspaper. It didn't just happen in the U.S. People all over the world saw these auroras. No one knew why they had happened. But earlier that same day, an astronomer had seen something on the sun's surface that he called a white light flare. Back then, the flare and the aurora seemed to have nothing to do with each other. But we now know that the spectacular aurora was caused by that flare, which was a coronal mass ejection. And if this violent event happens again, it could destroy our modern technological world. The sun is the most familiar thing in the sky. It gives all life on Earth heat and light. It is so big that it's hard to imagine, and it makes up 99% of the mass of the solar system. This nearly perfect sphere has a diameter of 1.4 million kilometers and was made by the burning of hydrogen and helium for the last 5 billion years. But from an astronomical point of view, it's nothing special, a G main sequence star, also known as a yellow dwarf. But looks don't always tell the whole story. Solar flares and explosions of plasma, particles, and radiation from its surface travel far into space. We call this process the solar wind. Solar storms, on the other hand, are very violent eruptions. And a coronal mass ejection, or CME, is the most dangerous because it has the potential to bring our high-tech society to its knees. Today, we'll find out how bad a CME could be and what astronomers are doing to keep an eye on our star to try to predict when they might happen. Step back in time to 1859. First, in Victorian Britain, it was okay for a gentleman to be interested in solar astronomy. And one man did it in a very good way, Carrington Richard Christopher. We don't know what he looked like, though, because there are no known portraits of him. Carrington learned many important things from what he saw. He saw that different latitudes rotated at slightly different speeds, which meant the sun wasn't a solid body, but a fluid one. But he also saw that sunspots could be the start of a solar storm. On Thursday, September 1, 1859, there were no clouds in the sky in the morning. So Carrington was doing what he always did, which was to look for sunspots. He was using his telescope to project an image onto a screen. At 11:18, he saw two brilliant beads of blinding white light appear in what Carrington calls a kind of conflagration. Stranger still, they were gone after 5 minutes for no clear reason. Carrington had seen a coronal mass ejection, which was a huge magnetic explosion. A huge cloud of charged particles that are thrown off the sun's surface. After 18 hours, the Earth was hit by an electromagnetic storm. People started calling it the Carrington event. At the time, everyone was talking about the beautiful aurora, which could be seen all over the world. Even though a few telegraph systems went a little crazy because of power surges, it didn't have much of an effect on everyday life. Don't forget, though, that this was 20 years before the light bulb was made. That was in the past. Things would be very different right now. Coronal mass ejections are common, but they can be different sizes and move in different directions. So, the question is, what are the chances that something like what happened in Carrington will happen today? And how would it change things? So, what is going on at the sun, on the surface of the sun, when we talk about the solar wind and space weather? The sun is made of magnetic fluid, and when that magnetic fluid rotates, it twists and distorts the magnetic field. A twisted magnetic field stores energy, which can lead to eruptions, which are called mass ejections. And these explosions are huge, sending out 1 billion tons of material at 1 million miles per hour. So, we want to know where these things are going, because if they move toward Earth, they could affect the technologies we use. There's a very famous event in Quebec in 1989, where some power systems were disrupted for many hours in October. We've heard about the Carrington event, which happened in the 1800s. What would happen if it happened today, and how would it affect us? If we think about what we use satellites for now, we have GPS spacecraft that help us find our way, communication satellites, weather satellites, and even the stock markets are linked in some way. But we also have bigger power grids and a lot of wireless technology, and we don't know how they will react. How likely is it that something like the Carrington event could happen again? We know that the sun can still make these things happen. In 2012, there was an event that luckily didn't come toward Earth, but it did pass over one of the spacecraft we use to watch the solar wind. And it pushed all the sensors on that spaceship to their limits. So from what we've learned, we think that was at least as powerful as the Carrington event, and maybe even more so. It's just a coincidence that a big CME and one that's headed toward Earth both happened at the same time. And that's mostly just a matter of luck. We either get one or we don't. And how do we do with making predictions? Can we predict what the sun will do in a week, a month, or a year? Once a CME is up and running, we can start making predictions so that we can figure out how big it is, how fast it's moving, and most importantly, where it's going. All of this sounds very scary. Space weather is a problem, and the UK government knows this. The National Risk Register lists it. It's about as bad as a pandemic of flu. So, the people who make spacecraft are trying to find out what the most extreme conditions are in space, so they can make them so that they can handle those conditions to a certain degree. Both NASA and ESA are getting ready to send satellites into space that will get closer to the sun than ever before. The MET office's Space Weather Operations Center opened in 2014. It is one of only 3 places in the world that can predict the sun's effects on Earth around the clock. So far, the sun has had almost no sunspots, and the side that faces Earth is not expected to have any more sunspots or CMEs that are important. So luckily, there isn't much going on right now, and things don't look too different in the long run. So, spacecraft, satellites, power supplies should be safe for the foreseeable future. Trouble is, the foreseeable future in space weather forecast is, at most, just a few days. We still don't know a lot about CMEs, like where they're going, how big they are, or when they might happen in the future. 2 new solar probes will get closer to the sun than any other spacecraft has ever done. The Parker Solar Probe was supposed to be sent into space, and its destination will be close enough to the sun's surface to fly through the source of the most energetic solar particles. The Parker Solar Probe is an exploration mission that will measure the gas and magnetic field near the sun to figure out why this stuff is spreading out into the rest of the solar system. And this, the Solar Orbiter from ESA. Solar Orbiter might find out how sunspots, flares, and coronal mass ejections on the sun's surface are related to the solar wind. Solar Orbiter's success will be very important for our understanding of how the sun works. We think that the sun's magnetic field is made in a way similar to how Earth's is, but it is much more dynamic and changes all the time. We have an 11-year sunspot cycle, during which the sun's magnetic fields move towards the poles and the polarity changes. On top of that, the magnetic field goes out into the solar system and flows over all of the planets. Solar Orbiter will measure these magnetic fields for the first time, and it will also give us the chance to watch the magnetic fields move to the sun's poles. To do this, Solar Orbiter will take pictures of the sun's atmosphere and measure the number, speed, and temperature of the particles moving across the space between the sun and Earth. But the magnetometer, which is made to measure the tiny magnetic fields in space that are carried by the solar wind, could be one of the most important and sensitive instruments. The sun is ever present in our lives. It gives us light, warmth, and even life itself. For Richard Carrington, who was the first person to record ACME, it was just a strange event. But now we know that these things can do a lot of damage to the world we live in. With new satellites and more observations, we might be able to learn more about these events and predict when the next coronal mass ejection will happen. Nothing existed at the outset. After then, the cosmos began to take shape some 13.7 billion years ago. How this came to be, or if there was ever a time before, time is still a mystery. Yet, physicists have pieced together an approximate timeline of significant events in the cosmos's existence using telescope data and models of particle physics. From its beginning to its inevitable demise, we examine key points in the evolution of our universe here. Welcome to the endless universe. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. The Big Bang. The Big Bang is a moment in time, not a location in space, from whence all else unfolded. To be more precise, it's the first second of time, the point in history from which all other seconds have been measured. The Big Bang, despite its common name, was not an explosion, but rather a time when the universe was incredibly hot and dense before space began to expand outward in all directions simultaneously. The Big Bang scenario suggests that the universe was an infinitesimally small point of infinite density. However, this is merely a convenient way of expressing that we don't know for sure what happened at that time. We now understand the cosmos to break down at the Big Bang because mathematical infinities don't make sense in physics equations. Cosmic inflation era. The next cosmic confab was to rapidly expand in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but it has gained favor among cosmologists as a possible explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014. Nevertheless, further investigation revealed that the true culprit was nothing more than interplanetary dust causing interference. Quark-gluon plasma. The temperature of the early cosmos was between 7 trillion and 10 trillion degrees Fahrenheit, or 4 trillion and 6 trillion degrees Celsius, just a few milliseconds after the Big Bang. Quarks, Elementary particles ordinarily contained within protons and neutrons were free to move about at these temperatures. These quarks were combined with gluons, carriers of the basic force known as the strong force, in a primordial that pervaded the whole universe. In particle accelerators on Earth, scientists have replicated these circumstances. In both terrestrial atom smashers and the early cosmos, the challenging to achieve condition only lasted for a few fractions of a second. The early epoch, the subsequent period of time, beginning perhaps in the neighborhood of a few thousandths of a second following the Big Bang, was a period of intense activity. The universe chilled as it expanded, creating an environment conducive to the merger of quarks into protons and neutrons. The cosmic neutrino background, which has not yet been detected by scientists, was created 1 second after the Big Bang, when the density of the cosmos decreased sufficiently for neutrinos to sail across space without interacting with anything. The first atoms, protons and neutrons, fused together during the first 3 minutes of the universe's existence, creating the isotope of hydrogen known as deuterium, along with helium and a trace quantity of the next lightest element, lithium. Yet, this procedure ceased as the temperature dropped. As temperatures settled down 380,000 years after the Big Bang, hydrogen and helium atoms could join with free electrons to form the first neutral atoms. The cosmic microwave background, a remnant of this epoch first identified in 1965, was created when photons that had previously collided with electrons were able to flow without being disrupted. The Dark Ages. There was a lengthy period of time when nothing in the cosmos emitted any light. The cosmic Dark Ages refer to this time frame of around 100 million years. Because practically all of what astronomers know about the cosmos can be gleaned by studying starlight, this era remains exceptionally challenging to study. It's hard to piece together what happened if there are no stars to guide us. The first stars. The first stars were formed when hydrogen and helium began to compress into massive spheres, some 180 million years after the Big Bang, creating hellish temperatures at their centers. After the neutral hydrogen atoms in interstellar space were broken apart into protons and electrons by the intense photons generated by early stars and galaxies, the cosmos entered a period known as cosmic dawn or reionization. It's hard to put a time limit on reionization. As it happened so soon after the Big Bang, its signals have been masked by subsequent gas and dust. Thus, the most that scientists can determine is that it was finished by around 500 million years after the Great Bang. Large-scale structure. Almost 1 billion years after the Big Bang, supermassive black holes developed at the cores of merging early galaxies. Intense quasars, visible from 12 billion light-years away, switched on and began emitting their bright beams of light. The universe's middle years. Throughout the subsequent few billion years, the cosmos underwent more evolution. Denser regions in the early cosmos drew more material due to gravity. A gorgeous filamentary cosmic web is the result of them slowly expanding into galaxy clusters and lengthy strands of gas and dust. Birth of the solar system. A yellow star with rings around it formed from a cloud of gas around 4.5 billion years ago in one galaxy. These accreted rings eventually became the 8 planets of our solar system, as well as numerous comets, asteroids, dwarf planets, and moons. Either the third planet out from the sun retained a lot of water via this process, or it received a deluge of ice and water from comets later on. Earth and humanity. Little primitive bacteria appeared on that third watery world between 3.8 and 3.5 billion years ago. These organisms arose and progressed into amazing marine monsters and enormous dinosaurs that fed on leaves. Some 200,000 years ago, upright beings emerged, capable of contemplating the vastness of space and learning about the universe's origins. The end, or not. It isn't the final chapter, of course. The future of the cosmos is still a mystery to physicists. It is dependent on our ability to accurately quantify the characteristics of dark energy, the unknown factor thought to be accelerating the expansion of the universe. All the stars in all the galaxies will have burned out, and even black holes will evaporate into nothing if the universe continues to expand forever, leaving behind a lifeless cosmos saturated with inert energy if this scenario comes to pass. Alternatively, the Great Crunch, a reversal of the Big Bang in which gravity triumphs over dark energy's expansionary force, will occur. The Great Rip, in which the cosmos rips itself apart, is another possibility if dark energy accelerates everything apart to greater and greater distances. Thanks for watching, and don't forget to hit the like button, subscribe, and turn on notifications for more content like this in the future. Our solar system is a harsh environment. Volcanoes are destructive everywhere, from the ice volcanoes of Saturn's moon, Enceladus, to the immense lava fields of Jupiter's moon, Io, to our own planet Earth. It is truly true that we would not be here if there were no volcanoes. Volcanoes influence and alter our climate. Volcanoes are both the creators and destroyers of existence. Today's spacecraft and observatories have revealed volcanoes on planets we once believed to be dead. The discovery of volcanoes on an object smaller than the moon was a major surprise. If there are volcanoes on other worlds, could there also be life? Volcanoes are among the most potent natural occurrences on Earth. They create new land, destroy the old. They emit gases that alter the atmosphere we breathe. Deep in our oceans, volcanic heat fuels bizarre new forms of life. Volcanoes help sustain life on Earth. Now we look for signs of life on other planets. We understand that life requires water. We are aware that it requires energy. And this is where volcanoes come in, as they generate tremendous quantities of energy. If we locate volcanoes on other planets, we may discover life. The search begins with this planet, which orbits the Earth closest. Venus, a planet that closely resembles our own. Venus and Earth have similar masses. Earth and Venus were very similar 3 billion years ago, with new land, new oceans, and an atmosphere. Both planets was conducive to life. On Venus, however, something went awry. Something caused the history of Venus to diverge drastically from that of Earth. Venus took a definite turn to the dark side a long time ago. Venus is hell, our malevolent twin planet. Today, the surface of Venus is like a furnace. The surface is 900 degrees Fahrenheit hot. It is actually heated enough to melt some metals, so you have no chance. Venus is a greenhouse world. Its atmosphere contains a high concentration of carbon dioxide. It absorbs solar heat like a blanket. Actual images of Venus's surface reveal a desolate, extremely hot desolation. The planet was annihilated by dense CO2 atmosphere. The CO2 was produced by volcanoes. Spacecraft in orbit provided the initial clues. Radar broke through Venus's thick clouds and showed volcanic formations all over the planet. These formations look a lot like the shield volcanoes on Earth. Round and flat, shield volcanoes derive their name from their shape. These volcanoes ooze, but they ooze for thousands of years. Once we were able to map the entire surface of Venus using cloud-penetrating radar, we began to examine its landforms and discovered that many of them were quite familiar. In particular, we observed enormous shield volcanoes that resembled the shield volcanoes in Hawaii. The radar images of Venus were identical to those of Hawaii's shield volcanoes. In the past, Venus was home to volcanoes. We were astounded to see a picture of Venus for the first time. We discovered a cratered volcanic surface. There are at least 1,000 large volcanoes and possibly tens or hundreds of thousands of lesser ones. Lava plains cover 3/4 of Venus's surface, evidence of an ancient catastrophe. This could have been a home for life. It was instead consumed by flames. Numerous trillions of tons of carbon dioxide were expelled by Venus's volcanoes into the planet's atmosphere. The temperature rose dramatically. The oceans evaporated. On Earth, carbon dioxide is able to absorb into the rocks. It can be absorbed by the ocean. On Venus, however, there is no water, and the temperature is so high that carbon dioxide cannot even combine with the minerals. Volcanoes released carbon dioxide into the atmosphere eons ago, and as time passed, fewer and fewer methods existed to remove it from the atmosphere. Volcanoes sanitized the entire planet if Venus ever supported life. Earth is the only known planet with life. That may alter. This is the gas giant Jupiter, with its moons believed to be frozen and lifeless. A mystery surfaces as a cloud hovering over a cold and lifeless world upon closer inspection. On Venus, volcanoes transformed a planet similar to Earth into a hyperheated inferno. Volcanoes on a planet similar to Earth were not a surprise. But the discovery of volcanoes on the moon was an astonishment. In March 1979, the Voyager 1 spacecraft provided us with our first up-close look at Jupiter's minuscule moon Io, a world we once believed to be frozen and lifeless. And they witnessed something odd. They observed this arc next to the moon, and it almost appeared as though there was a second moon behind it. We scratched our minds and asked, what could that be? Everyone is aware that Io is lifeless, dull, and uninteresting. And then people realized, oh my God, it's a volcanic eruption. We discovered that the area is engulfed in volcanoes. It is geologically extremely active. There are constant volcanic eruptions. And what they're erupting is a great deal of sulfur, which becomes extremely heated. And sulfur changes color as its temperature changes. It may be red, orange, yellow, or even black. As a result, these images of Io's visage resemble a pizza with various types of cheese and olives where the small black spots are. Io is not dead. It is alive and growing. There are more than 400 active volcanoes. The largest, Pele, erupts from a gigantic lava lake. It extends approximately 400 kilometers into space. It would be an extraordinary sight if we could stand on the edge of that lava lake and observe that plume shooting off into the void of space. Pele's eruptions are so massive due to Io's diminutive size. There is nothing holding the lava back, as there is virtually no atmosphere and little gravity. These enormous eruptions make Earth's volcanoes resemble fireworks. How can a moon so small be so volcanic? The answer is Jupiter. Similar to how the moon raises the tides in Earth's oceans, Jupiter raises solid rock tides on Io. The orbit of Io around Jupiter is not circular. Sometimes it's closer, sometimes farther away. Jupiter exerts a gravitational force on Io. Jupiter's gravity stretches and squeezes Io. In every 2-day orbit, the ground rises and falls by nearly 300 feet. This pummeling generates extreme heat and enormous pressure. Wherever there are weak spots in the crust, lava erupts. Volcanism is therefore planet scale. In contrast to Earth, where certain portions are active around the plates or in weak areas, this is an entire moon. That's one active hotspot. Io is the most volcanism-active planet in the solar system as a result of the immense power of gravity. Volcanic activity on Io has taught us something new. It taught us that internal energy sources can drive volcanism in a manner distinct from that on Earth. Io is a lava world that is extremely hot and violent. It is difficult to conceive of anything surviving there. We have discovered strange eruptions on numerous planets and moons. But so far, the only world where volcanoes are linked to life is ours, or so we thought. This is Europa. It orbits Jupiter at a distance of nearly 500 million miles from the Sun and is a 2,000-mile wide sphere of ice. From afar, its surface appears to be polished. Up close, it's a different story. Europa is pummeled by Jupiter's immense gravity, just like its companion Io. The surface rises and bends, forming ridges and deep fissures. When we first obtained close-up images of Jupiter's moon Europa, they seemed vaguely familiar, and it turns out that they resemble Arctic ice flows. And it turns out they're the same. A global liquid ocean lies beneath Europa's several-mile-thick icy crust. Magnetic measurements indicate Europa's ocean is an astounding 60 miles deep. The gravitational impact of Jupiter heating the rocky interior and melts the ice above. As the core is stretched by tides and heated, possibly melting, it is not preposterous to believe that there is a boundary between a hot core and a liquid water ocean. Underwater eruptions on Earth are surrounded by life. The same may occur on Europa. Here, the darkness is complete. The pressure, a crushing 2,000 Earth atmospheres. A harsh environment, but perhaps a cradle for life. If there is evidence of life on Earth, why not Europa? An energy source, volcanic activity, a universal solvent, liquid water, and a complex hydrocarbon chemistry are all present. Life would be difficult, but not impossible on Europa. There is life at every extreme on Earth, including searing heat, crushing pressure, and absolute darkness. Life on Europa may resemble our own in unanticipated ways. If life exists beneath Europa's ice, it would be aquatic, but without eyes, because there is no significant light. Organisms that essentially feed off the energy of the volcano would most likely utilize sonar to make sense of their surroundings. Volcanoes on Europa could be the genesis of new life. It is even conceivable that Europa is typical, that this is the norm for planets with life. Earth may represent an exception. Consider that Europa could serve as a model for the billions of moons in the universe, with liquid oceans. So, all of a sudden, our horizons have expanded several billion times by looking at the moons of Jupiter. Our solar system is home to more than 170 moons. Multiply this by the size of the universe, and that's a lot of potential habitats for life. Only liquid water and a source of energy are required. Potentially, both are provided by volcanoes, and they are ubiquitous. This is Saturn, twice as far from the Sun as Jupiter. However, it also has volcanic moons, and similar to Europa, these moons could support life. Saturn is one of the odd planets in our solar system, with a 600,000-mile-wide ring system, an astounding 62 moons, and one with a secret. Enceladus is one of the lesser and more distant moons of Saturn, and it's been known for a long time that it's covered in ice due to its extremely brilliant and reflective surface. However, when the Cassini spacecraft visited the planet, it made a remarkable discovery. Not on the planet itself, but on Enceladus did the Cassini probe disclose a remarkable discovery. A massive plume, backlit by the sun and erupting into space, is conclusive evidence of volcanic activity. Cassini's sensors zoom in on the south pole of the moon to capture these enormous craters scarring its surface. At the south pole of Enceladus, there are extraordinarily large fissures, which open and close as Enceladus orbits Saturn due to the tides. Now, these fissures are enormous. They extend for hundreds of kilometers. And when they begin to open, you would see a large crevasse opening at approximately 100 miles per hour along its length. It'd be incredibly spectacular. Huge gravitational forces cause the surface to open and contract with incredible velocity. This helps produce the heat necessary to dissolve ice and form oceans beneath the surface. The conditions of the water beneath the surface of Enceladus are ideal for life. It is at the ideal temperature. It would be beneficial for life. Liquid water would be just like seawater here on Earth. And the chemistry of the water we observe erupting from these fissures suggests that it contains salt. It contains organic matter as well. Therefore, we have identified a location in the solar system where there is a strong possibility that there is life right now. In the ice particles, Cassini has detected complex carbon molecules. In conjunction with liquid water, they suggest that perhaps life could exist deep within this mysterious moon. Enceladus is possibly not alone. Another of Saturn's moons might also harbor life. Titan, one of the largest moons in our solar system, the only moon with a thick atmosphere, a frozen world, ice as hard as rock, lakes of liquid methane. Yet, we may also discover evidence of volcanoes and the tantalizing possibility of extraterrestrial life on this planet. Volcanoes are one of the most destructive forces in the universe, as evidenced by Io's raging conflagration and Triton's ice and nitrogen explosions. Even on Saturn's enigmatic moon Titan, however, destruction can lead to the prospect of life. It has a diameter of 3,000 miles, making it larger than Mercury. It has the thickest atmosphere of any moon in our solar system. There is weather, including cyclones, winds, rain, and even lakes, but the temperature is so low that liquid methane replaces water, and it's loaded with essential compounds for life. Titan has proven to be one of the most fascinating locations in the solar system. It's an active world. It is the only moon with a dense atmosphere, an atmosphere very similar to that of Earth due to the presence of nitrogen and, as it turns out, organic molecules. High in Titan's atmosphere, methane gas reacts with sunlight to produce compounds essential to life. But if sunlight consistently converts methane into organic compounds, why does methane not run out? Methane is abundant in the atmosphere, but we know that it is quickly eliminated by sunlight, so it shouldn't be there. There must exist a source of methane. Something on Titan emits methane in a continuous stream. Cassini has spotted what appears to be a crater. Infrared cameras disclose that the crater is surrounded by various types of materials. Scientists believe the green areas may be volcanic, possibly plains of lava ejected from Titan's interior. On Titan, the boiling liquid emitted by volcanoes could be either ammonia or water. Methane and ethane are emitted by Titan's volcanoes, and this is likely the cause of the planet's extremely dense cloud cover and orange atmosphere. This atmosphere likely originated from the outgassing of Titan's volcanoes. Even on a globe as frigid as Titan, volcanoes require heat. On Titan, there are two sources of heat. Radioactive substances heat the interior, and Saturn's enormous gravity caresses the moon, similar to Enceladus. These two forces produce sufficient heat to transform ice into water and liquid methane into gas. Could volcanoes on Titan give life a chance to survive here? The chemical reactions necessary for life as we know it require an atmosphere, a solid surface, liquid water, and heat. Volcanoes could provide everything on Titan. If life does exist on Titan, it would be truly alien. It would breathe hydrogen instead of oxygen and possibly swim through methane reservoirs at 300 degrees below zero. There may be oceans of ethane. Possibly there are tidal pools as well as volcanic and hydrothermal activity. Perhaps volcanic heat could produce enough energy to support life on Titan. That's a speculation, but it can't be ruled out. However, we may not need to travel so far to discover signs of life. We may discover it on Mars, a volcanism-rich world much closer to home. Volcanoes are ubiquitous throughout the solar system. Planets such as Io, Titan, and Triton are intricate, volatile, and violent. Once, we believed that Earth was the only planet with both volcanoes and life. Now, we find volcanoes everywhere, but alien life has yet to be discovered. Volcanoes exemplify the absolute force of creation and destruction. They go hand in hand. It is literally true that if there weren't volcanoes here, we would not be here either. Volcanic cauldrons are the birthplace of life. Volcanoes create new landscapes, seed the atmosphere with complex chemicals, replace the old with the new. If volcanoes are linked to the processes of life, where is life on other planets? Perhaps the origin of the answer lies in ancient times, when the solar system was immature on a planet similar to our own. This is the planet Mars. 3 billion years ago, volcanoes were active. The greatest volcano in the solar system still stands. The cliffs leading up to it are greater than 6 miles in height. Even Mount Everest would be comfortable in their shadow. This is the formidable Olympus Mons. It covers an area the size of Arizona. Its crater alone is 53 miles wide. A structure of this magnitude takes millions of years to construct, a period of time that volcanoes on Earth never have. The Earth's crust is constantly in motion. In the depths of the Earth, a solitary hotspot forces magma to the surface, creating a new volcanic island. While the hot point remains stationary, the surface is in motion. The new island moves away from the hot location and is replaced by a new volcanic island. Mars is different. The crust is locked solid. On Mars, there is simply no tectonic activity. The crust is one big solid plate, and so if there's a hot spot, it just sits there and builds and builds and builds. And you get a larger and bigger volcano. Therefore, Olympus Mons is so enormous. Today, Olympus Mons is an icy remnant of a distant, warmer era. Olympus, an extinct volcano on a fading planet, is now a veritable colossus due to Mars's diminished atmosphere. However, the ancient volcanic terrain of Mars could one day support life. The evidence is readily available on Earth. Volcanoes on Hawaii have formed enigmatic tunnels known as lava tubes, which are formed when rivers of molten rock rush into the ocean. Lava tunnels are formed when there is an underground river of basaltic lava, magma, and molten rock at 2,000 degrees Fahrenheit. Imagine it as an icy river with a crust of ice forming on the surface. It's the same, except here, the crust is solid rock and the river continues to flow beneath, creating this cave, this lava conduit. Recent images imply that Mars volcanoes may have also created lava tubes. Any rocky planet with basaltic volcanism will likely contain lava pipelines. Now, after possibly millions of years of inactivity, these lava tunnels could revive life on the red planet. This existence will be our own. Radiation will be one of the obstacles that future humans will face when attempting to live on Mars. And especially during solar cyclones, the incoming cosmic rays can be lethal. The tunnels and caverns of Mars's extinct volcanoes could one day serve as an ideal home, retaining air and shielding us from harmful radiation. A long-dead volcano could help fill a world with new light. Volcanoes are capable of both destruction and creation. We used to only know about the planets that circled around our sun. But now we know that there are rocky worlds and huge gas clouds that circle other stars. They have a great story to tell. The early history of these planets would have been very, very violent. Planets are made the same way everywhere. They come from the dust and other things that are left over after stars are born. So, if they're all made the same way, what makes them so different? As it turns out, the universe is full of galaxies, gas clouds, stars, and planets. There are 8 worlds in our sun's system. But now we know that they are just a small part of the huge family of planets in the sky. It's a very important moment in the history of science to be sure that there are other systems of planets out there. And in our Milky Way galaxy, which has 200 billion stars, there are probably dozens of planets. NASA sent the Kepler Space Telescope out into space in 2009 on a 6-year mission to find new planets that orbit other stars. So far, they have found more than 400. Some are huge, spinning balls of gas that are 5 times as big as Jupiter. Others are huge, rocky worlds, many times larger than Earth. Some follow wild, erratic orbits, so close to a star they're burning up. One thing is clear. No 2 planets are the same. Each one is unique. But most of these new worlds are very far away and hard to study. Most of what we know about how planets work comes from the 8 that circle our sun. Our own planets come in 2 main types. There are 4 rocky planets in the inner solar system: Mercury, Venus, Earth, and Mars. And in the outer solar system, there are 4 giant gas planets: Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the other 7. When our solar system was born 4.6 billion years ago, they started to develop their own personalities. When the sun ignited, it released a massive cloud of gas and dust into space. All 8 planets, including the metal planets closer to the sun and the gas planets farther away, came from this cloud of space debris. All of the worlds in our solar system are made of the same materials. They're made from the same cloud of gas and dust, but they formed under very different conditions. Some of them formed close to the sun, where it was much hotter, and some formed far away, where it was much colder. And since the situations were so different, the things that came out of them were also different. So, at the beginning of the solar system, there was a pretty even mix of silicates, water vapor, hydrogen, a lot of hydrogen, methane, and other things. These elements in the dust cloud are like ingredients in a cake. They cook in different ways based on how the ingredients are mixed and how hot the oven is. And you'd mix the ingredients just like you did with the cake. Then you'd put it in the oven and bake it, and it would change. So basically, this is what happened in the solar system. Overall, the planet cooks in a slightly different way, depending on how close it is to the sun. Near the sun, where it is hot, gases are burned off and water boiled away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the sun. As a planet moves farther away from the sun, it cooks in a different way. But what kind of planets will form depends on what's in the cloud. Based on what kind of cloud a solar system forms in, it might not have any rocky planets because it didn't have enough materials to make something like Earth. Instead, it might have more gas giants and none at all. If you want planets that are made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the things in it that have a high boiling point start to condense out as solids, and these very small mineral grains can start to form. These tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust molecule and another dust molecule, and they would basically hit each other and make one slightly bigger dust molecule, and they'd keep getting more and more. This process is called accretion. As these things got bigger, they became basically rocks. Then rocks slam into other rocks and form boulders. Boulders smash together to form bigger boulders. At some point, you'll have something big enough that its weight is strong enough to start pulling things towards it. So instead of just crashing into things and getting bigger that way, it was actively pulling things in. At first, there were a lot of young planets in our own solar system. Maybe 100. Most of them didn't make it. If you go to the asteroid belt and look at the asteroid 4 Vesta, you can get a good idea of how big a hard planet has to be before it can pull itself into a sphere shape. Vesta is only 329 miles across, which isn't quite big enough to be a sphere. To become round, a growing planet needs to be 500 miles across. Then, it has enough gravity to crush it into a sphere. Any smaller, and it stays in irregular shape. Every time a round baby planet crashes into something, it makes it hotter and hotter until it starts to melt. Gravity is now starting to sort the heavy things from the lighter ones. Lighter things tend to float up and form a crusty layer, while heavy things, like most metals, fall down and form a much denser core at the planet's center. Finally, the young planets are starting to look like planets. But now, they have to make it through a time of violence and destruction, a cruel time that will decide which planets will live and which will die. After the sun was made, all 8 of our planets came from the same cloud of dust and gas, but they turned out to be very different. There was no real plan for how each of the new planets should be made. They did follow the rules of physics and chemistry, but most of what happened was just a matter of luck. About 4.5 billion years ago, our sun was surrounded by about 100 young planets. It turned into a demolition derby. Planet hit planet. Most were wiped out. The early history of these planets would have been very, very violent, with many of these collisions happening in the last stages of each planet's growth. As these collisions happened and things ran into each other, some of the planetesimals started to grow at the expense of the others. And these things that would eventually become planets grew and grew. As they got bigger, they sucked up all the smaller planetesimals around them, which caused a lot of space debris to hit the surface of the protoplanet. After it was over, there were only 4 different rocky planets left. Because of the things that happened to each planet in the past, they are all so different from each other. Mars is a frozen wasteland. Earth flows with liquid water. Venus is a place full of volcanoes. And Mercury is small, empty, and very hot because of a huge crash. Mercury, for example, has a very thin crust and is very dense. So, it could have been a bigger planet in the past. Then something hit it at an angle, which tore off the lighter crust and left only the dense center. Also hit hard was the young Earth. At the end of the Earth's development, it was hit by something else, which tore apart its mantle and sent the pieces into orbit around the Earth, where they regathered to form the Moon. Something also seems to have crashed into Mars. The crust of the Earth is thinner in the north than in the south. One idea about what might have caused this is that the northern hemisphere of Mars was hit by something early in the planet's history, which blew off a lot of its crust, and that crust started to build up again in the south of Mars. There were two effects of all these collisions. They cut down on the number of baby planets that were still alive, and they brought more ingredients to the survivors. If you had a collision with something that was metal, rich, those chunks would tend to descend down into what was becoming the core, where if you collided with something light or icy, they would tend to just float about and form part of the crust instead. Near the Sun, there were 4 rocky planets that were almost done. They were made of a solid core of hot iron surrounded by a layer of liquid iron and a shell of molten rock. On top of that is a crust on the surface. All of these rocky planets were made the same way from the same basic materials. But each of them was very different. Different sizes and very different destinies. Space may look empty, but it's not. It's full of stuff blown out of the sun. Strong magnetic fields are made by the sun. These fields rise up in giant loops above the surface. When they hit each other, a storm of very hot, very charged particles shoots out into space. The name for it is the solar wind. Astronauts can see it from space, but only when they close their eyes. When you close your eyes, you sometimes see a little flash. And that flash of light is caused by an energetic particle going through your head and interacting with the fluid in your eye, and you see one of these every few minutes. Solar wind could kill the astronauts if they were exposed to a lot more of it. During the Apollo program, there was an explosion on the sun between 2 moon missions that would have killed the astronauts if they were there. So, radiation in space is a big deal. But here on Earth, the solar wind doesn't pose much of a threat because we are protected by an invisible magnetic field that comes from the center of the Earth. You can make magnetic fields from motion by converting the energy of the motion into magnetic energy. Deep inside the Earth, the same thing happens. As the Earth spins, the hot liquid metal flows around the solid core, turning its energy into a magnetic field that comes out of the poles. It keeps the solar wind from getting into the atmosphere of the planet. And if the planet has a magnetic field, the magnetic field will send the solar wind around the planet. The solar wind is pushed away from Earth by the magnetic field, which protects the atmosphere and everything on the surface. Big storms of solar radiation can sometimes mix up the magnetic field. Then, big light shows called auroras happen over the poles. Without a magnetic force field, Earth's atmosphere and water would be blown away by the solar wind, leaving a planet that is dead and dry, a lot like Mars. Mars was made the same way Earth was, but today it's cold and dry, and there's not much going on. So why have the 2 planets changed so much? NASA sent 2 robots to Mars in 2004 to find out what was there. The Spirit and Opportunity rovers looked at miles of the surface of Mars. They proved that Mars is a dry, dangerous desert with only the atmosphere of Earth. But they did find signs that water used to be there. Mars wasn't always a dry, barren place. We have found strong evidence that water was once below the surface, rose to the surface, and evaporated away. In a few places, we can also see ripples that are made when water flows over sand. So, not only was there water under the ground, it had flowed across the surface. If Mars used to have water, it probably also had a lot of atmosphere around it. So what happened? We can see that there were volcanoes on Mars in the past, so it had a hot interior at some point. And because it was made of the same stuff as Earth, it would have had a hot iron core surrounded by liquid metal in the middle. It should have also had a magnetic field. The question is, where did it go? Early in the planet's history, Mars apparently had a strong magnetic field. And it was probably caused in the same way as it is on Earth. But Mars is a smaller planet than Earth. Because of this, it will lose heat more quickly. And that means that a liquid core can become solid when it freezes. If you completely freeze the core, the convection will stop. The flow stops, and the magnetic field disappears. As soon as the magnetic shield stopped working, the solar wind blew away the atmosphere and the water evaporated. Mars turned into a cold, empty place. The rocky planets, Mars, Earth, Venus, and Mercury, all formed within 150 million miles of the Sun. But 4 times farther out, the Sun baked a very different kind of planet. These monsters are very big, made of gas, and have no solid surfaces at all. So far, astronomers have found more than 400 new planets in solar systems far away. Almost every one of them is huge and made of gas. Our solar system has 4 of these so-called gas giants: Jupiter, Saturn, Uranus, Neptune, all of which have thick, soupy atmospheres with lots of hydrogen, helium, and methane. Why are these outer 4 made of gas when the inner ones are rocky? It's very cold here, 500 million miles from the Sun. At the start of the solar system, there was some dust, but mostly gas and water, frozen in ice grains. It was cold enough to make solid snow where the big planets began to form. And we think that we were able to make ice snowflakes, and that these were able to stick together to form the cores of the giant planets. We think that's why the big planets might have grown so big. Because there was so much ice and gas, their cores grew to be about 10 times the size of Earth. A lot of gravity came from these big cores. They had so much pull that they sucked in all the gas around them and made thick, soupy atmospheres that went down tens of thousands of miles. The more gravity they made, the bigger they got. More and more dust and debris kept getting pulled towards the planets, and this is what made up their moons. Each of Jupiter and Saturn has more than 60 moons. The gas planets have something else that makes them unique: rings. Saturn is different from the other planets because it has these beautiful rings. It turns out that Jupiter, Uranus, and Neptune also have rings, but they are very weak and hard to find. But they are there. There are rings around all 4 of the gas giants, but Saturn's are the most obvious. From far away, Saturn's rings look like a single flat disk, but in reality, they are made up of thousands of small rings that are only a few miles wide each. When the Cassini probe flew by, it found that billions of pieces of ice and space debris were moving around inside the rings at up to 50,000 miles per hour. These pieces of ice and rock hit each other all the time. Some of them turn into small moons. Some of them fall apart. But they never grow bigger because Saturn's huge gravity pulls them apart. Scientists are just now starting to figure out how the rings came to be. The idea is that a comet hit a moon and knocked it out of its orbit. bringing it closer to the planet. Saturn's gravity tore it to pieces. All of that stuff got stuck in rings that went around the planet. But the real mysteries of the gas giants are deep inside them, tens of thousands of miles below the clouds. Here is where things really get going. It's a place so extreme that it goes against the natural laws. Most of the new planets we find orbiting faraway stars are huge gas planets. They are so big that Jupiter seems small next to them. But nobody knows what happens inside gas giant planets, whether they are in our solar system or far away. We know that Jupiter's thick atmosphere goes down 40,000 miles, and we can see bands of gas moving at high speeds that make violent storms on its surface. But we don't know what's happening inside, far below the storms. NASA sent the Galileo spacecraft on a 14-year trip to Jupiter to find out. December 7, 1995. Galileo sent a probe into Jupiter's atmosphere, which it did at a speed of 160,000 miles per hour. As it fell through the thick air, the parachute slowed it down. It saw lightning in the clouds and 450-mile-per-hour winds. The probe transmitted data back to Earth for 58 minutes. What happened to the Galileo probe that we dropped in? It didn't hit anything. It just kept falling into Jupiter's environment, and the pressure kept going up and up and up. As it fell, it measured pressures 23 times higher than on Earth and temperatures over 300 degrees higher than on Earth. When you're in the environment of a gas giant, and you go deeper and deeper into this soup of hydrogen, which has no solid surface, it can still be very heavy. And so eventually you would be crushed by the overlying weight of the material that's there. Even though the probe only went 124 miles down before it was crushed, it showed scientists what Jupiter's inside looked like. But the dark heart of the planet still remains a mystery. Like some rocky planets, the gas giants have a magnetic field too. Jupiter's magnetic field is 20,000 times stronger than Earth's, and so big that it goes all the way to Saturn, which is more than 400 million miles away. Like on Earth, Jupiter's magnetic field keeps the solar wind away from the atmosphere and keeps it safe. When scientists looked at Jupiter's magnetic field, they found that it affected the moons of Jupiter. The volcanic moon Io orbits only 217,000 miles from the planet. Every second, Io's volcanoes send a ton of gas and dust into space. It gets even stronger because of Jupiter's magnetic field, which makes powerful belts of radiation. And this makes the area around Jupiter very busy in a lot of ways. If you point a radio antenna at Jupiter, you can hear how the planets and the magnetic field interact with each other. Jupiter and Saturn can make auroras without the solar wind. They make their own magnetic fields because they're so big. These auroras show that planets with gas also have magnetic fields. But how do magnetic fields get made on gas planets? On Earth, the job is done by a very hot liquid metal that spins around the planet's solid iron core. Most likely, gas planets do about the same thing. But gas planets don't have iron cores that get very hot. They formed around frozen cores of dust and ice. So we don't really know what's going on inside. We really don't know what makes up the deepest parts of Jupiter's interior. So it's possible that Jupiter has a solid core at its center, or it could just still be liquid. We might never know. No probe could ever go the 44,000 miles to the center of the planet to look into it. Galileo was destroyed before it could reach the center of the planet. Gravity and heat shape how planets evolve from their inner cores to their outer atmospheres. They're the great creative forces in planet building. But there's one more thing that has a big effect on how planets turn out. And that ingredient is water. Planets may look like they are fixed and don't change, but they are always changing. One planet in our solar system lost its atmosphere and turned into a desert. Another planet got too hot and changed into the planet from hell. Planet Earth has also changed, and it was water that changed the game. When you look at Earth from space, you can see a lot of water. We are, after all, the blue planet. That means it must be very wet, right? At first glance, our world seems to have a lot of water. After all, 3/4 of it is made up of oceans. Not true. Only 0.06% of the mass of the Earth is water. Some water is on the surface as oceans, and some is stuck in the mantle. But actually, the Earth is a relatively dry rock. All of the inner rocky planets formed very close to the sun, so they started off dry. Any water they might have had either evaporated or was blown away when things hit. These massive collisions that formed the Earth were so energetic that if there had been water here, it would have evaporated and left the Earth. So where did all the new water on Earth come from? It's now here. When you look at Jupiter, Saturn, Uranus, and Neptune, you can see that they have a lot of water locked up inside them. And even more dramatically are the moons. At least half of the water on the moons of Jupiter, Saturn, Uranus, and Neptune. A lot of water was out there. So, how did some of it get to planet Earth? And the answer is almost certainly that there were some asteroids and comets left in our solar system that were far enough from the sun that they could keep their water. There were millions of these watery asteroids and comets that flew into the inner solar system. Some of them crashed into our planet. Over time, the Earth got the water that used to be in the asteroids. This is what makes up the mass of water that now covers almost all of the Earth. Without surface water, there would have been no life. What about water that is too much? The oceans would be much deeper and cover the continents and even Mount Everest. And it's likely that the exact amount of water that the Earth has is what made it possible for us, Homo sapiens, to evolve into a technological species. About 4 billion years ago, a blizzard of comets and asteroids brought just the right amount of water to Earth. This is how the world we know today came to be. And it's possible that the same thing is going on somewhere else in the universe right now. There is a lot of water out there, that much is certain. The most common atom in the universe is hydrogen, and oxygen is one of the next most common. H2O will definitely be a very popular molecule, which is exactly what is happening in our universe. So, water is everywhere in the universe, and we're finding that planets are too. But we haven't yet found another planet where water is liquid. More than 400 new planets have been found by scientists. Our world doesn't look like any of them. What we haven't found yet is a planet around another star that is about the same size, mass, and chemical makeup as Earth. So, it remains an extraordinary holy grail for humanity to find other abodes that remind us of home. But we'll keep looking. We know that our galaxy alone has around 200 billion stars, and up to 40 billion of them could have their own planets. We are entering what will be called the golden age of planetary exploration in the future. We'll start to really understand for the first time how different things are out there. I think this is going to be a very exciting time. The laws of physics and chemistry tell us how planets are made. Many scientists think it's only a matter of time before we find another planet like Earth, one that formed from the same materials in the right place with the right amount of water. One thing is certain. There are billions of planets out there waiting to be discovered. Ladies and gentlemen, welcome to today's topic, aliens. Are they real? Do they exist? And if so, what do they look like? Today we will dive deep into the topic of aliens, exploring various theories and facts about these mysterious creatures. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. Here are a few theories about aliens. Extraterrestrial life exists. This is the theory that life exists elsewhere in the universe, perhaps even within our own solar system. Microbial life could potentially exist on Mars, or some of the moons of Jupiter and Saturn, for example. More complex life forms, such as intelligent civilizations, could also exist on planets orbiting other stars. The Fermi paradox. The Fermi paradox suggests that if intelligent life is common in the universe, why haven't we detected any evidence of it? Some theories suggest that intelligent civilizations tend to self-destruct, while others propose that they are too far away or have no desire to communicate with us. Ancient aliens. This theory suggests that aliens have visited Earth in the past and have influenced human history and culture. Proponents of this theory point to ancient artwork and texts as evidence of alien visitation. UFO sightings. Unidentified flying objects are often cited as evidence of alien visitation. While many sightings can be explained by natural phenomena or human-made objects, some remain unexplained and could potentially be evidence of extraterrestrial visitation. The simulation theory. This theory proposes that our entire reality is a computer simulation created by an advanced civilization. While not specifically about aliens, this theory suggests that the creators of the simulation could potentially be an extraterrestrial civilization. To start with, let's address the most basic question: do aliens exist? Well, according to the Drake equation, which was developed in 1961 by astronomer Frank Drake, the probability of intelligent life existing elsewhere in the universe is high. The equation takes into account factors such as the number of stars in our galaxy, the number of planets that could potentially support life, and the probability of life forming on those planets. Using these factors, the Drake equation estimates that there could be millions of intelligent civilizations in our galaxy alone. But the question remains, have we ever encountered these civilizations? Many people believe that we have, and there are countless stories of alien sightings, abductions, and encounters. However, there is little concrete evidence to support these claims. So, let's explore some of the most popular theories about what aliens might look like. The traditional image of aliens as small, green, big-eyed beings is a product of popular culture. However, it is unlikely that aliens would look anything like this. In fact, it is impossible to predict what aliens might look like, as their appearance would depend on the conditions of the planet they evolved on. For example, if an alien species evolved on a planet with high gravity, they might have shorter, stockier bodies. If they evolved on a planet with a harsh, radiation-filled environment, they might have evolved to be more resilient to radiation. It's also possible that some alien species might not even have bodies as we know them. They might exist as pure energy, or as a hive mind collective. But why would aliens visit Earth? There are a few possible reasons. Some scientists speculate that aliens might be interested in our planet because of its unique location in the universe. Earth is in a Goldilocks zone. It's not too hot, not too cold, and has the right conditions for life to thrive. Aliens might be interested in studying our planet to learn more about how life can survive in these conditions. Another reason aliens might visit Earth is to make contact with us. If there are millions of intelligent civilizations in the galaxy, it's possible that some of them are trying to communicate with us. However, if this is the case, they might be communicating in ways that we can't even comprehend. Their methods of communication might be vastly different from ours. So, what should we do if we ever do encounter aliens? Many scientists believe that we should approach any encounter with caution. We should avoid making any sudden movements or aggressive actions, as these might be misinterpreted by the aliens. Instead, we should attempt to communicate in a peaceful and non-threatening manner. If we do make contact with aliens, it could have profound implications for our understanding of the universe. It could challenge our beliefs about our place in the cosmos and force us to confront some of the big questions about life, the universe, and everything. Now that we've explored some of the theories and possibilities of alien life, let's consider the idea of the Fermi paradox. This paradox asks the question, if there are so many intelligent civilizations out there, why haven't we seen any evidence of them? Why haven't we detected any signals or observed any spacecraft from other worlds? One possibility is that advanced civilizations tend to self-destruct. With technology comes the potential for destruction, whether through environmental damage, war, or some other catastrophe. It's possible that many intelligent civilizations reach a point where they are unable to sustain themselves and ultimately fail. Another possibility is that intelligent civilizations have no desire to make contact with us. Perhaps they are simply not interested in Earth or in communicating with other species. Or perhaps they are too far away to detect our signals and we are too primitive to detect theirs. Regardless of the reasons, the Fermi paradox remains a mystery and a subject of much speculation. But let's turn our attention to the possibility of life in our own solar system. While we haven't found any evidence of intelligent life, there are some promising signs that microbial life might exist on other planets or moons. For example, NASA's Mars rover has detected methane on the planet's surface, which could be a sign of microbial life. And scientists have found evidence of subsurface oceans on some of Jupiter and Saturn's moons, which could potentially support life. If we do find evidence of microbial life in our own solar system, it would be a major discovery and could have significant implications for our understanding of life in the universe. Let's consider the potential implications of discovering intelligent life. If we were to make contact with an alien civilization, it could have profound impacts on our society and our understanding of the universe. For one, it could challenge our existing beliefs and worldviews. We might need to reevaluate our ideas about our place in the cosmos, our religious and philosophical beliefs, and our understanding of the origins of life. It could also raise questions about the ethics of interacting with other intelligent species and the responsibilities that come with such interactions. Another potential impact is on our technology and scientific progress. If we were to encounter a more advanced civilization, we could learn from their technology and knowledge, potentially accelerating our own progress. On the other hand, it could also pose a threat if the aliens have hostile intentions towards us. It's difficult to say for certain whether aliens, if they exist, would be dangerous to us. We have no concrete evidence of intelligent extraterrestrial life, and so any speculation about their intentions or behaviors is purely hypothetical. Some people argue that aliens could be dangerous if they are more technologically advanced than us and have the ability to conquer or destroy us. Others point out that any civilization advanced enough to travel through space would likely have a more sophisticated understanding of the universe and may be more peaceful and cooperative. It's also possible that aliens could be indifferent to us, simply observing us from a distance without any intention to interact with us at all. Overall, while it's fun to speculate about the potential dangers of alien life, the truth is that we simply don't know enough to make any definitive conclusions about their intentions or behaviors. The search for extraterrestrial life should be approached with an open mind and a healthy dose of curiosity rather than fear or paranoia. Regardless of the potential impacts, the search for intelligent life continues. We are constantly developing new technology and refining our techniques to search for signals and evidence of other civilizations. And while the chances of finding intelligent life may be slim, the pursuit of knowledge and discovery is a worthy endeavor in and of itself. That's all for today's topic of aliens. We hope you've enjoyed this discussion and learned something new. If you have any questions or comments, please leave them in the comment section below. Thanks for tuning in, and we'll see you next time. We inhabit a galaxy known as the Milky Way, which contains hundreds of billions of stars. How did we arrive at this point, and what is our future? These concerns involve galaxies in every aspect. The known universe contains 200 billion galaxies, each of which is unique, immense, and dynamic. Where do galaxies come from? How do they work? What is their future? And how will they die? If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. This is the Milky Way, our galaxy. Approximately 12 billion years old, the galaxy is a vast disk with enormous spiral arms and a central nucleus. It is only one of countless galaxies in the universe. Galaxies are massive assemblages of stars first and foremost. A typical galaxy could contain 100 billion stars. They are actually stellar nurseries, the locations where stars are formed and perish. The stars in a galaxy are formed in nebulas, which are concentrations of dust and gas. Our galaxy contains billions of stars, many of which have planets and moons orbiting them. But for a very long time, we knew very little about galaxies. A century ago, we believed that the Milky Way was the only galaxy in the universe. In 1924, astronomer Edwin Hubble altered the entire situation. Hubble observed the universe using the most sophisticated telescope available at the time, the 100-inch Hooker on Mount Wilson near Los Angeles. Far, far away, he saw hazy masses of light in the darkness of the night sky. He realized they were not even separate stars. They were entire star-filled cities, constellations far beyond the Milky Way. The astronomers received an existential jolt. We went from the Milky Way galaxy being the only galaxy in the universe to billions of galaxies in a single year. Hubble made one of the finest discoveries in the history of astronomy when he discovered that the universe contains a large number of galaxies rather than just one. This is the Whirlpool Galaxy. It comprises over 160 million stars and is characterized by two enormous spiral arms. In addition, the stars of the huge elliptical galaxy M87 shine with a golden hue since it is one of the oldest galaxies in the cosmos. And this is the Sombrero Galaxy. Its massive bright core is surrounded by a cloud of gas and dust. All galaxies are very beautiful. They stand in for the fundamental building block of the cosmos. As they spin across space, they resemble enormous pinwheels. Galaxies are enormous on a grand scale. On Earth, we measure distance in miles. In space, astronomers use light years. This is how far light can travel in a year. Our galaxy's diameter is over 100,000 light years. and we're now located at a distance of 25,000 from its center. However, in the grand scheme of things, even it seems like a tiny dot. While the Milky Way seems enormous from Earth, when compared to other galaxies, it is really rather little. Andromeda, the galaxy closest to us, is about 200,000 light-years wide, making it twice as large as the Milky Way. M87 is the largest elliptical galaxy in our own cosmic backyard, and much bigger than Andromeda. But M87 is tiny compared to this giant. 6 million light-years across, IC1011 is the biggest galaxy ever found. It's 60 times the size of our own Milky Way. It's common knowledge that galaxies are enormous and ubiquitous. But why is this the case? The origin of galaxies is a key mystery in astrophysics. Approximately 13.7 billion years ago, the universe began with what we refer to as the Big Bang, a period of intense heat and density. We know that there could not have been anything like a galaxy at that time. So galaxies must have come from that very early universe and formed from it. For stars to form, and for galaxies to form from those stars, gravity is essential. After the Big Bang, the first stars began to emerge only 200 million years later. The earliest galaxies formed as their masses began to clump together because to gravity. Thanks to the Hubble Space Telescope, we can now see the early universe when galaxies were just beginning to form. Numerous galaxies are visible to the Hubble, the light we see from distant galaxies now. However, really departed those objects many millions or perhaps billions of years ago. What we see now is the distant past of those galaxies since it took so long for their light to get to us. The Hubble Deep Field reveals a collection of fuzzy dots. They are quite different from the galaxies we see now. We can hardly make out these little specks of light. Those fuzzy patches of light are really millions or billions of stars beginning to combine. The oldest galaxies are represented by these barely visible blotches. They began to take shape around 1 billion years after the Big Bang. However, Hubble's range of visibility ends there. A second sort of telescope, one too large to send into space, is required if we are to travel much farther back in time. Not only can the telescope identify primordial galaxies, but it can also trace their evolution. The evolution of galaxy and galaxy cluster formation may be followed. All the galaxies that have developed since the cosmos was just a few 100,000 years old are leaving their imprints for us to observe. Finally, scientists can begin to answer the question, what did young galaxies look like? Galaxies have evolved from clusters of stars to the complex web of systems we see today, and this process is being seen by astronomers. As far as we can tell, the greatest structures in the universe today originated as star clusters, evolved into galaxies, formed clusters of galaxies, and ultimately coalesced into superclusters of galaxies. There was a lot of stardust, gas, and clumpy structures in the early galaxies. However, modern galaxies seem organized and tidy. When and how can tangled clusters of galaxies become neatly organized spirals and pinwheels? Gravity is the explanation. Galaxies are molded by gravity, and its effects determine their fate. At the center of most galaxies lies an unfathomably strong and destructive gravity source. And our own Milky Way has one hidden at its core. Over 12 billion years have passed since galaxies first appeared. These stellar conglomerations may take many forms, from spirals to giant spheres of stars, as far as we can tell. However, there is still a great deal we don't understand about galaxies. How did galaxies evolve into their present forms? Did spiral galaxies always have to be spirals? The answer is almost certainly no. Young galaxies are a mix of stars, gas, and dust. They are untidy and chaotic. They begin as chaotic formations, like the Whirlpool galaxy, then over billions of years develop into more orderly forms. The Milky Way wasn't born from a single galaxy, but from a cluster of several. Our Milky Way originated as a collection of disparate formations, objects of varying sizes and shapes that gradually merged to become the galaxy we see today. Gravity is what binds the various components together. Over time, it gradually draws stars closer. They pick up speed and flatten out into a disk shape. Massive spiral arms gather stardust and gas. This process was carried out countless times during the course of the cosmos. While visually distinct, these galaxies share the fact that they all seem to circle the same central object. For a long time, researchers pondered what might possibly alter a galaxy's behavior. And they found out: a black hole. And not just any kind of black hole, but it's a supermassive black hole. The discovery of extreme amounts of radiation coming from the centers of certain galaxies was the first indication of supermassive black holes. Black holes in these galaxies are eating their surroundings, much like a giant Thanksgiving feast. The gas and stars are the supermassive black hole's dinner. Sometimes black holes consume their food so rapidly that they spew it out into space as beams of pure energy. They refer to it as a quasar. The presence of a quasar indicates the presence of a supermassive black hole at the center of the galaxy. However, what about the Milky Way? There's no quasar here. Does it rule out the existence of a supermassive black hole? Observing the motion of the stars is the key to finding the supermassive black hole in the heart of our Milky Way. Like the planets that circle the sun, the stars also move due of gravity. What we discovered was a bizarre and violent environment. At the center of our galaxy, everything is more extreme. Things move very quickly. The stars will be passing one another at high speeds. It is unlike any other place in the universe. The photographs of the stars in orbit showed a remarkable phenomenon. They had to have been traveling at 1,000,000 miles per hour or more. Only a gigantic black hole has the energy to toss large stars around like that. This curvature was the conclusive evidence for a supermassive black hole at the heart of our galaxy, as it is the black hole's gravity that drives the orbits of these stars. A massive black hole measuring 15 million miles wide sits at the heart of our Milky Way galaxy. So, is there any danger to Earth? We are in absolutely no danger of being sucked into our supermassive black hole. It's simply too far away. In reality, the distance between Earth and the supermassive black hole in the heart of the Milky Way galaxy is 25,000 light-years. That's many trillions of miles. For the time being, Earth is secure. Although supermassive black holes are the source of enormous quantities of gravity, they are not strong enough to bind galaxies together. In reality, the rules of physics dictate that galaxies should accelerate away from one another. So what's stopping them? Because there's something stronger than a gigantic black hole waiting to be discovered. It is invisible and very difficult to detect. It's called dark matter, and it's everywhere. Supermassive black holes discovered by astronomers are found in the centers of galaxies and are responsible for the rapid movement of stars in their vicinity. However, They are insufficient to hold together all of the stars in a vast galaxy. So what does hold them together? It was a mystery until a maverick scientist proposed that something unknown was in action. Fritz Zwicky, a Swiss astronomer, pondered in the 1930s why galaxies clustered together. He reasoned that because they weren't producing enough gravity, they should be flying apart. However, the force of our own gravity was insufficient. Therefore, he deduced that it must be something that had never been discovered before, something that had never even been considered, and he called it dark matter. Fritz Zwicky was decades ahead of his time, and that's why he graded on the astronomical community. And this is a brilliant idea. But he was correct, you know. It's possible that individual galaxies are also held together by the mysterious substance that Zwicky dubbed dark matter. Galaxies rely on dark matter as a kind of protective framework that keeps them from collapsing and moving about. Now, scientists have discovered that dark matter does more than just bind galaxies together. It may have also triggered their evolution. Scientists believe that after the Big Bang, dark matter started to cluster, and these dark matter clumps evolved into the galaxy's nucleus. However, the nature of dark matter is still a mystery to physicists. Weird things happen with dark matter since we don't know what it is. Obviously, it's not constructed from the same substance that humans are. You can't push against it. You can't feel it. However, it is likely everywhere. It's a ghost-like material that will pass right through you as if you didn't exist at all. Although our understanding of dark matter is limited, it seems to be abundant across the cosmos. That means there must be at least 6 times as much dark matter as regular matter, what humans are comprised of in the cosmos. And the way the cosmos seems to function depends on it. Observations of its effects on light have led to its recent indirect detection in deep space. Through a process known as gravitational lensing, it warps the light. The existence of dark matter may be tested using gravitational lensing. As a ray of light from a distant galaxy travels towards us, its course will be bent around a huge collection of dark matter due to the latter's greater gravitational attraction. Some distant galaxies indeed seem stretched and warped when seen via the Hubble telescope. The picture distortion is due to the presence of dark matter. We can determine the density of dark matter by carefully examining the forms and degrees of distortion of these galaxies. Now more than ever, the importance of dark matter to the cosmos is undeniable. It's what makes galaxies form and stops them from collapsing. Even though it's invisible and undetectable, dark matter rules the cosmos. These galaxies seem to be completely alone. It's true, they are trillions of miles apart. But actually, they live in groups called clusters. And these clusters of galaxies are linked together in superclusters, containing tens of thousands of galaxies. The Milky Way's place in the cosmos remains a mystery. If you look at the overall image, you'll see that our galaxy is associated with a smaller group of galaxies, including about 30 members in total, and that our galaxy and Andromeda are the 2 largest members of this group. Further observation reveals, however, that our galaxy is embedded inside the Virgo supercluster. Researchers are now making maps of galaxy clusters and superclusters to better understand the cosmos. Galaxies are the immense star empires. The shapes range from enormous balls to intricate spirals. The problem is that they are always evolving. When we stare out into the cosmos, it's easy to assume that our galaxy hasn't changed in eons. It's not. The Milky Way is a dynamic galaxy. Over cosmic eons, its basic nature has been changing. Galaxies don't only evolve, they move as well. And sometimes they run into each other. The two galaxies will merge over millions of years when they collide. This kind of collision occurs all the time in the cosmos. Our own Milky Way is no exception. We are on a collision course with the galaxy Andromeda, and that's terrible news for the Milky Way. At a speed of around 250,000 miles per hour, our Milky Way galaxy will collide with Andromeda in about 5 billion to 6 billion years. It's all over for the Milky Way galaxy. If you could look out into space, you'd see the whole Andromeda galaxy hurtling toward us at a tremendous rate of speed. As the two galaxies interact, they both become more and more disturbed and closer together. There will be a dance of death between the two galaxies. Whenever galaxies collide, they release clouds of gas and dust in all directions. As galaxies collide, their combined gravity rips stars from their orbits and launches them into the void. As we approach doomsday for the Milky Way galaxy, it would be spectacular. The two galaxies will ultimately pass through one another and merge into a single one. The Milky Way and Andromeda as we know it will cease to exist, and Milkomeda will be born, and it will look like a whole new galaxy. There's no escaping what's going to happen. The question is, what's it mean for planet Earth? We may either be thrown out into outer space when the arms of the Milky Way galaxy are ripped apart, or we could wind up in the stomach of this new galaxy. Stars and planets will be pushed all over the place, so this may well be the end of planet Earth. Galaxies all over the universe will continue to collide. But this age of galactic cannibalism will eventually pass. Because there is an even more destructive force in the universe, a force that nothing can stop. It will eventually tear the cosmos apart by stretching everything to the point that galaxies are pushed apart from one another. Researchers have identified a new cosmic power. It's called dark energy. Unlike dark matter, dark energy has the opposite effect. It pushes galaxies apart rather than bringing them together. Dark energy, which we've only discovered in the last decade and which dominates the universe, is significantly more enigmatic. We don't have the slightest idea why it's there. What it's made from, we don't really know. We are aware of its presence, but beyond that, our understanding of it is limited. Dark energy is really weird. Things resist and are pushed away from one another as if space itself contained tiny springs. In the far future, scientists predict that dark energy will triumph over dark matter in the cosmos. And with that triumph, galaxies will finally begin to drift apart. Galaxies will eventually die off due to dark energy. It will do this by accelerating the expansion of the universe, forcing all galaxies to recede farther and further away from us until they become invisible and travel faster than the speed of light. Therefore, everything else in the cosmos will vanish before our own eyes. The remainder of the cosmos won't vanish today or tomorrow, but it may after 1 trillion years. Galaxies will be left alone in the void. However, this will not occur for an extremely lengthy period. The cosmos is doing well right now, and galaxies are creating favorable circumstances for life to exist. Without galaxies, I wouldn't be here. You wouldn't be here. Maybe not even life itself would exist. This is fortunate for us. The only reason why life has evolved on Earth is because our minuscule solar system was formed in the correct region of the galaxy. If we were any closer to the center, we wouldn't be here. Life in the center of a galaxy may be extremely hazardous. In point of fact, the proximity of our solar system to the core of our galaxy would render it so radioactive that it would be impossible for life to continue in any form. Too far away from the center would be just as bad. Out there aren't as many stars. We might not exist at all. We are therefore, in a sense, in the Goldilocks zone of the galaxy. Neither too close nor too far away, but just right. There may be millions of stars in the cosmic Goldilocks zone, where conditions are just suitable for life. Furthermore, if our galaxy can support life, then other galaxies should be able to as well. The cosmos is very large, and the really incredible part is that we continue to learn new things about it. Every time we believe we've figured out a solution to an issue, we uncover that it's really part of an even greater one. That's awesome. Our Milky Way galaxy and the galaxies beyond it are rife with mysteries and unanswered questions. Who would have guessed 20 years ago that we would be able to identify the black hole at the center of the galaxy? Who would have predicted 20 years ago that the astronomical community would accept the existence of dark matter and dark energy? We should be astonished to be alive at this particular moment in cosmic history, on this particular planet, on the fringes of this particular galaxy, with the ability to ponder questions and seek answers across the whole cosmos. Galaxies are born. They evolve, they collide, and they die. The Milky Way is a fortunate home for intelligent life. Our fate is intertwined with that of every galaxy. Ultimately, our fate rests in their hands since they are the ones who created us and are shaping our identities.
Beyond the Milky Way. With the size and shape of the galaxy measured, the question of our place in creation now shifted from the position of the Sun within the galaxy to the nature of the universe itself. If the progress from Copernicus through Newton to Leavitt and Shapley appears relatively fast, certainly when viewed in the context of the glacial progress through the 2,000-year dominance of Aristotelian thinking, then the decade that followed Shapley's determination of the size of the Milky Way might be described as an intellectual avalanche. The revolution was fueled from two sides. A new generation of telescopes and the increasingly sophisticated observational techniques developed by astronomers like Leavitt, Hertzsprung and Shapley provided the data, and in parallel, theoretical physics experienced a revolution. Claims of revolutions or paradigm shifts have to be made with great care in science. Indeed, the terminology is quite unfashionable in certain academic circles. But from a physicist's perspective, there is no doubt that physics experienced a revolution in 1915, because in November of that year, Albert Einstein presented a new theory of gravity to the Prussian Academy of Science. The theory is known as general relativity, and it replaces Newton's law of universal gravitation. Many physicists regard general relativity as the most beautiful piece of physics yet devised by the human mind, and we will explore why this is so a little later. For now, let us note that the Big Bang, the expanding universe, black holes, gravitational waves, and the whole evocative landscape of 21st century cosmological language began, absolutely, with the publication of general relativity. The parallels with the Newtonian revolution are clear. Without Newton's laws, there is no deep understanding of the solar system and the motions of the planets. Without general relativity, there is no deep understanding of the large-scale structure and behavior of the universe. But we are getting ahead of ourselves. As the second decade of the 20th century dawned, the size and shape of the Milky Way galaxy was established, albeit with rather large errors, but the true extent of the universe beyond our galaxy was still hotly debated. Could we at least cling to a sort of token pre-Copernican fig leaf and place our galaxy at the center of the universe? The desire to be special runs deep. The last intellectual rearguard action against our demotion can, rather theatrically, be said to have been played out on a single evening on the 26th of April 1920 in the Baird Auditorium at the Smithsonian Museum of Natural History, Washington, D.C. This is, of course, an oversimplification, but allow me a minute to enjoy the sound of the outraged, shaking jowls of 1,000 historians of science before I qualify and partially justify this hyperbolic claim. The Mariner 10 mission had enabled scientists to see about half of the planet, so the first real glimpses into the terrain of Mercury came from the flybys of Messenger. As planetary scientist Nancy Chabot explains, before Messenger, we had only seen 45% of the planet, and we saw some stuff during the flybys before we went into orbit. But after orbiting the planet, we've now mapped 100% of the planet and seen nearly everywhere. There are some permanently shadowed regions which are still mysterious, but after mapping the full planet, we have a good idea of what the surface looks like, and craters are absolutely a dominant landform. This planet has been sitting there for billions of years and been hit over and over, and it hasn't had a lot of processes to destroy those craters. Amongst the thousands upon thousands of craters on Mercury, the largest by far is Scariest Planitia, a lowland basin 1,525 kilometers in diameter that is thought to have formed in the early years of the solar system around 3.9 billion years ago. It was first spotted as Mariner 10 sped past in 1974, but due to the trajectory and timing of the craft, only half of it was lit, so the full character of this crater remained a mystery for another 30 years, until Messenger could photograph it in all of its glory. Taking one of its very first photos, Messenger revealed Scariest to be bigger than had been previously estimated, encircled by a range of mountains rising 2 kilometers from the Mercurian surface, whose peaks create a 1,000-kilometer boundary around the lava plains within. On the other side of the mountains, the vast amount of material that was lifted from the planet's surface at the moment of impact formed a series of concentric rings around the basin, stretching over 1,000 kilometers from its edge. The collision that created Scariest hit Mercury with such force that it also had more global consequences. Messenger photographed in great detail an area named, in the not particularly scientific vernacular, the weird terrain, a region at the planet's diametrically opposite point, the antipode to Scariest. This area of strange geological formations, distinct from the rest of the surrounding terrain, was likely created by the seismic shock wave of the Scariest impact, reverberating through the whole of the planet. Right up until the end of its mission in 2015, Messenger continued to uncover many of Mercury's secrets, including a few very particular surprises. Using a combination of photography, spectroscopy, and laser topography, Messenger revealed tantalizing evidence that even this close to the Sun, water ice can exist on the surface of a planet. Even though the Sun blasts much of Mercury's surface, the tilt of its rotational axis is almost zero, so there are craters and features around the planet's poles that never see direct sunlight. Combined with the lack of atmosphere, these regions are forever exposed to the freezing temperatures of space, and it's in this environment that Messenger was able to record the clear signature of water ice. Here, in the eternal night of a polar crater, it's cold enough for ice to survive for millions of years, just meters away from the savage ferocity of the sun's light. However, Messenger's most startling discovery was still to come. The mission objectives had been developed to explore the deep history of Mercury and provide data to test against our theories of the formation and early life of the planet. Messenger was equipped with a collection of spectrometers designed to analyze the composition of Mercury at different depths. The Messenger team had worked on a detailed set of predictions outlining the chemistry of the planet. But as the spacecraft began to sniff at the Mercurian surface, it soon became clear that our assumptions had not been quite right. As the gamma-ray and X-ray spectrometers analyzed the elements on Mercury's surface, they began to measure the unexpected characteristic signature of a number of elements such as phosphorus, potassium, and sulfur at much higher levels than they were expecting. Up to this point, The working hypothesis had been that during the formation of Mercury and all the rocky planets, as the rock condensed and combined to form the planet, the heavier elements like iron would sink towards the center, forming the bulk of the core, while the lighter elements, such as phosphorus and sulfur, would remain near the surface. These more volatile elements would then be expected to be stripped away from the surface, particularly on a planet like Mercury, which is so close to the Sun. And yet the messenger data confirmed high levels of potassium, and sulfur was detected at 10 times the abundance of the element on Earth or the Moon. Both are volatile elements, easily vaporized, and when this close to the Sun, they simply should not have survived the planet's birth. On top of that, the messenger data confirmed what we had long suspected about the structure of Mercury, that it is the densest of all the planets, with a massive iron core making up 75% of the planet's radius, compared to just over 50% here on Earth. The core creates a strange lopsided magnetic field, indicating that the internal dynamics of the planet are different to anything we have seen before. All of this adds up to making Mercury something of a mystery, as nothing quite accords. The eccentric orbit, the abundance of volatile elements on the surface, and the oversized iron core all point to the planet having a history far more complex than was first imagined. And the only explanation to make sense of the messenger data is that Mercury was not born in its current sun-scorched position. It has long been supposedly known that the orbits of the planets are eternal, stable loops that sustain the structure of the solar system in an endless rhythm. But everything we are learning now suggests that this is far from the whole story. Mercury, like all 4 of the rocky siblings, was formed of molten rock. A few million years later, as the young planet began to cool, its crust solidified, and its journey around the Sun transformed from being part of a swirling cloud into a clearly defined passage, an orbit. The path the infant Mercury travelled, however, was most probably far removed from the course it now holds. The young Mercury was born not as the closest planet to the Sun, but at a much greater distance, far beyond the orbit of Venus, beyond Earth, perhaps even beyond Mars. This was a planet that came into being in the mildest region of the solar system. It was far enough away from the Sun to allow volatile elements like sulfur, potassium, and phosphorus to be folded into its first rocks without being vaporized away by the heat of the Sun, but maybe near enough for its surface to be warmed, perhaps even just the right amount for liquid water to settle on its surface. This may well have been a planet big enough to hold an atmosphere, a watery world upon which all the ingredients of life could well have existed. Mercury, it seems, really did have its own moment in the Sun, but these hopeful beginnings were not to last. Today, it's hard to imagine the planets in any orbit other than our night sky. They feel eternal, permanent, and so it's natural to think of the solar system as a piece of celestial clockwork, a mechanism running with perpetual and unchanging precision, marking out the passage of time. In time frames that we can comprehend, days, weeks, months, and years, the motion and trajectory of the planets is just that, clockwork. We use these markers to plot out the 24 hours of a day, 365 days of a year, and the lunar cycle is, of course, intimately linked to our months. Beyond that, Newton's laws of universal gravitation, first described in 1687, allow us to this day to plot out the trajectories of all the heavenly bodies far into the future and back into the distant past. This predictability of motion is what allows us to plot great astronomical events, such as eclipses and transits, far into the future. It's why, for example, we can predict that on the 14th of September 2099, the Sun, Moon, and Earth will be in precise alignment to create the final total solar eclipse of the 21st century across North America. But 100 years ahead or behind us is nothing more than a proverbial blink in terms of the life of the solar system, and over longer durations the clockwork becomes a lot less reliable. If there was only one planet orbiting one star, for example, if Mercury was the orphan child of the solar system, we would be able to calculate precisely the gravitational force between Mercury and the Sun, and to plot Mercury's orbit around the Sun with essentially infinite precision. But add one more planet into our rather vacant imaginary solar system, let's say we make it Jupiter, so there is now a gravitational force between all three objects, the Sun, Mercury, and Jupiter, and it's no longer possible to calculate exactly where they're all going to be in the future, or where they were at some point in the past. When there are more than two objects in play at any one time, you have what physicists call a chaotic system. It means the planets can push and pull one another, moving entire orbits in ways we simply cannot predict. So the further we look back in time, the less certain we are of the position of any of the planets. Our mathematics fails, so instead we have to rely on circumstantial evidence to piece together a picture of the past. In the case of Mercury, it's the evidence from MESSENGER detailing the levels of volatile elements like potassium and sulfur that enable us to begin to understand the early life of the planet and infer that Mercury must have begun life further out in the solar system than it finds itself today. So what happened next? How did a planet that began its life in the sweet spot of the solar system end up in the scorched interior? The answer lies in the other clue MESSENGER confirmed for us, Mercury's massive iron core. Relative to its size, Mercury has the most massive core of any of the rocky planets. 75% of its diameter and almost half of its mass is molten iron, compared to around just a fifth of the mass of the Earth. We've suspected the oddity of Mercury's composition for well over 150 years, and that's because of some brilliant deduction by a German astronomer called Johann Franz Encke, who determined the mass of Mercury by measuring the gravitational effect it had on a passing comet, a comet that we now call, unsurprisingly, Comet Encke. With an approximation of the planet's mass, we are able to calculate the density of the planet, and with that calculation, approximate its composition. So we've known for some time that Mercury is odd, but only with the arrival of MESSENGER did we begin to reveal just how odd the smallest planet actually is. By accurately measuring Mercury's magnetic field, we've been able to confirm that far from being a geologically dead planet, Mercury has a dynamic magnetic field driven by an internal force, indicating that the core is at least partially liquid. This goes against the conventional thinking of planetary dynamics, because we would expect a planet as small as Mercury to have lost its internal heat long ago. Just as Mars lost its heat because of its size, we would have expected the core of Mercury to have cooled and solidified. But MESSENGER's data proved otherwise. By combining precise measurements of Mercury's gravity field with the extraordinary mapping of its surface, MESSENGER found that Mercury's structure is unique in the solar system. It appears to have a solid silicate crust and mantle above a solid layer of iron sulfide, which surrounds a deeper liquid core layer, possibly with a solid inner core at the center of the planet. This challenges all the theories about its formation. 4.5 billion years ago, we know that the inner solar system was in turmoil. In the middle of it all, the newly born Mercury found itself orbiting far out from today's intimate proximity with the Sun, surrounded by rocky debris and scores of planetary embryos all jockeying for position. The young solar system was still a place where planets could live or die. But it wasn't just the rocky planets that found themselves disturbed. Jupiter, the largest and oldest of all the planets, was on the move. And when a planet of that size shifts its position, there are almost always casualties. We'll come back to the story of Jupiter's grand tack and the havoc it spread throughout the solar system in Chapter 3. But for now, all we need to know is that the evidence suggests that the juvenile Mercury was kicked by the gravitational force of Jupiter on an inward trajectory, finding itself flung in towards the Sun and into the path of danger. In the crowded orbits of the early solar system, such a change of course was fraught with danger, and all of the evidence indicated that this was the most violent and defining of turns in Mercury's history. As the planet swerved inwards, it collided with another embryonic world and shattered. Today we see the evidence of this ferocious collision in the strange structure of this tiny planet. A giant core has been left behind, the exposed interior of a planet that had much of its outer layer, its crust mantle, stripped away and lost to space in the aftermath of the collision. This collision not only transformed the physical characteristics of the planet, but also knocked Mercury further inwards on a lopsided trajectory that we see reflected in the most elliptical orbit of all the planets. Although we cannot be certain of these events, it's a brilliant piece of scientific deduction to use the evidence we have to create a plausible scenario of events that happened unimaginably long ago. Events that drove the first rock from the Sun from a position full of potential to a place much too close to the Sun to support any form of life. An opportunity lost. After 4 years of observation and its brilliant discovery of Mercury's ancient past, Messenger finally ran out of fuel on the 30th of April 2015 and added yet another crater to this tortured world that once held such promise. Shrouded in an unbroken blanket of cloud, the next rock from the Sun tells a very different story. Over 50 million kilometers beyond Mercury lies a world that at first sight has the potential to be far more Earth-like than her scorched inner companion. Venus is perhaps the most mysterious of all the planets. Lying on the inner edge of the so-called habitable zone, this is a planet that holds its secrets close. For centuries, it has teased us with its brightness in the early morning and early evening sky. It's so bright because it's a large planet about the same size as the Earth. It's not too far away from us either, and the clouds that shroud it are highly reflective, reflecting 3/4 of the light that hits them. That's the frustrating but tantalizing thing about Venus, because even when you look at it through a big telescope, it is featureless. You never see the surface, which means that until the 1950s, scientists could only speculate about what lay beneath. In the late 19th and early 20th centuries, many thought that beneath her clouds Venus was hiding a mirror world to Earth. If not home to complex sentient life, then certainly hosting basic life forms. Faced with that impenetrable cloak, our collective imaginations fueled the idea of a living, breathing world beneath the clouds, a shroud that meant for the first half of the 20th century we lived convinced that we were far from alone in the solar system. Nobel Prize-winning chemist Svante Arrhenius was one of the most renowned scientists to fuel the mythology of what lurked behind Venus's cover. Like many of the scientists of his era, Arrhenius let his curiosity wander into many different realms, including astronomy, and he hypothesized at length about the Venusian environment. Assuming the clouds of Venus were composed of water, he wrote in his book The Destinies of the Stars that a very great part of the surface of Venus is no doubt covered with swamps, creating an environment not unlike the tropical rainforests found here on Earth. Expanding on this picture, he suggested that the complete cloud cover of the planet created a uniformity totally unlike the extremes of weather that define different parts of the Earth. In Arrhenius's imagination, this stable environment, with a consistently uniform climate all over the planet, meant that any life on Venus lived without the evolutionary pressures of changing environments that drive natural selection here on Earth, leaving Venus in an evolutionary limbo akin to the Carboniferous period. Describing a world full of prehistoric swamps and dark forests, Arrhenius created the perfect canvas for science fiction writers of the time to conjure up a menagerie of curious life forms lurking beneath the clouds. Today, Arrhenius is far less known for his fertile imaginings on the wildlife of Venus than he is for his work on the climate of Earth. In 1896, he was the first scientist to use basic principles of chemistry to demonstrate the impact that the atmosphere can have, in particular levels of carbon dioxide, on the surface temperature, a process that was called the Arrhenius effect, but is now known as the greenhouse effect. an effect that would not only have profound consequences for our understanding of our impact on our own planet, but would also be vital in explaining the true nature of Venus beneath the clouds. By the 1920s, as ground-based technology improved, we stopped painting the surface of Venus with our imaginations and started filling in the gaps with facts. The first spectroscopic analysis of the planet's atmosphere suggested that it wasn't water or oxygen that filled the clouds of Venus, so some thought this hinted at an arid desert land beneath. Others speculated that formaldehyde filled the air, leading to the belief that Venus was not only a dead planet but a pickled one too. But come the 1950s, the true nature of Venus began to be revealed, as more accurate Earth-based observations suggested the presence of overwhelming levels of one defining gas in the Venusian atmosphere. This was not a planet shrouded in clouds of water and oxygen, nor pickled in formaldehyde. This was a planet engulfed in a blanket of carbon dioxide, and as Aryan Use had demonstrated on Earth, this almost certainly meant that whatever lay beneath the clouds, the heat would be beyond the limits of even the most resilient life forms on Earth. As the first spacecraft were being built to explore our sister world, it was becoming increasingly clear that visiting Venus would be far from easy, and she would be far from welcoming. In the early 1960s, the Soviet Union began a series of missions under the program name Venera, which attempted to explore the atmosphere and surface of Venus directly for the first time. The initial launches of the Venera program failed before they had even left Earth's orbit, but within a couple of years the program began to slowly see some success. Venera 1 was successfully launched on the 12th of February 1961. Designed as a flyby mission, it is thought to have passed within 100,000 kilometers of Venus, but a total telemetry failure on the craft meant that no data was returned to Earth. As far as we know, Venera 1 is still in orbit around the Sun to this day. Venera 3 attempted to go a step further, and was designed to enter the Venusian atmosphere to take the first direct measurements. However, on crossing the atmospheric boundary, the probe's systems failed, and no data was returned as it plummeted towards the ground. All that was left for Venera 3 was the historic position as the first human-built object to crash into another planet's surface. Despite multiple failures, the Soviets didn't give up, and in October 1967, Venera 4 entered the atmosphere of Venus and sent back data supporting the Earth-based observations, revealing for the first time that the blanket of clouds surrounding Venus was made up of primarily carbon dioxide, 90 to 95%, 3% nitrogen, and just trace amounts of oxygen and water vapor. Venera 4 confirmed beyond all doubt that this was no second Earth. As it descended through the thick clouds, the temperature rose to 262 degrees Celsius. The atmospheric pressure increased to 22 standard atmospheres, 2,200 kPa, and this was still 26 kilometers above the surface. As Venera 4 parachuted its way down to the surface, it provided data to Earth while confirming its own imminent death. This was a spacecraft that was not designed to survive the intense pressures and temperatures it was measuring, let alone the lack of the water landing it was designed for. The craft failed during the descent, and was lost long before it reached the surface. Gradually, through the following missions, the Soviet scientists began to overcome each and every challenge Venus put in front of them. Venera 7 was built to survive the most violent of landings, and even though its parachute failed, it made it to the surface intact in 1970, and was able to use its damaged antennae to transmit limited temperature data for 23 minutes before it expired. Venera 9 not only made it to the surface and operated for 53 minutes in October 1975, but was also the first craft to successfully deploy its camera on the ground and transmit an image back to Earth. In the first ever picture taken from the surface of another planet, the black and white fractured image revealed a rocky, desolate landscape, with measurements confirming it to be a blistering 485 degrees Celsius, with an atmospheric pressure of 90 atm crashing down. By the time Venera 13 launched on the 30th of October 1981, the ambition of the missions and the confidence in delivering data from the surface had been radically transformed. Venera 13 functioned for 127 minutes, in recorded temperatures of 457 degrees Celsius and a pressure of 89 Earth atmospheres. The probe's cameras deployed, taking the first color image from the surface of Venus. Spring-loaded arms measured the compressibility of the soil, while a mechanical drill arm took a sample of the Venusian surface that was analyzed by an onboard spectrometer. If that wasn't enough, onboard microphones were deployed to record the vicious winds that were assumed to be whipping the surface of Venus, the first ever recording of the sound of another planet. As the Venera missions came to a close in 1983, not even the smallest doubt remained of Venus's hostility. Far from the benign water world we had once imagined, the reality was that this was not a sister we recognized. In our search of the heavens for a place like home, we'd found a toxic, fiery hellscape. Venus is an enigmatic world, almost Earth-like in size, position, and potential, and yet as far from paradise as it's possible to imagine. If Mercury's story is one of catastrophic orbital change, and Earth's of balance and stability, the story of Venus is a tragedy, a tale of subtle yet relentless decline. So why did it all go wrong for Venus? Why did a world born with such similarities to the Earth take such a different path? To answer that, we need to look beyond the tortured planet we see today and go back to a time when Venus was a young, thriving planet. 4 billion years ago, Venus was a familiar world, a world created from the same dust as the Earth, born just about the same size, and settled into an orbit that seemed just far enough away from the glare of the sun to allow a precious process to begin to take hold. In almost every conceivable way, Venus's early life mirrored that of our own world. As its newly formed crust settled and cooled from the violent heat of its birth, an atmosphere began to grow around the young planet, fed by gases bubbling up from the molten rock below its surface, as well as captured from the clouds of gas and dust it swept through on its orbit around the sun. Clinging to the young Venus, this thin layer of gas would have certainly contained nitrogen, oxygen, and carbon dioxide. But most intriguing of all, we are certain it would have also contained large amounts of water vapor. High in the Venusian atmosphere, this water vapor eventually cooled enough to change state from vapor to liquid. And with that transformation, a process began that perhaps for the first time on any of the planets would have seen the conditions become just right for droplets of liquid water to take shape and begin falling from the Venusian sky. These were the first rains of the solar system, showering down onto the dry plains of Venus. Gradually these rains would have not just fallen but flooded the surface. Rivers would have flowed, and shallow oceans taken hold of large swathes of the planet's surface. Venus, perhaps before even the Earth, became a water world, a planet with skies full of clouds and a surface full of oceans, feeding the cycle of water around this young planet. How can we be certain this blue version of Venus existed? Unlike Mars, where we can see the evidence of its watery past etched onto its surface, we have no such direct evidence of the presence of liquid water on the surface of Venus. The only physical evidence we have that suggests the planet's watery past comes from measurements taken by NASA's Pioneer Venus spacecraft back in 1978. One of its most surprising discoveries revealed an unexpected amount of deuterium, heavy water, in the atmosphere compared with hydrogen. This DH ratio is far smaller on Venus than it is on Earth, and that's interesting because when the two planets formed, the ratio would have almost certainly been the same. Because hydrogen is far more easily lost from an atmosphere than deuterium, this smaller ratio suggests that Venus has lost a lot more water than the Earth over its lifetime, the signature of a long-lost primordial ocean. As cosmochemist Larry Nittler explains, scientists believe that Venus once had a lot of water in its oceans, but lost it over time, and perhaps in oceans as recently as 1 billion years ago. The reason we can tell this is from the isotopic composition of hydrogen measured in its atmosphere by spacecraft. Now, hydrogen has 2 flavors of isotopes. Whereas most hydrogen atoms are just a single proton in the nucleus, some, a small fraction, are what we call deuterium, that have a proton and a neutron, so they weigh twice as much as the regular hydrogen. What happens when you have evaporation of water from a planet, or the atmosphere, is that the water molecules that contain hydrogen are much lighter than the water molecules that contain deuterium, so they evaporate more easily and can be lost more easily. So over time, as you evaporate water, deuterium-bearing molecules stay behind relatively to the regular ones, and you build up a deuterium-to-hydrogen ratio. And by back-calculating from the measured ratio today, we can figure out how much water has been lost over the billions of years of evolution, and on Venus, it's quite a lot. None of this is solid proof, but it does begin to point us in one direction. And with no further exploration of the surface, we've had to rely on an accumulation of indirect evidence to begin to paint a more detailed picture of Venus's watery past. As with almost all of our understanding of the planets, the evidence that built this picture has been accumulated through decades of exploration. Starting with the Venera mission's first touchdown on the planet, to the Pioneer Venus orbiter, and to the more recent Magellan mission, which not only relayed extraordinary radar soundings of the surface of Venus, but provided the first full topographical map of the planet collated over a period of 4 years in orbit. Combining all of the data that has been accumulated over decades of exploration has allowed us to peer deep into the planet's past, using the same tools that enable us to model the future of climate change here on Earth, to create climate models of Venus in the past, present, and future. The results of this analysis, conducted most recently by a team from NASA's Goddard Institute for Space Studies, GISS, all point to the same conclusion. In the distant past, Venus was a planet covered in shallow, primordial oceans. Some estimates suggest that this water world was far from fleeting, a blue planet just like our own that could have been sustained for around 2 billion years, and perhaps only disappeared some 700 million years ago. It's a tantalizing thought that such a similar world to our own existed for so long with liquid water on its surface. We know life took hold quickly on our own blue planet, within 500 million years of the Earth being formed. So there seems good reason to suspect that if Venus really was as wet as the models predict, it too could have sprung into life. Exactly what went on in the long-lost rivers and oceans of Venus is yet to be discovered. Hidden behind the clouds, we have not yet been back to search for any signs that life ever took hold here. Our exploratory attentions have turned to Mars as a planet that not only has a fertile past, but is also a possible target for human colonization in the future. We know for certain that no life, at least no life we understand, could exist on Venus today, and perhaps even the evidence of any biology on that long-lost water world has long ago vanished under the oppressive heat, rampant volcanism, and extreme pressures of the planet today.
The history of science is littered with crunching moments of conflict, debates, and disagreements that divided opinion in the most passionate of battles. The wonderful thing about science, however, is that the debates can be settled when facts become available. Science and conservative common sense famously clashed in 1860 when Thomas Huxley and Samuel Wilberforce fulminated over the new theory of evolution published by Darwin 7 months earlier. I imagine Wilberforce's indignant, reddening cheeks shaking with righteous outrage as he denied the repugnant possibility that his grandfather was a monkey. None of his relatives was a chimpanzee, by the way. We simply share a common ancestor with them around 6 or 7 million years ago. But the unctuous, oleaginous, and saponaceous bishop, as Disraeli once called him, was having none of it. This might be a little unfair to the great Victorian orator and Bishop of the Church of England, But in the case of evolution, he was firmly on the wrong side of reality. Few great leaps in knowledge occur without dividing opinion, and this is entirely appropriate. Extraordinary claims require extraordinary evidence, and the great scientific discoveries we are celebrating here are utterly extraordinary. The trick, as an educated citizen of the 21st century, is to realize that nature is far stranger and more wonderful than human imagination, and the only appropriate response to new discoveries is to enjoy one's inevitable discomfort, take delight in being shown to be wrong, and learn something as a result. The world of astronomy had its moment of intellectual sumo in what has become known as the Great Debate. The year was 1920, and two eminent astronomers found themselves stuck on a train together, traveling the 4,000 kilometers from California to Washington to discuss the greatest cosmological question of the day. The younger of the two men, Harlow Shapley, we have already met. He had just published his data suggesting that the Milky Way galaxy was much larger than previously suspected. This, however, was where he believed the universe stopped. Shapley was convinced our galaxy was the beginning and end of the cosmos. His travelling companion thought otherwise. Heber Curtis had been studying a misty patch of light known as the Andromeda Nebula. He was convinced that this was not part of our galaxy, but a separate island universe of billions of other stars. It's not known what they discussed on the train, but the debate itself took place at the Smithsonian Museum of Natural History throughout the day and night of the 26th of April. At stake was the scale of the universe itself, and both men knew that the question would ultimately be settled by evidence rather than debating skills. The human race had already been shunted from the centre of the universe by Copernicus, and now faced the possibility that the Milky Way galaxy itself was part of a multitude, stretching across millions of light-years of space. The question wasn't settled that evening, but the experienced Curtis, perceived as the underdog because of the magnitude of what he was suggesting, landed significant blows. Curtis observed that the Andromeda Nebula contains a number of novae, exploding stars that shine temporarily but brightly in the night sky. But he also noted that the novae in Andromeda appeared on average to be 10 times fainter than any others. Curtis asserted that Andromeda's novae appear dimmer simply because they are perhaps 500,000 light-years further away than those in the Milky Way. Andromeda is therefore another galaxy, claimed Curtis, which strongly implied that the other so-called nebulae were other galaxies too. This was the very definition of an extraordinary claim, and the extraordinary evidence came only 4 years later. In 1923, a photo of Andromeda, taken by a 33-year-old astronomer called Edwin Hubble, further fueled the Great Debate. It's only a photograph, but just like Anders' Earthrise, it belongs to a rarefied group of images that have transformed our perspective. Aside from their scientific merit, such images assume great cultural significance because of the ideas they generate and the philosophical and ideological challenges they pose. They also carry with them, in the shadows, personal stories. Someone would have taken a photograph of Andromeda someday and discovered what Hubble did. But Hubble took this one, and his story therefore becomes inextricably intertwined with it. Some don't like their history presented in this way, but science is richer when its stories include people as well as ideas. Curiosity is, after all, a human virtue. Hubble may never have taken the photograph had he followed through on a promise to his father to practice law. Reading jurisprudence at Queen's College, Oxford, as one of the first Rhodes Scholars, Hubble aimed to fulfill his father's wishes, but John Hubble died before Edwin finished his degree. The death of his father encouraged Edwin to ditch law and revisit his childhood passion for astronomy. He left Oxford for the University of Chicago, joined the Yerkes Observatory, and received his PhD in 1917 with a thesis entitled Photographic Investigations of Faint Nebulae. After brief service in the US Army at the end of World War I, Hubble obtained a position at the Mount Wilson Observatory. He found himself at the controls of the largest, most powerful telescope on the planet, and with the knowledge and good sense to point it at the most intriguing and controversial object in the night sky, Andromeda. Just like Curtis before him, Hubble could make out distinct features within the misty patch,
but the newly commissioned 100-inch Hooker telescope allowed him to see much more detail. On the 5th of October 1923, he took a 45-minute exposure, found 3 unidentified specks that he assumed were new novae, and marked them all with an N. To confirm his findings, Hubble needed to compare this plate with previous images of Andromeda taken at Mount Wilson. The following day, he made the journey down to the basement archive where the observatory's collection of images was catalogued and stored. To Hubble's delight, 2 of the specks were indeed newly discovered novae, what we now know to be the bright nuclear flares of white dwarf stars as they accrete gas and dust from a nearby companion. But it was the 3rd speck that he found most interesting when he compared it to previous images. As Hubble scanned back through the Mount Wilson catalogue, he discovered that the star had been captured before. In some plates it appeared brighter, whereas in others it appeared dim or not present at all. Hubble immediately grasped the importance of his discovery. The 3rd speck was a Cepheid variable, the type of star Henrietta Leavitt had studied 2 decades earlier. In one of the most famous corrections in scientific history, Hubble crossed out the letter N and replaced it in red ink with the letters VAR, followed by a very understated exclamation mark. Hubble had discovered a cosmic yardstick in Andromeda, and it was a trivial matter to calculate the distance. The new star varied with a period of 31.415 days, which, following Leavitt, implied its intrinsic brightness was 7,000 times that of our Sun. And yet it appeared so dim in the night sky that it was invisible to all but the most powerful of telescopes. Hubble's initial calculations revealed that the star was over 900,000 light-years away from Earth, a staggering distance when the size of our own galaxy was estimated to be no more than 100,000 light-years across. Hubble, with the help of Leavitt's ruler, laid the great debate to rest. Andromeda, the distant patch of light in the night sky, is a galaxy, an island, according to current estimates, of 1 trillion suns. Current measurements put the giant spiral at a distance of 2.5 million light-years from the Milky Way, one of around 54 galaxies gravitationally bound together to form our galactic neighborhood known as the local group.
In the daytime, our universe stretches only as far as the horizon. The sun hides in plain sight because it's too bright for us to see it directly. Only rarely do we glimpse a watercolor moon. Unless we think hard, our intellects are confined to the surface of the Earth. After sunset, beyond cities, the universe appears, a destination for the imagination, albeit separated by a seemingly unbridgeable gulf. This may be true for the stars, but it is not so for the planets. There are times when Mars, Venus, Jupiter, and Saturn dominate the sky, bright lights that shift position nightly against the fixed stars, commanding our attention even if we aren't certain what we're looking at. The distances are still vast by terrestrial standards, but despite appearances, the gulf is certainly not unbridgeable, because we have visited all of these planets and taken our first steps into the outer reaches of the solar system beyond. And yet the wandering lights in the dark still feel detached from human affairs, and the time and effort we've spent in visiting them might seem to be an indulgence. This assumption, however, is profoundly wrong. The solar system is a system. The Sun and the 8 major planets and countless billions of minor planets, moons, asteroids, comets, and unclassified lumps of ice and rock were formed back in the mists of time, and they continue to evolve as one. We rarely notice the dynamic, interconnected nature of our system, although asteroid strikes on our planet are not such a rare occurrence. The Chelyabinsk impact in February 2013 injured 1,500 people when a 12,000-ton asteroid broke up as it entered the Earth's atmosphere at 60 times the speed of sound. And the Tunguska airburst in Siberia in 1908 flattened 800 square miles of forest in an explosion comparable to that of the most powerful hydrogen bomb ever tested. The surface of the Moon bears testament to a record of violence and destruction from the skies that the Earth has also endured. But the relentless erasure of craters by weathering, and our good fortune that no major impacts have occurred in recorded human history, are the reason for our misplaced sense of isolation from the heavens. The interdependent nature of the solar system has become more evident as we've begun to understand its history. It's tempting to imagine that the physical layout of the planets is a fossilized remnant of primordial patterns in the collapsing dust cloud around the newly ignited Sun 4.6 billion years ago. But our exploration of the planets, coupled with increasingly powerful computer simulations of the evolution of the solar system, has revealed that this is not the case. Planetary orbits are prone to instability, particularly so in the early, more chaotic years when our solar system was young. The details of precisely how the planetary orbits have shifted are still uncertain, but we now suspect that Mercury, the innermost planet, began life much further out and was deflected inwards to its present-day seared orbit. Jupiter and Saturn may have drifted inwards shortly after their formation, before reversing their course and retreating, but not before affecting the distribution of material out of which Mars and Earth would later form. Around the time that life began on Earth, Neptune and Uranus may have been flung outwards, disrupting the orbits of billions of smaller objects far from the Sun. The record of this time of unprecedented violence, known as the Late Heavy Bombardment, is written across the scarred surface of the Moon, itself most likely formed in a glancing interplanetary collision between Earth and a Mars-sized planet 4.5 billion years ago. The planets are like snowflakes. The detail of their structure, their composition, size, spin, and climate are a frozen record of their past. An understanding of the planets beyond Earth is therefore a prerequisite for understanding our home world, and that, in turn, is a prerequisite for understanding ourselves. Earth is unique in the solar system because it's a planet with a complex ecosystem. The genesis and subsequent 4 billion year evolution of life on Earth required planetary characteristics which are necessarily linked to the evolution of the system as a whole. There had to be liquid water on the surface, and much of this water was delivered after the Earth's formation by icy, water-rich asteroids and comets, possibly deflected inwards from the outer solar system by Jupiter. These rivers, seas, and lakes of extraterrestrial origin had to persist for the best part of 4 billion years, which required a stable atmosphere to maintain surface temperatures and pressures within a limited range. 4 billion years is a long time, around a third of the age of the universe. The Sun has brightened by 25% since the Earth formed, which makes the stability of our environment all the more difficult to understand. In a chaotic system of planets around an evolving star, a planet with life-supporting properties and the remarkable stability enjoyed by Earth over billions of years may be extremely unusual. The study of our sister worlds, Mars and Venus, has proved instructive in understanding just how fortunate we may have been and how delicate our position today might be. 4 billion years ago, as life began on Earth, Mars was also Earth-like. It had oceans and rivers, an active geology and complex surface chemistry, the ingredients of life. One of the primary goals of the fleet of spacecraft currently in orbit around and exploring the surface of Mars is to search for evidence of past or even present life, and to understand why the red planet was transformed from a potential Eden at the dawn of the solar system to the frigid desert world we observe today. The story is complex, but one of the most important differences between the two worlds is size. Mars is just 1/10 the mass of Earth, too small to hang on to its internal heat, its protective magnetic field, and its atmosphere for much more than 1 billion years after its formation. Yet Mars formed in a similar region of the solar system to Earth and Venus, so why is it so small? The answer may lie in the fast-changing orbits of Jupiter and Saturn early in the solar system's history. These surprising findings will be explored later in this book. The history of Venus is perhaps even more puzzling, in part because of the immense difficulty of exploring the planet. Venus is often described as a vision of hell. Surface temperatures are high enough to melt lead, and the atmospheric pressure is 90 times that on Earth. Sulfuric acid raindrops fall from its clouds. And yet, long ago, Venus too may have been Earth-like. Perhaps there were once Venusians, before a runaway greenhouse effect took hold, and began destroying Venus's temperate climate about 2.5 billion years ago, although this date is highly uncertain. Taken together, the stories of the three large terrestrial planets are salutary. If an alien astronomer observed our solar system from afar, they would classify Mars, Earth, and Venus as potentially living worlds, orbiting as they do inside the so-called habitable zone around the Sun, the region within which, if atmospheric conditions are right, liquid water can exist on the surface of the planets. All three worlds may once have been habitable, and all three worlds may once have harbored life, but now only Earth supports a complex ecosystem, let alone a civilization. Understanding why Mars and Venus diverged so significantly from Earth over the last 4 billion years will provide great insight into the fragility of worlds, and perhaps suggest whether our own good fortune is near impossible to comprehend or merely outrageous. Planets change. Ours could change at any moment. A stray comet from the frozen Kuiper belt beyond the orbit of Neptune could put an end to our story. We could also put an end to ourselves. The study of Venus might help us avoid one of the ways by which we can destroy ourselves, because it shows us what greenhouse gases are to avoid. I think one of the reasons why anthropogenic climate change is so difficult to observe is that the atmosphere is theory and capable of trapping enough heat to modify the temperature. Those people might suggest where they can squash and boil and dissolve on the surface of the planet. The explanation of the process is important. If we want to know how we came to be, we need to understand the histories of the planet. Should be our primary concern. That may be so, but I argue that a deeper understanding of the evolution of the planets is essential for our continued prosperity and existence on this one. The threat of catastrophic climate change is an obvious example, but there are many other reasons why knowledge is important. There is feedback in human affairs. Our collective state of mind affects the decisions we make. To confine our imaginations to the surface of the earth is to ignore both our immense good fortune and the fragility of our position. A wider knowledge of both will, I believe, help secure a safer and more prosperous future.
Earth sits a mere 150 million kilometers from the Sun. Not too hot, not too cold. With surface temperatures ranging from -88 to +58 degrees Celsius. This Goldilocks location has created a stability of climate that, despite the best efforts of ice ages and impacts, has allowed life to maintain an unbroken chain for nearly 4 billion years. And yet we know for certain that it cannot last. Our Sun, like every star in the universe, is far from static. Stars have life cycles of their own, and eventually the hydrogen fuel that powers the nuclear reactions within a star will begin to run out, and the star will enter the final phases of its lifetime. It will expand, cool, and change color to become a red giant. Small stars like our Sun,
will undergo a relatively peaceful and beautiful death, which will see it pass through a planetary nebula phase to become a white dwarf, which will cool down over time to leave a brown dwarf. Life on Earth has prospered through our Sun's middle years, but these optimum conditions are waning. At first the changes will be invisible, but 1 billion years from now they will be obvious to any life forms left on the planet. An immense sun filling the sky will warm and transform itself and the Earth that it shines upon. The sun is both the giver and the taker of life on our planet. It is one of the great paradoxes of the universe that as the life of a star like ours begins to wane, its size and luminosity will increase. A rise in luminosity of just 10% will see the average surface temperature on Earth rise to 47 degrees Celsius instead of the 15 degrees Celsius that it is today. The effect of this rise in temperature manifests in a lifting of vast amounts of water vapor from the oceans into the atmosphere, creating a greenhouse effect that could quickly and rapidly run out of control, evaporating the oceans and sending the surface temperature skyrocketing. Astrobiologist David Grinspoon explains. The greenhouse effect is the name we give to the physical process by which planets heat up through the interaction of their atmospheres and solar radiation. Basically, solar radiation comes in what we call the visible wavelengths. Primarily, they're wavelengths that we can see, and most atmospheric gases are very transparent to visible radiation. So light from the sun comes through pretty much unimpeded by an atmosphere and reaches the surface of a planet. Then the surface of the planet re-radiates that radiation in infrared, because planets are much cooler than the sun. And that means they radiate at much longer wavelengths, what we call infrared or heat radiation. That infrared radiation doesn't make it through an atmosphere so easily. Some of the atmospheric gases, the ones we call greenhouse gases, block infrared radiation, and so therefore the more of those greenhouse gases that are in a planet's atmosphere, the harder it is for that surface radiation to make it back out into space, and the more that planet will heat up. Estimates of the timescale that will see our oceans disappear vary massively, and are heavily influenced by a multitude of factors. But few are in doubt that by the time our planet reaches its 8 billionth birthday, in 3.5 billion years' time, the end will be in sight. With temperatures heading above 1,000 degrees, life will have long disappeared from a surface that is beginning to melt under the burning sun. Moving even further into the future, the outlook becomes bleaker. As the sun enters old age, it will grow into a red giant, engulfing the Earth within its expanding atmosphere. Moonless, lifeless, and perhaps reduced to its inner core, our planet and the civilizations it once harbored will be nothing but a distant memory, etched in the atoms that made us all, as they are dispersed amongst the cosmos. For planet Earth, the clock is ticking, and time is slowly running out. But ours is far from the only world to enjoy its moment in the sun. Across the history of our solar system, stretching deep into its ancient past and reaching far into its future, we see stories of worlds in a constant battle with our ever-changing star. Close in, ancient worlds such as Mercury, which long ago lost their fight with the sun, are taunted by views of Earth and what might have been. Further out and even hotter, Venus circles, shrouded in a choking cloak of cloud, and even further beyond the Earth, Mars sits cold and barren. Beyond these planets, frozen worlds await, huddled in perpetual hibernation, anticipating the moment when the warmth of the sun reaches out far enough, with sufficient heat, to trigger a first spring. On that day, mountains of ice will melt, rivers of water will flow, and where there was once only bleakness, in the distant future on planets once frozen and lifeless, we might find a place that looks very much like home. The story of our solar system is not as we once thought it, eternal and unchanging. Instead, it is a place of endless transformation. It is a narrative that repeats itself with a predictable rhythm. As one world passes, another comes into the light. Only one planet has maintained stability for almost the entire life of the solar system. The Earth has remained habitable for at least 4 billion years, while change has played out all around it. What makes the Earth so lucky compared to all of its terrestrial siblings? To answer that question, we need to look not just at our planet, but at the whole of the solar system, going right back to the very beginning. For the first few million years after its birth, there were no terrestrial worlds to see the sun rise, and there were no days, no nights, no circular tracks around it. Instead, surrounding our infant star was a vast cloud of dust and gas. A tiny fraction of the material left over from the sun's formation. This swirling cloud would one day coalesce to form the various planets of the solar system, and many other smaller bodies. But at this time, 4.7 billion years ago, there was nothing but tiny specks of dust reflecting back the light of our slowly growing star. Only time, vast amounts of empty time, would allow enough of this gas and dust to catch and cluster, randomly forming the smallest of seeds. Most of these seeds would hardly get the chance to grow at all, smashed apart and returned to the immense swirl of dust from whence they arose. Just a few would grow big enough and survive long enough to capture and condense more of the cloud, slowly increasing their mass and density. We still do not fully understand the process by which grains of dust no thicker than a human hair can amass to become rocky objects the size of a car, and as yet no model exists to explain this part of the evolution of a planet. But what we do know is that once that disk of gas and dust becomes populated with clumps of rock that make it past the meter-sized barrier, a powerful force comes into play to propel the process forward. These newly formed planetesimals are big enough to allow the great sculpting force of gravity to draw the clumps together, growing to sizes of over 1 kilometer in length. Swirling around the sun, thousands upon thousands of these objects live and die, colliding and coalescing under the increasing gravitational forces of attraction, until eventually just a few emerge as planetary embryos, moon-sized bodies known as protoplanets. In the last violent stages of the process of planetary birth, these protoplanets swirl around in crowded orbits, and many are destroyed, returned to the dust of their origins. But occasionally, when a collision brings 2 or more of these giant objects together, the size of this mass of rock becomes big enough for gravity to pull it in from all sides, creating a sphere of newly formed rock, a new world. In that moment, a planet is born. Each of the terrestrial planets in our solar system was born this way. They are the survivors of a process that destroys far more worlds than it ever creates, and which left just 4 rocky planets remaining, starting closest to the Sun with Mercury, then Venus, Earth, and finally, farthest out, the cold and dead world of Mars. Today, these 4 worlds all look vastly different, and yet all were created the same way, made up of the same ingredients and orbiting the same star. So why have they ended up so distinct from each other, and with such starkly different environments? And what makes this place, the Earth, so unique, the only one of the rocks that has blossomed with life? To understand, we have to look deep into the past of our solar system, to explore the unique history of each of the planets by means of amazing feats of human engineering across billions of miles, and into environments of unknown and unimaginable extremes. Getting to the smallest planet in the solar system is anything but easy. Skirting past the Sun at a distance of just 46 million kilometers at the closest point in its orbit, Mercury is a planet that is not only held deep in the gravitational grip of our massive star, but is also moving at an average orbital speed of 48 kilometers per second, by far the fastest orbiting planet in the solar system, and far outpacing the Earth's more leisurely 30 kilometers per second. It needs to whip around this quickly, otherwise it would have fallen into the Sun's embrace long ago. But the combination of its speed and position make it a planet that's immensely difficult to get close to, and even harder to get into orbit around. In order to do so, you have to travel fast enough to catch up with Mercury, but not so fast that you cannot somehow slow down to prevent a headlong descent into the Sun. And that challenge has meant that until relatively recently, it was the least explored of all the terrestrial planets. For many decades, our first and only close-up glimpse of the innermost rock orbiting the Sun came from the Mariner 10 spacecraft, when on 3 separate occasions in 1974 and 1975, it briefly flew past Mercury. This was the first spacecraft to use another planet to slingshot itself into a different flight path, using a flyby of Venus to bend its trajectory, to allow it to enter an orbit that would bring it near enough to Mercury to photograph it close up. Clad in protection to ensure it could survive the intense solar radiation and immense extremes of temperature, Mariner 10 was able to send back the first detailed images of Mercury as it flew past at just over 200 miles above its surface. It passed by the same sunlit side of Mercury each time, so it was only able to map 40 to 45% of Mercury's surface. The spacecraft took over 2,800 photos, which gave us never-before-seen views of the planet's cratered moon-like surface, a surface that we had never previously been able to fully resolve through Earth-based observation. Despite the beauty of the pictures taken, it wasn't the images from Mariner 10 that really surprised us. It was the data the probe collected relating to Mercury's geology, which pointed to a much more surprising history of the planet than had previously been imagined. Mercury, it seemed, was far from being just a scorched husk. Mariner was able to sense the remains of an atmosphere consisting primarily of helium, as well as a magnetic field and a large iron-rich core, opening a mystery that would remain unexplored for another 30 years. As it flew past Mercury for the last time on the 16th of March 1975, the transmitters were switched off and its contact with Earth silenced. Mission completed, Mariner 10 began a lonely orbit of the Sun that, as far as we know, continues to this day. At first sight, many things about Mercury simply don't make sense. During its 88-day orbit around the Sun, it travels in a lopsided elliptical orbit, which means it can be as far away from the Sun as 70 million kilometers, but occasionally as close as 46 million kilometers. This is by far the most irregular of orbits of all the planets, but it is not the end of Mercury's oddity. Temperatures at midday can rise to 430 degrees Celsius on the surface, but at night, because it's a small planet and it has no atmosphere, temperatures fall to minus 170 degrees, giving it the greatest temperature swing of any known body in the solar system. Its rotation is also unusual, gravitationally locked to the Sun in what is known as a 3-to-2 spin-orbital resonance. This means the planet spins precisely 3 times on its axis for every 2 orbits, which in turn means that its day is twice as long as its year. In effect, you could be travelling over its surface at walking pace and keep the Sun at the same point in the sky as you strolled through eternal twilight. As planetary scientist Nancy Chabot explains, a day on Mercury is not like a day on Earth. It has a very unusual orbit. It has to go around the Sun twice to have one complete solar day on the planet, where the Sun goes from directly overhead to directly overhead, and this actually takes 176 Earth days. Because of the planet's orbit, there are places on the Mercurian surface where a hypothetical observer would be able to see the 2.5 times larger in the sky Sun appear to rise and set twice during one Mercurian day. It rises, then arcs across the sky, stops, moves back towards the rising horizon, stops again, and finally restarts its journey towards the setting horizon. Most of Mercury's anomalies can be explained by the orbital mechanics of its journey around the Sun. except, that is, for the odd elliptical orbit that takes it on such an oval-shaped, elongated course. This irregularity has puzzled astronomers for centuries, and hints at an ancient planet that was very different from the Mercury we see today. To truly begin to understand Mercury's history, we had to wait nearly 40 years before we could return to her. On the 18th of March 2011, NASA's Messenger spacecraft became the first to enter Mercury's orbit. And over the next 4 years, it succeeded in not only photographing 100% of the planet's surface, but also collecting extensive data on its geology. But before any of this could happen, Messenger had to take perhaps the most circuitous route in the history of our exploration of the solar system. Just passing close to Mercury to take a few snaps, as Mariner 10 did, is hard enough. But actually entering into its orbit was thought to be either too difficult to achieve or too costly to execute, as cosmochemist on the Messenger mission Larry Nittler explained. There are two major challenges to getting a spacecraft into orbit around Mercury: gravity and money. When you go from Earth to Mercury, you're falling into the gravitational well of the Sun, which makes you accelerate faster and faster as you get closer. And if you were to go straight from Earth to Mercury, this means that you would basically just zip right by the planet, or you would need to bring an incredible amount of fuel to put the brakes on, more than you could actually afford. A number of missions never made it further than pencil and paper, while others floundered and failed at the proposal stage. It was only when Chen-Wan Yen, a NASA engineer from the Jet Propulsion Laboratory, JPL, provided a trajectory that could not only get a craft into orbit, but could do it at an estimated bargain bucket cost of $280 million, that the Messenger mission could really begin to take flight. Taking off from Cape Canaveral on the 3rd of August 2004, Messenger began a 6-year, 7-month, 16-day journey to Mercury that would take it on a 7.9 billion kilometer trajectory before it entered into orbit around the smallest of all the planets. To arrive at Mercury with the right speed and on the right course would require a complex route that would entail a number of gravity-assist maneuvers around the Earth, Venus, and Mercury itself to reduce the speed of the craft relative to Mercury. So, combined with the brief firing of its large rocket engine to finally insert it into orbit, this mission profile allowed Messenger to complete its voyage without the need to carry the vast reserves of fuel required to slow its passage through the firing of rockets. This design made the craft lighter and cheaper, but ultimately much slower. Almost 7 years was a long time to wait for the team patiently charting its progress across the stars. Larry Nittler described Messenger's course as sneaking up on Mercury by taking a 7-year journey, flying around the Sun many times, doing multiple flybys around Mercury and Venus, and each time transferring some of the craft's speed and energy to the planet, so it could slow down, so that when we finally got to Mercury after 7 years, we were able to fire our engine just a little bit to slow down even more and get captured by the weak gravitational field of the planet. Appropriately, when Messenger finally entered into Mercury's orbit at 0045 UTC on the 18th of March 2011, the path it settled into was highly elliptical. This orbit took it on a 12-hourly cycle from 200 kilometers above the planet's surface to 10,000 kilometers away from it. It may seem like an odd orbit for a craft with the singular aim of getting as close to Mercury as possible, but this was an essential part of the design of the mission, vital to protect Messenger from the fierce heat radiated by the scorching hot surface of Mercury. The sunlight reflected from the surface is so powerful, it would have literally melted the solder holding the spacecraft together if it wasn't given time to cool down between its closest approaches to the planet. Protected by an enormous ceramic solar shield and its eccentric orbit, Messenger could begin its work. For 2 years, the spacecraft mapped pretty much every bit of the surface of Mercury, and the images beamed back to Earth revealed a planet that's been in the firing line for billions of years.
too small to hold on to an atmosphere that might protect it from meteorites, and lacking any processes to recycle old terrain. Mercury's ancient surface is the most cratered place in the solar system. 1968 was a difficult year on planet Earth. The Vietnam War, the bloodiest of Cold War proxy tussles, was at its height, ultimately claiming over 3 million lives. Martin Luther King Jr. was assassinated in Memphis, prompting presidential hopeful Bobby Kennedy to ask the people of the United States to tame the savageness of man and make gentle the life of this world. Kennedy himself was assassinated before the year was out. Elsewhere, Russian tanks rolled into Prague, and France teetered on the edge of revolution. As I approached my first Christmas, my parents could have been forgiven for wondering what kind of world their son would inhabit in 1969. And then, as Christmas Eve drifted into Christmas morning, an unexpected snowfall decorated Oakbank Avenue, and Borman, Lovell and Anders, 400,000 kilometers away, saved 1968. Apollo 8 was, in the eyes of many, the moon mission that had the most profound historical impact. It was a terrific, noble risk, a magnificent roll of the dice, a distillation of all that is great about exploration, a tribute to the sheer balls of the astronauts and engineers who decided that, come what may, they would honor President Kennedy's pledge to send a giant rocket more than 300 feet tall, the length of this football field, made of new metal alloys, some of which have not been invented, capable of standing heat and stresses several times more than have ever been experienced, fitted together with a precision better than the finest watch, carrying all the equipment needed for propulsion, guidance, control, communications, food, and survival on an untried mission to an unknown celestial body, and then return it safely to Earth, re-entering the atmosphere at speeds of over 40,000 kilometers per hour, causing heat about half that of the temperature of the sun, almost as hot as it is here today, and do all this, and do it right, and do it first, before this decade is out.
If I heard that from a leader today, I'd be first on the rocket. Instead, I have to listen to vacuous diatribes about fairness, hard-working families, and how we're all in it together. Sod that, I want to go to Mars. To set Apollo 8 in context, Apollo 7, the first manned test flight of the Apollo program, was flown by Schirra, Isola and Cunningham in October 1968. Apollo 8 was supposed to be a December test flight for the lunar lander, conducted in the familiar surroundings of Earth orbit, but delivery delays meant that it was not ready for flight, and the aim of meeting Kennedy's deadline looked to be dead. But this wasn't the 21st century, it was the 1960s, and NASA was run by engineers. The program manager was George Low, an Army veteran and an aeronautical engineer who knew the spacecraft inside out and had the strength of character to make decisions. Why not send Apollo 8 directly to the moon without the lunar lander, proposed Low, allowing Apollo 9 to test fly the LEM, Lunar Excursion Module, in Earth orbit in early 1969 when it became available, and pave the way for a landing before the decade was out. Virtually every engineer at NASA is said to have agreed, and so it was that only the second manned flight of the Apollo spacecraft lifted off from Kennedy on the 21st of December, 10 short weeks after Apollo 7, bound for the moon. The crew later said that they estimated their chance of succeeding to be 50-50. Precisely 69 hours, 8 minutes and 16 seconds after launch, the command module's engine fired to slow the spacecraft down and allow it to be captured by the moon's gravity, putting the 3 astronauts into lunar orbit. Newton's almost 300-year-old equations were used to calculate the trajectory. This was a spectacular, practically unbelievable engineering triumph. Less than a decade after Yuri Gagarin became the first human to orbit the Earth, 3 astronauts traveled all the way to the moon. But the mission's powerful and enduring cultural legacy rests largely on 2 very human actions by the crew. One was the famous and moving Christmas broadcast. the most watched television event in history at that time, when distant explorers read the first lines from the book of Genesis. "We are now approaching lunar sunrise, and for all the people back on Earth, the crew of Apollo 8 has a message that we would like to send to you," began Anders. "In the beginning, God created the heaven and the earth was without form and void, and darkness was upon the face of the deep." Borman concluded with a sentence clearly spoken by a lonely man 400,000 kilometers from home. "And from the crew of Apollo 8, we close with good night, good luck, a Merry Christmas, and God bless all of you on the good Earth." The mission's most potent legacy, however, is NASA image AS8142383, snapped by Bill Anders on a Hasselblad 500 EL at f11 and a shutter speed of 1/250th of a second on Kodak Ektachrome film. It was, in other words, a very bright photograph. The image is better known as Earthrise. When viewed with the lunar surface at the bottom, Earth is tilted on its side with the South Pole to the left and the equator running top to bottom. Little landmass can be seen through the swirling clouds, but the bright sands of the Namib and Saharan deserts stand out salmon pink against the blackness beyond. Just 368 years and 10 months after a man was burned at the stake for dreaming of worlds without end, here is Earth, a fragile crescent suspended over an alien landscape, the negative of a waxing moon in the friendly skies of Earth. This is an unfamiliar planetary Earth, no longer central, just another world. When Kennedy spoke of Apollo as a journey to an unknown celestial body, he meant the moon. But we discovered Earth, and in the words of T.S. Eliot, came to know the place for the first time.
Today, Venus has the slowest rotation of any planet in the solar system, taking 243 Earth days to complete one rotation on its axis. This period is known as the sidereal day, which is different to a solar day, the time it takes for the Sun to return to the same point in the sky. On Earth, the sidereal day at 23 hours 56 minutes and 4.1 seconds is very close to the solar day, which lasts pretty much exactly 24 hours. But on Venus, the difference between these two periods is much greater. Even though the planet takes 243 days to rotate on its axis when combined with its orbit, a solar day on Venus lasts for 116.75 Earth days. It means every day on Venus lasts almost 4 months on Earth. And not only that, but Venus also rotates from east to west, one of only 2 planets to do so, along with Uranus. So across this toxic world, a sunrise would last literally for days as it inches across the sky. This slow progression of the Sun in the Venusian sky, due to the planet's creeping rotation, has raised many questions about how in the past the planet would have been heated, and how the climate would have been affected by such a different rotation compared with the Earth's. Today, the climate of Venus is what is known as isothermal. There is a constant temperature between the day and night sides, and between the equator and the poles. This is because the thick atmosphere literally acts like a blanket, dissipating the heat of the Sun so that the only real variation in temperature on the Venusian surface occurs due to differences in altitude. In its past, however, this may have been very different. With a more Earth-like atmosphere, so the Sun would have been beating down on the planet's surface for days on end. To make things even more complex, we know the spin of a planet is intimately linked to its climate, and we've got strong evidence to suggest that how fast a planet spins is directly related to its chance of habitability. Until very recently, it was assumed that the slow rotation of Venus must have been caused by the presence of a thick atmosphere early on in its history that in effect acted as a brake on the planet's spin. However, recent studies now suggest that the planet could have had a thin atmosphere like that of modern Earth, and still have ended up with its slow rotation. Gradually, as we start to build a picture of ancient Venus, we begin to see beyond the cloud cover of today, through to an ancient planet with an Earth-like atmosphere, and a day lasting over 200 Earth days as the sun beat down on the ocean-covered surface. To make sense of the climate of this Earth-like Venus, the team at the Goddard Institute needed to make another tweak, or postulation to be more precise, to the model. With the sun hitting the one side of the surface for so much longer than on the Earth, the evaporation rate of the oceans would be far greater and potentially incompatible with the water world we suspect existed. But by simply adjusting the amount of dry land on the surface of Venus, especially in the tropics, the effect is dramatic. With a higher percentage of land, the models suggest that even the slow rotation would not dry out the planet, and it could have held on to enough water to be ripe for supporting the emergence of life. By combining all of this data, the GIST team have painted our most up-to-date picture of early Venus, and it's a beguiling image. Within the infant solar system, it is a planet the size of Earth, with similar atmosphere to the one we see today. On Venus, days lasted for months as the sun arced slowly across the sky from west to east, rising and setting over a vast, shallow ocean. Finally, the data from radar measurements taken by NASA's Magellan mission in the 1990s was used to paint the last brushstrokes of this long-lost world. Filling in the lowlands with water, the topography of this ancient world emerges, with the highlands exposed as the Venusian continents. It all points to the possibility that Venus could have been the first habitable world in our solar system. So what changed? To find out, we need to look not just at the planet in isolation, but also at the star around which it orbits. No planet lives out its life in isolation. Venus, like all the planets, is not just part of a configuration of planets and moons, asteroids and comets, but is also part of a solar system, a system that is driven more than anything else by the star at its center. Today, the sun burns bright in our skies, bathing our planet in just enough starlight to keep the oceans from freezing, but not too much to boil them away. Earth lies in the sweet spot we call the Goldilocks zone, but as we have already seen in this chapter, nothing in the solar system is forever, and what we see today is not what we will see tomorrow, nor what we would have seen yesterday. As our sun gets older, it's gradually burning hotter and hotter. This is because as it ages, the process of nuclear fusion, the fusion of hydrogen into mainly helium, gradually leads to an increase in the amount of helium in its core. This rise in helium causes the sun's core to contract, which in turn allows the whole star to shrink in on itself, creating an increased pressure that results in a rise in the rate of fusion, and so the energy output of the sun goes up. If tomorrow the sun is burning hotter than today, it of course makes sense that in the early days of the solar system our sun burned far less brightly. It's a life cycle that is common to all main sequence stars, the category of star that includes our sun. And as the most common type of star in the universe, we've been able to study this life cycle in intimate detail, allowing us to make immensely detailed predictions about the characteristics of our sun in the past and in the future. Winding back the clock, the current consensus among astronomers is that 4 billion years ago the faint young sun was at least 30% dimmer than it is today. This cooler sun would have undoubtedly had a big impact on all of the terrestrial planets. Earth would have been much colder, and as it was receiving far less solar energy, it remains something of a mystery as to why our planet wasn't frozen solid. Instead, at this time on Earth, first life was just beginning, in the liquid water that we are pretty certain covered its surface. At the same time, 3.5 to 4 billion years ago, the young sun would have bathed Venus in a warmer glow. This ocean world found itself in its very own sweet spot, a world held in a delicate balance. With the sun weakened and restrained, the Earth-like atmosphere of Venus could act as a gentle blanket, keeping the surface temperate and covered in an abundance of liquid water. But even with this additional solar energy, we think Venus would still have been much cooler than the Earth is today. In fact, we believe temperatures at that time would have been like a pleasant spring day here on Earth. It wasn't to last. Slowly the young sun grew brighter, its increased energy output causing temperatures to gradually rise, which in turn began to lift more and more water vapor into the air, thickening the atmosphere and sealing the planet's fate. Although the oceans of Venus may have persisted for billions of years, as the surface warmed and the atmosphere thickened, the destiny of this planet was already set, driven by an unstoppable process we have recently become very familiar with here on Earth. The greenhouse effect is a process that has the power both to protect and to destroy a planet. But despite this power, it actually boils down to some pretty simple physics. It's all about how sunlight, solar radiation, interacts with the constituent parts of an atmosphere. In the case of the Earth, as solar radiation hits our atmosphere, some of it is reflected straight back out into space, some is absorbed by the atmosphere and clouds, but most of the sunlight, about 48%, passes straight through the atmosphere and is absorbed by the Earth's surface, where it is heated up. The reason so much solar radiation makes it to the surface is because the gases in our atmosphere, like water vapor and carbon dioxide, are transparent to light in the visible spectrum. When you think about it, that's pretty obvious, because there's a source of visible light in the sky, the sun, and we can all see it. But it's a different story when that sunlight heats the surface of the Earth and re-radiates back out, not as visible light, but as the longer wave infrared light, thermal radiation. We can't see this light, but as it radiates back out from the Earth's surface, carbon dioxide and water vapor absorb the infrared, trapping that energy, and so the planet maintains a higher temperature that is intimately linked to the constituent parts of the atmosphere. The higher its level of gases like water vapor, carbon dioxide, methane, and ozone, the greater the greenhouse effect and the bigger the uplift in temperature. Despite the very real threat that this now poses to the future of our planet, the greenhouse effect on its own is not necessarily a bad thing. The Earth would be at an average temperature of around -18 degrees Celsius without it. But as we are currently witnessing here on Earth, shift the balance of those gases, and things can change very quickly. At some point in Venus's past, the levels of water vapor lifted into the atmosphere by the warming sun pushed the greenhouse effect to become precariously more intense. With less and less of the sun's energy escaping, the ambient temperatures began to rise exponentially, until the day came when the last raindrops fell onto the surface of the planet, the heat evaporating the rains long before they could reach the ground. Venus had reached a tipping point. With the increasing temperatures feeding more and more water vapor into the atmosphere, a runaway greenhouse effect took hold, driving away the oceans. This led to the surface of the planet getting so hot that carbon trapped in rocks was released into the atmosphere, mixing with oxygen to form increasing amounts of another greenhouse gas, carbon dioxide. With no water left on the surface and no other means to remove it, carbon dioxide built up in the atmosphere, setting the planet on a course that would result in the scorched body that we see today. And so Venus's moment in the sun came to an end. Earthlings take note. When it comes to the greenhouse effect, there is a precariously thin line between keeping a planet warm and frying it. Of the 4 rocky worlds, only one has managed to navigate through the instability and constant change of our solar system over the last 4 billion years and maintain the characteristics needed to support life. Mercury lost its fight early as it was flung inwards towards the sun. Venus flourished at first before slowly coming to the boil, and Mars, the runt of the litter, became a frozen wasteland long ago. Only Earth, uniquely among the planets, has persisted with an adequate stability over the last 4 billion years, to allow liquid water to remain on its surface, and an atmosphere just thick enough to keep its climate calm, not too hot and not too cold. Events have rocked us, and extremes of temperature have waxed and waned, but never outside of the parameters needed to harbour life. In a chaotic solar system filled with planetary might-have-beens, Earth is a shining example of stability, and the evidence for this is to be found in every nook and cranny of the planet. Today, Earth is dominated by life. The land and seas are teeming with millions upon millions of species, with thousands of new life forms discovered each year. Somehow, even when disaster threatened, the Earth has remained a living world. While endless species have come and gone, life has always persisted. It's woven into the fabric of the planet, an integral part of every continent and every ocean. Life plays a crucial role in maintaining the balance of the atmosphere that keeps our planet temperate. But we know for certain it cannot last. The Kamchatka Peninsula in eastern Siberia is one of the most inhospitable places on Earth. A volcanic wasteland, peppered with thousands of hot springs, it's here that we find some of the toughest living things. Extremophiles survive here that are able to withstand temperatures and pH levels higher than any other land-based life forms we have ever discovered. Kamchatka is part of the Pacific Ring of Fire, and despite its remoteness, biologists have long been enticed here to explore its toxic, bubbling cauldrons for signs of life. Complex life, animals and plants, struggle to survive in temperatures above 50 degrees Celsius, so searching for life here is all about searching for single-celled life forms, bacteria and archaea, ancient microorganisms, that are somehow able to endure in this hostile environment. Life forms like Acidilobus aceticus, an archaea that can be found in a hot spring where the water is so acidic it reaches a pH of 2, and where temperatures rise to 92 degrees Celsius. In other parts of the hydrothermal field, bacteria like Desulforella acetivorans have been discovered, which happily live in pools that are touching 60 degrees Celsius, but it's these that are the real hotheads. In one of the biggest and hottest pools investigated by scientists, a large number of microbes have been found living in temperatures approaching 97 degrees, making it one of, if not the, hottest environment ever studied for signs of life on land. But to find the greatest hotheads on planet Earth, you need to look not on land, but deep beneath the sea. In the furthest depths of the Atlantic, around the black smoker hydrothermal vents blurting out of the ocean floor, we found strains of archaea that can survive temperatures of 122 degrees Celsius, and perhaps even higher. These rare life forms live at the very edges of biology. Unique adaptations to their cellular chemistry enable the proteins and nucleic acids that create the structure of the microorganism to function, while the membranes that are protecting the cells utilize different fatty acids and lipids to keep the cells stable at the higher temperatures. Perhaps there are even tougher life forms that we are yet to discover, but the thermophilic microorganisms that we have so far identified and investigated in places like Kamchatka all point to the fact that life has its limits. Evolution by natural selection can only adapt so much, and even though it's impossible to imagine what life on Earth will look like in a few 100 million or even a few billion years' time, we know that biology is constrained by thermodynamics, and so we can say with some certainty that there will come a time when the Earth is too hot for any living things to exist. Natural selection will eventually run out of options as the laws of physics outplay it, and all life will come to an end. When this will happen, no one can be certain, but as the sun ages and grows hotter, temperatures on Earth will rapidly rise. Today, the average surface temperature on the planet is 14.9 degrees Celsius, but with just a 10% rise in the sun's luminosity, the average temperature will rise to 47 degrees Celsius and climbing. The increased temperatures will raise great storms across the planet. The rains will remove carbon dioxide from the atmosphere, and it will be locked away as newly formed sedimentary rock. Trees and plants will struggle as they are robbed of the gas that sustains them, until eventually photosynthesis will cease. The lungs of our planet will fail, and the precious oxygen that green plants and algae produce will dwindle. With the primary food source gone, the food chain will collapse and the age of complex life on Earth will draw to a close. Heat-loving extremophiles may flourish for millions of years more, but eventually nuclear physics will have its way, and as average temperatures race above 100 degrees Celsius, the last pockets of life will be extinguished from the Earth. We can say with confidence this is going to happen because we can plot the future of our Sun far more precisely than the future of the Earth. Our understanding of nuclear physics allows us to predict what happens inside the cores of stars, and thus we can see the past, present, and future of stars like ours written across the night sky. The heavens are filled with shining examples of stars that give us a glimpse into the future of our Sun. Arcturus, for example, in the constellation Boötes, is one of the brightest stars in the northern hemisphere. It's around the mass of the Sun, perhaps a little bit heavier, and so in the distant past would have had remarkably similar characteristics to our own star. Today, though, Arcturus is 6 to 8 billion years old, potentially 3 billion years older than the Sun, and as it is no longer a main sequence star, it is now in the red giant phase. Its fuel exhausted, it has swollen up to 25 times its original diameter and is around 170 times as luminous, despite the fact that as its core slowly burns out, it is cooling. To see even further into the future, we need to look towards the brightest star in the northern sky, Sirius. The dog star, as it's commonly known, is twice the mass of the Sun and still fully in the main sequence. But obscured by the glare of Sirius A is a faint companion, Sirius B. This is a star that has already burnt through its fuel, swollen into a red giant, and the outer layers have drifted off into space, leaving the fading core of the star about the size of the Earth, known as a white dwarf. These stars are just two examples amongst many that point us towards the ultimate fate of our Sun, a fate that we believe will play out over the next 5 billion years or so. Just like Arcturus, as the Sun exhausts its hydrogen fuel, its outer edge will inflate and it will enter a red giant phase. Expanding millions of kilometers out into space, it will engulf Mercury first. Venus's fate will be sealed next as the Sun expands further. Some models predict that Earth may just escape the fiery end of its neighbors, heated to 1,000 degrees Celsius, but hanging on beyond the edge of the dying star as its orbit extends out due to the lessening mass of the Sun. Dead but not destroyed, Earth and Mars will orbit as burned-out relics of their former selves. The era of the 4 rocky inner planets will be over, the billions of lives lived on the surface of one of them nothing but a distant memory. But within our solar system lies another family of rocky worlds, whose moment in the Sun may be to come. Far beyond the asteroid belt, millions of miles away from the sun-drenched planets of the inner solar system, the gas giants of Jupiter and Saturn are home to another family of rocky worlds. Jupiter alone has 79 known moons orbiting it, a menagerie of satellites of multiple shapes and sizes. We've been peering at these moons since Galileo Galilei spotted 4 of them, Io, Europa, Ganymede, and Callisto, known as the Galilean moons, over 400 years ago, with his telescope transforming our understanding of our place in the solar system. Today we have explored the Galilean moons not just from afar, but close up, and found them to be dynamic worlds. Io is fiercely volcanic, and Europa, the ice moon, shows tantalizing evidence on its surface pointing to a subsurface ocean sitting below its icy crust. Ganymede and Callisto make up the final 2 Galilean moons, and just like Europa, they are rocky worlds with an abundance of water ice on their surfaces, and perhaps their own oceans lurking beneath. These 3 rocky, frozen worlds are all sitting in the cold outreaches of our solar system, touched by the distant sun but barely warmed, lying dormant until perhaps one day the aging sun will reach out and turn these bodies into ocean worlds for the very first time. The next planet out, Saturn, also has its ever-growing family of moons. Amongst its collection of over 60 confirmed satellites are Titan, the only known moon with a dense atmosphere and liquid lakes on its surface, though they are primarily methane, not water, and Enceladus, a frozen ice moon just like Europa with a liquid ocean deep beneath its ice. We will come to Enceladus in detail in Chapter 4, but for now it's intriguing to note that this icy moon may be our best current candidate as a second life-sustaining world in our solar system. Until we go back and explore further, we can't be certain what lies below its surface. But the possibilities that the Cassini probe has so tantalizingly hinted at make it one of the most exciting places for us to visit within the next generation of interplanetary expeditions. All these ice worlds, sitting dormant in the frozen reaches of the solar system, offer the promise of a very different future, one in which the rocky worlds of the inner solar system have been reduced to cinders, and a new generation of worlds waits to awaken. Ice worlds will become water worlds, warmed by the expanding sun, until our dying star ultimately collapses into a white dwarf.
Outwards to the Milky Way. Newton's laws are the keys to understanding our place in our local neighbourhood. Coupled with precision observations of the motion of the planets and moons, they allow the scale and geometry of the solar system to be deduced and their positions to be calculated at any point in the future. The nature and location of the stars, however, requires an entirely different approach, because at first sight they appear to be point-like and fixed. The observation that the stars don't appear to move is important if you know something about parallax, as the ancients did. Parallax is the name given to a familiar effect. Hold your finger up in front of your face and alternately close each of your eyes, keeping your finger still. Your finger appears to move relative to the more distant background, and the closer your finger is to your face, the more it appears to move. This is not an optical illusion. It's a consequence of viewing a nearby object from two different spatial positions, in this case the two slightly different positions of your eyes. We don't normally perceive this parallax effect because the brain combines the inputs from the eyes to create a single image, although the information is exploited to create our sense of depth. Aristotle used the lack of stellar parallax to argue that the Earth must be stationary at the centre of the universe, because if the Earth moved, then the nearby stars would be observed to move against the background of the more distant ones. Thousands of years later, Tycho Brahe used a similar argument to refute the conclusions reached by Copernicus. Their logic was completely sound, but the conclusion is wrong because the nearby stars do move relative to the more distant background stars as the Earth orbits the Sun, and indeed as the Sun orbits the galaxy itself. You just have to look extremely carefully to see the effect. Amongst the thousands of stars visible to the naked eye, 61 Cygni is one of the faintest. It's not without interest, being a binary star system of two orange K-type dwarf stars, slightly smaller and cooler than the Sun, orbiting each other at the lethargic rate of around 700 years. Despite the pair's relative visual anonymity, however, 61 Cygni has great historical significance. The reason for this quiet fame is that this faint star system was the first to have its distance from Earth measured by parallax. Friedrich Bessel is best known to a physicist or mathematician for his work on the mathematical functions that bear his name. Pretty much any engineering or physical problem that involves a cylindrical or spherical geometry ends up with the use of Bessel functions, and in blissful ignorance, you will probably encounter some piece of technology that has relied on them in the design process at some point today. But Bessel was first and foremost an astronomer, being appointed director of the Königsberg Observatory at the age of only 25. In 1838, Bessel observed that 61 Cygni shifted its position in the sky by approximately 2/3 of an arcsecond over a period of a year as viewed from Earth. That's not very much, An arcsecond is 1/3600th of a degree. It is enough, however, to do a bit of trigonometry and calculate that 61 Cygni is 10.3 light-years away from our solar system. This compares very favourably with the modern measurement of the distance, 11.41 plus or minus 0.02 light-years. Parallax is so important in astronomy that there is a measurement system completely based on it, which allows you to do these sums in your head. Astronomers use a distance measurement known as a parsec, which stands for per arcsecond. This is the distance of a star from the Sun that has a parallax of 1 arcsecond. 1 parsec is 3.26 light-years. Bessel's measurement of the parallax of 61 Cygni was 0.314 arcseconds, and this immediately implies that it's around 10 light-years away. Even today, stellar parallax remains the most accurate way of determining the distance to nearby stars, because it is a direct measurement which uses only trigonometry and requires no assumptions or physical models. On the 19th of December 2013, the Gaia space telescope was launched on a Soyuz rocket from French Guiana. The mission will measure, by parallax, the positions and motions of 1 billion stars in our galaxy over 5 years. This data will provide an accurate and dynamic 3D map of the galaxy, which in turn will allow for an exploration of the history of the Milky Way, because Newton's laws, which govern the motions of all these stars under the gravitational pull of each other, can be run backwards as well as forwards in time. Given precise measurements of the positions and velocities of 1% of the stars in the Milky Way, it is possible to ask what the configuration of the stars looked like millions or even billions of years ago. This enables astronomers to build simulations of the evolution of our galaxy, revealing its history of collisions and mergers with other galaxies over 13 billion years, stretching back to the beginning of the universe. Newton and Bessel would have loved it. Stellar parallax, when deployed using a 21st century orbiting observatory, is a powerful technique for mapping our galaxy out to distances of many thousands of light-years. Beyond our galaxy, however, the distances are far too great to employ this direct method of distance measurement. In the mid-19th century, this might have appeared an insurmountable problem, but science doesn't proceed by measurement alone. As Newton so powerfully demonstrated, scientific progress often proceeds through the interaction between theory and observation. Newton's law of gravitation is a theory. In physics, this usually means a mathematical model that can be applied to explain or predict the behavior of some part of the natural world. How might we measure the mass of a planet? We can't weigh it directly, but given Newton's laws, we can determine the planet's mass very accurately if it has a moon. The logic is quite simple. The moon's orbit clearly has something to do with the planet's gravity, which in turn has something to do with its mass. These relationships are encoded in Newton's law, and careful observation of the moon's orbit around the planet therefore allows for the planet's mass to be determined. For the more mathematical reader, the equation is m planet plus m moon equals 4 pi squared a cubed over gp squared, where a is the time average distance between the planet and the moon, g is Newton's gravitational constant, and p is the period of the orbit. This equation is in fact Kepler's third law, discovered empirically by Kepler in 1619. Kepler's laws can be derived from Newton's law of gravitation. Under the assumption that the mass of the planet is far larger than the mass of the moon, this equation allows for the mass of the planet to be measured. This is how theoretical physics can be used to extract measurements from observation, given a mathematical model of the system. To measure the distance to objects that are too far away to use parallax, therefore, we need to find a theory or mathematical relationship that allows for a measurement of something, anything, to be related to distance. The first relationship of this type, which opened the door to all other methods of distance measurement out to the edge of the observable universe, was discovered at the end of the 19th century by an American astronomer named Henrietta Leavitt.
Mars is a mirror for our dreams and nightmares. To the naked eye, the planet exhibits a reddish hue, blood red in the imagination, god of war, star of judgment. Through a small telescope, it is the most Earth-like of planets, with cinnabar deserts and white polar ice caps. A world we could imagine visiting, perhaps even settling in. 19th-century astronomers convinced themselves they saw plains and mountain ranges, and canals delivering meltwater from high latitudes to arid equatorial cities. Some thought the Martians a peaceful civilization, far in advance of our own. Others saw threat. Across the gulf of space, minds that are to our minds as ours are to those of the beasts that perish, intellects vast and cool and unsympathetic, regarded this earth with envious eyes, wrote H.G. Wells in his classic science fiction novel The War of the Worlds in 1897. The nature of Mars remained a mystery until well into the 20th century, because the planet is small and far away, and therefore difficult to view with ground-based telescopes. Even the Hubble Space Telescope, high above the distorting effects of Earth's atmosphere, produces images which would not at first sight have prevented Wells from publishing. With a little imagination, the ice caps, high clouds, and dark regions circling the deserts could be mistaken for evidence of a water cycle feeding the seasonal advance and retreat of vegetation. Photographs from the first flyby of Mars by NASA's Mariner 4 spacecraft on the 15th of July 1965 abruptly laid to rest the romantic notion of Mars as Earth's habitable twin or potential foe. These images revealed an arid surface reminiscent not of our blue planet, but of our desiccated moon. Overnight, we discovered for certain that Earth is the only planet in the solar system capable of supporting complex life. And contemporary accounts of the impact of the Mariner 4 flyby suggest that this was a powerful realization. In November 1965, the Bulletin of the Atomic Scientists carried an article entitled "The Message from Mariner 4," and the message was bleak. The shock of Mariner's photographic and radiometric reports is caused not only by their denial of the terrestrial image of Mars, but by the revelation that there is no second chance, at least not in the solar system. President Lyndon B. Johnson was reported as commenting, it may just be that life as we know it, with its humanity, is more unique than many have thought." The hesitation in the first few words is revealing. Here is Mars as a symbol of our cosmic isolation. It is as though deep, or perhaps not so deep, in the subconscious, the 1960s power brokers all the way up to the president suddenly understood that the Earth is far more fragile and precious than a dispassionate analysis of their Cold War brinkmanship might suggest. Or perhaps the perspective delivered by exploration is always shocking. Apollo 8's Earthrise, the photograph that delivered such a positive end to a troubled 1968 by setting the blue Earth against the grey moon, was 3 years away. But Red Mars provided a foretaste. In response, Carl Sagan co-authored a paper suggesting, somewhat playfully, that all was not lost. Mariner 4 took only 22 photographs with a resolution of over a kilometre, in a strip crossing the region in which the astronomer Percival Lowell had sketched canals from his observatory in Flagstaff, Arizona at the turn of the 20th century. From the warmth of the Arizona desert, Lowell wrote that Mars was chilly, but no more so than the south of England, which certainly supported a civilization of sorts. Using several thousand photographs of a similar resolution taken by meteorological satellites in Earth's orbit, Sagan and his co-authors found only a single feature that unambiguously indicated the presence of a civilization: Interstate Highway 40 in Tennessee. They concluded that Mariner 4 would not have detected human civilization had it flown by Earth. We do not expect intelligent life on Mars, but if there were intelligent life on Mars comparable to that of Earth, a photographic system considerably more sophisticated than Mariner 4 would be required to detect it. The non-existence of an extant Martian civilization was confirmed by the Mariner 9 mission in November 1971, the first spacecraft to orbit another planet. Mariner 9 achieved a photographic resolution of 100 meters per pixel, and no sign of intelligent life, past or present, was detected. The twin Viking landers in 1976 failed to detect even microbial life, although the combined results of the suite of microbiology experiments carried by the spacecraft are not considered to be unequivocal, because Martian soil chemistry is, to coin a phrase from the official NASA report, enigmatic, and could conceivably have masked any biological activity. In hindsight, the fact that Mars is not teeming with life today is not so surprising. Mars orbits 50 million miles further from the Sun than Earth, and receives less than half the solar energy. It is a small world with a tenuous atmosphere that provides little insulation or greenhouse warming. NASA's Curiosity rover in the Gale crater has measured midday temperatures above 20 degrees Celsius, but in the early hours of the morning it has experienced minus 120. As Alfred Russel Wallace wrote in 1907, any attempt to transport water across the Martian surface today would be the work of madmen rather than of intelligent beings. There are no canals, no cities, and no envious eyes. The planet is a frozen, hyper-arid desert, too far from the Sun to support complex life. Yet it hasn't always been this way. Observations from our fleet of orbiting spacecraft and landers have revealed a complex and varied past. Once upon a time, the red planet was glistening blue. Streams ran down hillsides, and rivers wound their way through valleys, carved by a water cycle from land to sky and down again, from mountains and highlands to the sea. This presents a great challenge for planetary scientists. Put simply, nobody would have been surprised if Mars had always been an inert rock because it is a small planet far from its star. But the geological evidence is unequivocal. The surface tells a different story. Mars, then, remains an enigma. As a wandering red star, it stirred the imagination of the ancients. As a telescopic image, too small and shifting for visual or intellectual clarity, it became our twin. When spacecraft flew by, it shocked us into considering our cosmic isolation. The red planet was relegated in our collective consciousness to the status of just one more rock glistening in the night. Then we landed and discovered a world that was once habitable and could be again. A map of Mars can be read like a history book. Unlike Earth, where constant weathering, tectonic activity and volcanism have erased the deep geological past, Mars has been relatively quiescent for most of its life. The scars of collisions from the first turbulent billion years after the formation of the solar system can still be seen from orbit. Ancient cataclysms documented below a thin film of dust. NASA's Mars Global Surveyor spacecraft spent 4.5 years mapping Mars in the late 1990s and provided detailed maps with colors corresponding to differences in altitude. Just as on Earth, there is significant variation, but the geological features on our smaller sister world are much bigger and bolder. The highest elevations on Mars are found on the Tharsis Rise, a great volcanic plateau and home to the largest volcano in the solar system, Olympus Mons. At over twice the height of Everest, Olympus Mons towers 25 kilometers above the lowlands of Amazonis Planitia to the west, and its base would fit inside France just about. Cutting a deep scar across Tharsis to the southeast of Olympus Mons is Valles Marineris, named after the Mariner 9 spacecraft that discovered it, a canyon that dwarfs anything on Earth. The Grand Canyon would fit into one of its side channels. The lowest points on Mars are found in the Hellas Impact Basin, the largest clearly visible impact crater in the solar system. From the highest points on the crater rim to the floor, Hellas is over 9 kilometers deep. It could contain Mount Everest. The atmospheric pressure at the floor is twice that at the rim, high enough for liquid water to exist on the surface, in a narrow range of temperatures. These are extreme altitude differences for a small world. Over 30 kilometers from the summit of Olympus Mons to the floor of Hellas, On much larger Earth, for comparison, there is only 20 kilometres difference between the summit of Everest and the Challenger Deep in the depths of the Mariana Trench. The most striking and ancient elevation difference on Mars is that between the northern and southern hemispheres of the planet, known as the global dichotomy. Mars is an asymmetric world. The northern hemisphere is on average 5.5 kilometres lower in altitude than the southern. There is no consensus as to how the dichotomy formed, other than that it was early in the planet's history, and before the large impacts which created the Utopia and Chryse basins around 4 billion years ago. At some later time, the northern lowlands were resurfaced by volcanic activity in a similar fashion to the smooth lunar seas, which accounts for their lack of cratering relative to the much more ancient terrain to the south. The oldest terrain on Mars is found in the Noakis Terra region of the southern highlands. It is characterized by heavy cratering reminiscent of the far side of the Moon. Even small craters in the Noakian highlands are heavily eroded, which suggests the regular, if not persistent, presence of liquid water. There are dry river valleys and deltas, and evidence of water pooling in the craters and overflowing their walls, forming interconnected networks of lakes. This is how we know Mars was once a warmer and wetter world, at least occasionally. The evidence is written across the land of Noah. In contrast, the younger terrain of Hesperia Planum displays much less evidence of regular erosion by water, but bears the scars of occasional catastrophic floods that cut deep valleys over very short periods of time, and may have formed temporary large lakes or seas. The Amazonis Planitia region shows little sign of flowing water, fewer impact craters, and less evidence of active volcanism, suggesting it was formed more recently, when Mars was significantly less geologically active. The persistence of surface features over many billions of years in the Noakian, Hesperian, and Amazonian regions has led to the historical epochs of Mars being named after the distinctive terrains that still bear the characteristic marks of the climate and geological activity that formed and sculpted them. The Noakian period was the earliest and wettest, and coincided with the origin of life on Earth around 4 billion years ago, when conditions on both worlds appear to have been very similar. The Martian atmosphere may have been denser than Earth's and dominated by carbon dioxide, but significant questions remain about how such an atmosphere could have warmed Mars sufficiently to deliver the warm, wet climate, and how that atmosphere was lost. The MAVEN spacecraft, currently in orbit around Mars, aims to answer this question, as we'll discuss later in this chapter. The Noakian period ended as Mars became increasingly cold and arid around 3.5 billion years ago, just as life was gaining a foothold on Earth. The Hesperian period, the time of catastrophic floods, ran from the end of the Noakian to around 3 billion years ago, when Mars entered its current frozen, arid phase, punctuated by occasional volcanic activity and the large-scale movement of ice, but with very little evidence of flowing water. The long 3 billion-year freeze from the end of the Hesperian to the present day is known as the Amazonian. This is a summary of what we know about Mars. The whys pose a significant challenge to planetary scientists. Given a warm, wet, and seemingly stable world early in its history, what triggered the loss of atmosphere and descent into modern-day aridity? What happened to the water on Mars? Was it lost to space, or does it persist today as surface ice or in subsurface rocks or reservoirs? If so, how much water is still accessible? Could we exploit the ancient reservoirs of Mars to support a human colony? And perhaps most significantly of all, did life arise on the planet during the Noakian period, coincident with the origin of life on Earth? And could that life still be present on Mars today? The current fleet of spacecraft in orbit around Mars and roving across its surface has been designed to answer these questions. Mars today is a planet buzzing with activity. Communications to Earth and the Martian Internet are managed by the Mars Reconnaissance Orbiter, MRO, an orbiting bridge between worlds. MRO carries the HiRISE instrument, a camera with resolution high enough to see basketball-sized features on the Martian surface. The Mars Color Imager Marquee camera monitors Martian weather, and the Compact Reconnaissance Imaging Spectrometer for Mars, CRISM, identifies mineral deposits, particularly those formed in the presence of surface water. Orbiting with the MRO is the Mars Atmosphere and Volatile Evolution Mission, MAVEN. This cameraless spacecraft operates between 150 kilometers and 6,000 kilometers above the Martian surface, measuring the composition of the atmosphere at different altitudes and observing how the tenuous gases are stripped from the planet by the solar wind. Mars Odyssey is the veteran of the orbiting fleet, having arrived in 2001 and still being operational in a polar orbit, searching primarily for water ice on the surface. Mars Express is a European Space Agency mission that is delivering high-resolution photographs, mineralogy data, radar investigation of the near subsurface, and atmospheric measurements, including the search for methane, a gas that on Earth is associated with biological activity. India's Mangalyaan space probe is primarily a technology demonstrator, but it carries a secondary scientific package capable of investigating atmospheric composition. The newest arrival at Mars is the joint European Space Agency Russian ExoMars Trace Gas Orbiter, which will observe seasonal changes in the Martian atmosphere and search for subsurface water deposits. The spacecraft will form the communications bridge for ESA's ExoMars rover, due to land in 2021. The two most recent explorers of Mars are the Opportunity and Curiosity rovers. The Opportunity rover landed on the Meridiani planum close to the Martian equator on the 25th of January 2004, with a planned lifetime of 90 Earth days. In a spectacular testament to the Jet Propulsion Laboratory's engineering excellence, Opportunity remained operational until a planet-wide dust storm covered its solar panels in June 2018, after over 14 years and a journey of 45 kilometers on the surface of Mars, exploring the Endurance, Victoria, and Endeavour craters. On the 13th of February 2019, Opportunity was finally declared dead. Opportunity's younger and far larger companion on Mars is Curiosity, the most massive and most capable spacecraft ever to touch down on a planet beyond Earth. The landing itself was a tour de force of engineering ingenuity and audacity. The enormity of the mission is best described through the words of Alan Chen, operations lead at NASA for the Curiosity mission, at 10:31 PDT on the 5th of August 2012, watching the landing at the Jet Propulsion Laboratory alongside the team. The engineers described it as 7 minutes of terror. 7 minutes to maneuver a spacecraft that had taken 8 years to design and build, with a program cost of more than $2.5 billion, from 13,000 miles per hour at the top of the Martian atmosphere to a soft landing on the surface of the planet. The tension reflected the high stakes. The Mars Science Laboratory mission, to give the lander and orbiter their full title, was a high-risk flagship science mission in the same category as Voyager, the Hubble Space Telescope, Viking and Cassini, and was beset by cost and schedule overruns and controversy. This is in many ways unsurprising. New technologies and ambitious scientific objectives are difficult to implement and achieve, and in part because of this deliver great rewards. In hindsight, nobody would question the value of any of these missions, which have delivered some of the greatest insights and most inspiring images in the history of exploration. Yet this never prevents bean counters and rival scientists with agendas, and more charitably, budgetary challenges of their own, whinging and even considering cancellation. This is naive. Funding for science is almost always grudging from a political class whose view of the acquisition of knowledge is utilitarian. The far deeper value of exploration as a critical part of the internal voyage of our species bringing us into direct confrontation with the mystery of our existence, is lost on them, at least until occasional Johnsonian President, not Alexander Boris de Pfeffel, moments. It may just be that life as we know it with its humanity is more unique than many have thought, and we must remember this. Which means that a cancellation of one project does not mean an uplift in funds for another. More likely the budget will be lost to science. At the time of writing, the same issues plague another NASA flagship mission, the James Webb Space Telescope. As Robert D. Baum wrote in an op-ed article for Space News in December 2008, at the height of the Mars Science Laboratory controversy, when implementing flagship missions, cost and schedule overruns are not uncommon, but history shows that the mission return often eclipses the expenditure. The Hubble Space Telescope experienced a development cost overrun several times its approved project budget, and was launched much later than originally planned. In hindsight, would any rational space scientist not concede that the return from Hubble was worth the investment? Given the febrile atmosphere, however, no amount of philosophy or reason would mitigate the costs of failure of the Mars Science Laboratory mission. A landing accident was both possible and unthinkable. Delivering almost a ton of fragile rover onto the surface of Mars with pinpoint accuracy is not trivial, which is perhaps why the chosen engineering solution seemed, not to put too fine a point on it, daring. Mars has a thin atmosphere, so slowing down a spacecraft when it's travelling around 10 times faster than a bullet is hard. And yet the atmosphere is thick enough to apply sufficient frictional heating to destroy a spacecraft without adequate protection, and turbulent enough to cause significant uncertainty in the landing site of an unsteered vehicle. This renders the more obvious engineering solutions redundant. You can't simply deploy a parachute and float to the surface. The 1970s Viking landers used a combination of heat shields during aerobraking, parachutes, and retro-rockets with success. But the Curiosity engineering team dismissed this tried-and-tested solution. It did not allow for high enough precision, or for the gentle landing required for the pinpoint delivery of a large rover with delicate wheels. The Viking landers had legs built like tanks. The Viking landers also carried their heavy descent rocket systems with them to the ground, which didn't matter because they stayed put. Curiosity would have had to lug all this unnecessary mass around Mars for years. The Opportunity rover, her sister ships Spirit and the earlier Mars Pathfinder, employed a combination of aerobraking, parachutes, rockets, and airbags to cushion the falling spacecraft. But these previous rovers were lightweight in comparison, at just over a fifth of the mass of the gargantuan Curiosity. A rover of this size and complexity bouncing over the surface in an airbag cocoon was not considered feasible, primarily because of the sheer mass of the airbag system needed to cushion the impact. The lightweight Opportunity rover's landing system was almost twice the mass of the rover itself. The chosen Entry, Descent and Landing Procedure, EDL, for Curiosity, was described by mission lead Adam Stelzner as the result of reasoned engineering thought. A beautiful example of the truism that reasoned engineering thought and common sense, at least of the sort possessed by the average golf club bore, do not always match up. The Curiosity EDL appears to the untrained eye to be bonkers, or maybe overcomplicated, but it wasn't, and it worked. Tucked up inside a protective shell, Curiosity encountered the outer layers of the Martian atmosphere, 125 kilometers above the surface and traveling at around 20,000 kilometers per hour, at 10:23 p.m. Pacific Daylight Time on the 5th of August 2012. The spacecraft, at this stage cocooned inside a protective enclosure, flew entirely under the control of its onboard computers, with no input from mission control on Earth. This was the first time an autonomous guided entry system was employed for an interplanetary mission, using a combination of thrusters and the ejection of balance masses to shift the center of mass and trajectory of the spaceship, and guide it with a design accuracy of around 10 kilometers towards the chosen landing site. This guided rather than ballistic trajectory allowed for a much wider choice of landing sites for Curiosity than for the previous landers, which required around 100 kilometers of flat, safe land surrounding the nominal touchdown point. But it also required the rover to fly itself. The round-trip travel time for a radio signal to Mars was over 13 minutes when Curiosity landed, making control from the Jet Propulsion Laboratory in California impossible. During the first stage of descent, a heat shield constructed from a unique material known as pica, phenolic-impregnated carbon ablator, protected Curiosity from peak temperatures of around 2,000 degrees Celsius, generated by friction in the thickening Martian atmosphere. 4 minutes after beginning the entry phase, slowed to just under 3,000 kilometers per hour, Curiosity's parachute deployed at an altitude of 11 kilometers above the surface. The supersonic parachute is a vast and complex structure, 80 suspension lines over 50 meters long, attached to a 16-meter canopy. Having slowed to a velocity of 700 kilometers per hour with the help of the parachute, the heat shield was jettisoned at an altitude of 8 kilometers, allowing the onboard radar to get a view of the ground and deliver high-precision altitude and velocity measurements. With the parachute fully unfolded in relatively dense, low-level Martian atmosphere, Curiosity drifted in the Martian sky for 80 seconds, descending ever more slowly. At an altitude of 1.8 kilometers, traveling at a sedate 280 kilometers per hour, the NASA timeline calls for a deep breath as Curiosity separated from the parachute system and dropped in freefall towards Mars. For engineers, says the NASA website, it's like jumping out of a plane for the first time. The freefall drop was designed to allow Curiosity to separate far enough from the parachute system so that it wouldn't accelerate back into it when 300 meters further down, its retro-rockets fired and the powered descent phase of the landing began. For the Viking landers, this was the final phase. But for Curiosity, after the rockets had delivered the rover to an altitude of just 20 meters with a descent velocity of less than 1 meter per second, almost a hover, the audacious final phase of the landing protocol kicked into action: the sky crane. The rover slowly departed the rocket cradle, attached by 3 nylon wires and an umbilical cord of electrical connections 7.5 meters in length. 4 of the rockets, angled away from the vertical so as not to damage the rover, continued to fire, allowing the whole delicate system to approach the surface at walking pace. At 5 meters from the surface, Curiosity unfurled its wheels, stowed for the 8-month journey from Earth. At 10:32 p.m., the rover confirmed its wheels were in contact with the Martian surface and issued one last command through the electrical umbilical up to the sky crane: "I'm down, cut the cables, and fly away." After a 500 million kilometer journey, Curiosity was delivered safely to Mars, just 2.4 kilometers from its nominal landing point. A triumph of engineering ingenuity and brilliance. Curiosity was sent to Mars to explore Gale Crater, a 150-kilometer wide impact crater formed during the late Noachian or early Hesperian period, when liquid water would have been present at least occasionally on the surface. In the great tradition of astronomy, the crater is named after the Australian amateur astronomer, planetary observer, comet hunter, and occasional banker, Walter Frederick Gale, who discovered a host of comets as well as a number of geological features on Mars at the turn of the 20th century, using self-built telescopes in his backyard. The primary reason for choosing Gale Crater was the unusual central structure Mount Sharp, or Aeolis Mons, which rises over 5 kilometers above the crater floor. There is still debate about precisely how Mount Sharp formed, but the layers visible from orbit along its flanks suggest that it is the weathered remains of sedimentary rocks which once filled the crater and were laid down over time after the impact. Subsequent erosion by the relentless Martian winds removed much of the surrounding rock to reveal the ancient crater floor once more, while leaving the towering central structure intact. Deep, exposed sedimentary layers are extremely enticing to geologists because a cross-section through rock is a cross-section through time. As surface and atmospheric conditions change, different sorts of rock are laid down and chemically modified. As Curiosity ascends the slopes of Mount Sharp, it climbs forwards through Martian time, and scientists are close behind. Joy Crisp, the deputy project scientist from NASA's Jet Propulsion Laboratory, explained the choice of landing site in the weeks before launch. Mount Sharp may be one of the thickest exposed sections of layered sedimentary rocks in the solar system. The rock record preserved in those layers holds stories that are billions of years old, stories about whether, when, and for how long Mars might have been habitable. Just as the layers of exposed rock in the Grand Canyon on Earth reveal the story of our planet, the exposed sedimentary layers of Mount Sharp are a storybook that the winds of Mars have opened, ready for Curiosity to read. At the time of writing, Curiosity has travelled almost 19 kilometres from its landing site on the flat plains to the lower slopes of Mount Sharp, stopping along the way at each interesting site to characterise the geological environment. Curiosity's suite of scientific instruments is the most sophisticated ever installed on a spacecraft. The rover is a mobile geological laboratory capable of analysis of the Martian surface and the layers just beneath. NASA loves acronyms. Curiosity acquires samples using the SSS, the Surface Sampling and Science System. It is made up of 3 parts: the SASPAR, Sample Acquisition, Processing and Handling Subsystem, SAM, Sample Analysis at Mars Instrument, and CHEMIN, Chemistry and Mineralogy Instrument. The main components of SASPAR, which is mounted at the end of Curiosity's robot arm, are an integrated scoop and sample processing system, Chimera, and a drill for acquiring surface and subsurface samples. The Scoop and Sample Processing System surely has one of the most inventive of all NASA acronyms. CHIMRA, pronounced Chimera, after the multi-headed creature of Greek mythology, which stands for the Collection and Handling for In Situ Martian Rock Analysis Tool. Someone deserves an award for that. These are transferred into SAM, which includes a gas chromatograph, a mass spectrometer, and a tunable laser spectrometer, and CHEMIN, the first X-ray diffraction experiment ever flown in space, and the most sophisticated modern technique for characterizing mineral samples on Earth. The science returned from Curiosity is only just beginning, as older data are analyzed and published and new data from its climb up the slopes of Mount Sharp and through Martian geological time continues. But current results are consistent with, and greatly enhance the detail of, our picture of a planet that was warmer and wetter when Gale formed around 3.5 billion years ago. In early October 2012, Curiosity rolled to a halt at a place the geologists christened Rock Nest and scooped up a handful of Mars. The sample of dust, dirt and finely grained soil was fed into the SAM and heated to 835 degrees Celsius. The baking process revealed the presence of significant amounts of carbon dioxide, oxygen, and sulfur compounds. SAM's analysis also suggested the presence of carbonates, which form in the presence of water. Perhaps most surprising of all, the soil from Rock Nest didn't just provide circumstantial evidence for ancient water. Around 3% of the sample's mass was water, suspended as small ephemeral droplets of salty liquid. Curiosity is sitting on the floor of a lost lake, a body of water that filled Gale at the Noachian-Hesperian boundary. The patterns of sedimentary deposits suggest the lake rose and fell in multiple cycles over tens of millions of years. A transient landscape of ancient streams, deltas, and ponds is bounded by the border of the crater. When alighting on ancient riverbeds running down from the crater's rim, Curiosity has found sulfur, nitrogen, hydrogen, oxygen, phosphorus, and carbon, all the necessary building blocks for life. Summarizing the results in August 2017, Michael Mayer, NASA's lead scientist for the Mars exploration program, said, "A fundamental question for this mission is whether Mars could have supported a habitable environment. From what we know now, the answer is yes." In June 2018, 2 new discoveries strongly reinforced the idea that Mars was once a habitable world, and maybe still is. Curiosity found complex organic molecules a few centimeters below the surface, in rocks known as mudstone that form from silt deposited on lake beds. This means that all the ingredients for life were present at the time when Gale Crater was filled with water. Detected molecules include benzene, toluene, propane, and butane. Even more tantalizingly, Curiosity also observed a strong seasonal variation in methane levels in the Martian atmosphere today, reaffirming and enhancing previous observations of methane spikes from orbit. The important additional information from Curiosity was that the methane peaked repeatedly in the warm summer months and declined in the cooler winter, which is what would be expected if the methane had a biological origin. This is not irrefutable evidence of life on Mars today by any means. It's thought that geological processes may be able to account for such a seasonal variation, although if this were Earth, a biological explanation would be favoured. The appropriately cautious Michael Mayer had this to say in June 2018. "Are there signs of life on Mars? We don't know. But these results tell us we are on the right track." Science is a humble and cautious pursuit, and from the time of Viking we've known that Martian soil chemistry is notoriously complex and can easily catch out the unwary scientist. So we should leave it there. Curiosity continues its journey through Martian geological history emboldened. It is certainly driving across an ancient lake bed where, for a reasonably extended period over 3 billion years ago, conditions were favorable and all the ingredients for life were present. While we shouldn't speculate or read too much into the results to date, we can let our imaginations wander for a moment to picture what Gale Crater might have been like during the late Noachian, when life was gaining a foothold on her sister world. We stand on the shores of a lake partially filling Gale, fed by runoff from snowmelt on the far northern rim. Where Mount Sharp now stands, a small island breaks the surface blue, not the mountain of today, but a small central peak left over from the impact. A place of grand beauty, where each Martian evening the pale sun sets in the west beyond the island, rays glinting dimly off the still waters, interrupted by the shadow of the peak out to the crater's edge. A sundial, marking the passing of time, on a lake populated by microbial Martians.
The Earth is replete with features named after rogues, because history is the province of the rich and powerful, and the deserving rarely become either. To find more worthy geographical nomenclature, it is necessary to look further afield, to a place that escaped the attention of the vain. The dark side of the Moon is such a place, because nobody had seen it until the Soviet spacecraft Luna 3 photographed it in 1959. It isn't dark, by the way. It permanently faces away from Earth due to an effect called tidal locking, and receives the same amount of sunlight as the familiar Earth-facing side. The first humans to see it were the crew of Apollo 8, when Bill Anders memorably described it as looking like a sand pile my kids have played in for some time. It's all beat up, no definition, just a lot of bumps and holes. Lacking the smooth lunar maria, the dark side is an expanse of craters, and many of these have been named entirely appropriately after deserving scientists. Giordano Bruno is there, of course, alongside Pasteur, Hertz, Millikan, D'Alembert, Planck, Pauli, van der Waals, Poincaré, Leibniz, van der Graaf, and Landau. Arthur Schuster, the father of the physics department at the University of Manchester, is honoured. And tucked away in the southern hemisphere, next to a plain named Apollo, is a 65-kilometre wide, partly eroded crater called Leavitt. Henrietta Swan Leavitt was one of the Harvard computers, a group of women employed to work at the Harvard College Observatory by Professor Edward Charles Pickering.
By the late 19th century, Harvard had collected a large amount of data in the form of photographic plates. But the professional astronomers had neither the time nor resources to process the reams of material. Pickering's answer was to hire women as skilled and cheap analysts. Scottish astronomer Wilhelmina Fleming was his first recruit, whom he employed after proclaiming that even his maid could do a better job than the overworked males at the observatory. Fleming became a respected astronomer. She was made an honorary member of the Royal Astronomical Society in London, and amongst many important published works, discovered the Horsehead Nebula in Orion. Buoyed by this successful policy, Pickering continued to expand his computers throughout the later years of the 19th century, bringing Henrietta Leavitt into the team in 1893. Pickering assigned her to the study of stars known as variables, whose brightness changes over a period of days, weeks, or months. In 1908, Leavitt published a paper based on a series of observations of variable stars in the Small Magellanic Cloud, which we now know to be a satellite galaxy of the Milky Way. It consists of a detailed list of the positions and periods of 1,777 variable stars, and towards the end a brief but extremely important observation. It is worthy of note that in Table 6 the brighter variables have the longer periods. It is also noticeable that those having the longest periods appear to be as regular in their variations as those which pass through their changes in a day or two. This discovery immediately caught the interest of Pickering, and for good reason. If a star's intrinsic brightness is known, then it is a simple matter to calculate its distance. Put very simply, the further away an object is, the dimmer it appears. Leavitt and Pickering published a more detailed study in 1912, in which they proposed a simple mathematical relationship between the period and intrinsic brightness of 25 variable stars. This relationship is known as the period-luminosity relation. All that was required to calibrate the relation was a parallax measurement of the distance to a single variable of the type observed by Leavitt. If this could be achieved, then the distance to the Small Magellanic Cloud could be obtained. In 1913, the Danish astronomer Einar Hertzsprung, in a spectacularly accurate piece of astronomical observing, managed to measure the distance by parallax to the well-known variable star Delta Cephei. Delta Cephei has a period of 5.366341 days and lies 890 light-years from Earth, according to modern measurements by the Hubble Space Telescope. Because of its historic place as the first of Leavitt's variable stars to have its distance measured, these stars are now known as Cepheid variables. Inexplicably, even though Hertzsprung managed to get the parallax measurement and the distance to Delta Cephei correct, his published paper quotes the distance to the Small Magellanic Cloud as 3,000 light-years, which is badly wrong. The modern-day measurement is 170,000 light-years. There is speculation that Hertzsprung made a simple typographical error in the paper and for some reason couldn't be bothered to correct it. In any case, the technique had been established, and 2 years later Harlow Shapley published the first of a series of papers that refined the method and led him to the first measurement of the size and shape of the Milky Way. He concluded that the galaxy is a disk of stars around 300,000 light-years in extent, with the Sun positioned around 50,000 light-years from the center. This is roughly correct. The Milky Way is around 100,000 light-years across, and the Sun is about 25,000 light-years from the center. This was an important moment in the history of astronomy, because it was the first measurement that relegated the solar system from being the center of everything. It's true that few, if any, astronomers would have claimed otherwise by the turn of the 20th century, but science is a subject that relies on measurement rather than opinion. The journey into insignificance had begun.
The solar system is in fact a system. Although we might feel isolated on a ball of rock in the dark, that is an illusion. No planet is an island. The system evolves as one. Draw a diagram of the food chain underpinning all complex life on Earth today, and at the base is a stream of photons generated 150 million kilometers away inside the Sun. Green plants are the interface between a star and civilization.
Our understanding of Mars demonstrates that a planet's relationship with the Sun is not all light and sweetness. The star can provide the energy for life, but the solar wind can also destroy life or prevent it from ever emerging through the damage it can cause to planetary atmospheres. The solar wind emerges from the Sun's atmosphere, known as the corona. The temperature at the Sun's surface is 6,000 degrees Celsius, but the temperature of the corona is over 1,000,000 degrees Celsius, heated by energy transferred from the surface by the powerful solar magnetic field, twisted and coiled by the star's rotation. At such high temperatures, atoms cannot hold together. Electrons are ripped away from atomic nuclei, and matter exists in a fourth state, not solid, liquid, or gas, but a soup of negatively charged electrons and positive ions known as a plasma. Some of these particles are moving so fast that they escape the Sun's embrace completely, streaming outwards across the solar system at velocities in excess of 800 kilometers per second. This is the solar wind. When these high-energy charged particles reach Earth, most do not smash directly into atoms at the top of our atmosphere, because we are protected by our magnetic field. They are deflected harmlessly by stretching and distorting the field out on the night side of the planet. The stretched field occasionally reconfigures, accelerating electrically charged particles back down the magnetic field lines to the Earth's poles, where they collide with atoms and molecules in the upper atmosphere, exciting them and causing them to emit light. This is the aurora, the northern and southern lights. From Earth, the aurora can be seen by those lucky enough to be far enough north or south on the right night, when the sky is clear, the sun is active, and the interplanetary magnetic fields are favorably aligned. From the lofty vantage point of the International Space Station, the aurora reveals itself as halos dancing around the poles. It is an unforgettable sight, undoubtedly one of nature's wonders. But as is often the case in science, and in life for that matter, the experience is greatly enhanced by knowledge. The lights, dancing faster than the eye can see or perhaps the brain can comprehend, are a direct result of the structure of atoms. Electrons shifting between allowed energy levels, determined by the number of protons in the atomic nucleus that holds them captive. High-altitude oxygen glows red. An atom is struck by a charged particle accelerated down the Earth's magnetic field lines towards the pole. The interaction shifts an electron into a long-lived excited configuration. If the atom is not involved in a collision in the thin air for around 100 seconds, an eternity in atomic time, the electron will shift down closer to the nucleus, and a red photon will be emitted. At lower altitudes, a different reconfiguration inside oxygen atoms causes the emission of green photons. This time the atom must avoid collision for around a second, still an atomic eternity in the denser air. Excited nitrogen molecules add a deep red or pink to the lower edges of the towering curtains of light during intense displays. This is quantum mechanics written across the sky, the structure of atoms revealed. To calculate the colors, physicists treat the electrons as waves trapped inside a deep well created by the electric charge of the protons. Particles imagined not as tiny flecks of matter, but as fields that can span great volumes of space. The energy to drive the display comes from nuclear fusion reactions inside the Sun, a factory 1,000,000 times the volume of Earth, converting hydrogen into helium at a rate of 600 million tons per second. The weak nuclear force acts slowly and grudgingly to convert protons into neutrons in the core. Nuclear alchemy that results in the creation of neutrinos, which stream across 150 million kilometers at close to the speed of light before passing unhindered through the entire planet on their journey to infinity. Thus, 60 billion per square centimeter stream through your head every second without even a nudge, because your head is almost entirely empty space, and neutrinos hardly ever come close enough to interact with your sparsely distributed molecules. It might happen once in your lifetime. The nuclear forces at work inside the Sun also assembled the heavy elements that make up your body inside old stars long ago from hydrogen and helium forged in the first few seconds after the Big Bang, carbon, oxygen, nitrogen, sulfur, phosphorus, and iron. Gravity assembled the stars by forcing the collapse of primordial interstellar clouds, causing them to heat up in their centers and triggering the nuclear reactions that release the energy to halt the collapse for a few billion years, long enough for life to emerge in the gradient between the nuclear furnaces and the chill of the expanding universe. All of these thoughts are ignited in the imagination by the auroral display. Our experience is enhanced by knowledge. A central component of the web of physical processes that make the aurora shine is our magnetic field, which deflects the solar wind harmlessly past our planet and allows it to return in a much subdued form to the poles. Without this, the processes that Maven observes stripping the atmosphere of Mars would happen on Earth. The magnetic field is one of the most important differences between our worlds. Earth's magnetic field is generated by what is known as a dynamo, which is easy to explain in broad brush terms, but extremely complex and not fully understood in detail. The basic physics is simple. Earth's core is composed largely of molten iron, which is an electrically conducting fluid. Plumes of molten liquid rise and cool as they approach the mantle, and the Earth's rotation swings these columns around into circulating, rising and falling flows. This circulating flow acts as a dynamo and generates a magnetic field. The stability of the dynamo is related to the temperature gradient between the core and the mantle, the radius of the core itself, the rate of rotation of the planet, and numerous other subtleties. The rate of heat flow through the mantle is affected by geological processes including plate tectonics and volcanism. The precise nature of the flows depends on the constituents of the core other than iron, for example the sulfur content and distribution, and so on. It's fiendishly complicated, and because of this complexity, our planetary magnetic field gives every indication of being a delicate phenomenon. It was certainly delicate on Mars. We suspect there was once a Martian dynamo, because the Martian crust is still partially magnetized in places, particularly in the ancient southern highlands, suggesting that these rocks cooled in the presence of a global magnetic field. The Hellas impact basin, which formed around 4 billion years ago, shows no sign of magnetization, suggesting the dynamo shut down before this impact. Impact basins that formed over 4.05 billion years ago do show signs of magnetization. The Martian meteorite ALH 84001, dated at 4.1 billion years old, also shows clear signs of having formed in the presence of a magnetic field. These observations lead to the current baseline view that Mars had a magnetic field not unlike Earth's, which seems to have switched off just before the Hellas impact. From that point onwards, the atmosphere was exposed to the full force of the solar wind, and the Maven results tell us that this was likely the key driver for the loss of the Martian atmosphere. It would be tempting, but wrong, to suggest that the loss of the magnetic field was the trigger that drove the change from the Noachian to the Hesperian. The timescales probably don't match, and in any case the loss of the magnetic field wouldn't have led to an immediate loss of the atmosphere. Sputtering is a gradual process which still continues today. There have been speculative attempts to link the switch-off of the dynamo to the Hellas impact, or multiple impacts around the time of the late heavy bombardment. The idea is that the heating of the mantle can disrupt the heat flow out from the core, in turn disrupting the smooth convective flows. At the time of writing, the sequence of events is reasonably well established, but there is no consensus on how or even if they are causally linked. A complicating factor is the relative instability of the Martian orbit. The planet's obliquity, the tilt of its spin axis, varies by tens of degrees over timescales of a few 100,000 years in response to gravitational interactions with the other planets and the Sun. In comparison, Earth's axis drifts gently between 22.1 and 24.5 degrees in a 41,000-year cycle, and even this small change is responsible in part for Earth's periodic ice ages. Imagine what happened to the Martian climate when the polar regions with their reservoirs of carbon dioxide and water ice
tilted towards the sun by 20 or 30 degrees. The stability of Earth's spin axis is maintained by the damping effect of the Moon, which is unusually large relative to our planet. The Earth-Moon system might almost be regarded as a double planet system. The more we learn about other worlds, the more fortunate our presence on Earth appears. Despite all this marvelous complexity, the simple thought with which we began this chapter probably captures the spirit of why Mars died. The red planet is simply too small. It lost its heat more quickly than Earth from its smaller core and through its thinner mantle and crust. Geological activity fell markedly after reaching a peak during the Hesperian, and the planet faded. The atmosphere, held more tenuously than Earth's because of the planet's lower mass and gravitational pull, and unprotected by a magnetic shield, was stripped away by the solar wind, and the surface approached temperatures more in tune with an orbit far from the Sun. Mars's fate was sealed during its formation 4.5 billion years ago. It is too small and too far away from the Sun to have remained a vibrant, active world. Today, faint auroras still dance in the Martian skies, as photographed by ESA's Mars Express spacecraft. Blue ghosts of a Martian past generated by localized magnetic hotspots scattered across the planet, and the last traces of carbon dioxide in the atmosphere, energized by the relentless solar winds. Despite its 3 billion-year quiescence, Mars had a bright and active adolescence that echoes down the ages and may yet have profound consequences for us, confined for now on her planetary neighbor a solar system's lifetime away. There may have been, and may still be, life on Mars. We're looking hard, and the next generation of spacecraft may find evidence for Martians within the next decade. The discovery of a second Genesis would have important philosophical, scientific, and cultural consequences. It would mean that, given the right conditions, liquid water, active geology, and a sprinkling of organics, we would know that life emerges with a sense of inevitability through the entirely predictable action of the laws of nature. It would be confirmation that we, along with every living thing on our planet today, are an outgrowth of the planet, an extension of geology. We would understand that whatever magic we perceive in the depths of our souls has its origins in the interface between water and heat and minerals and gas. We are bubbling chemistry that thinks. If it happened on 2 neighboring planets in a single solar system, it happened everywhere. We would understand that we are part of a grand living universe. We are not God's children, but we are also not alone. Of even greater importance, I think, is the role that Mars must play in our future. Mars is rich in potential. It has reservoirs of frozen or even liquid water below the surface, and a great wealth of mineral resources, all the things that are necessary to support a civilization. Because of its history, this is a world in waiting, a treasure island in stasis. I think in my lifetime there will be Martians. The Martians will be us. We will go to Mars and make it our home, partly because there is nowhere else to go. Mars is the only planet beyond Earth on which we could even contemplate a landing in the near future. The message from Mariner 4 was not interpreted correctly. There is a second chance for us on Mars, when we feel ready to take it. I don't mean that we will leave Earth en masse for the new world. This is manifest nonsense. The Earth is by far and away the best planet we know of anywhere in the universe. We were born of it, and sculpted precisely and perfectly to flourish on it through the action of evolution by natural selection. Yet it is possible now to build a colony on Mars. I imagine a group of pioneers on the new world, living off the land and constructing the infrastructure necessary for tens, hundreds, and ultimately thousands of individuals to follow in their footsteps across the solar system and extend the human frontier for the first time in many centuries. Frontiers are important. The intellectual frontier is the domain of science, and where would we be without the pioneers who felt drawn there?
The physical frontier is the domain of adventurers, engineers, and dreamers. And dreamers need somewhere to go. In Werner Herzog's film Encounters at the End of the World, a man named William Gierser describes the sort of person who gravitates to Antarctica, the last of Earth's frontiers. I like to say, if you take everybody who's not tied down, they all sort of fall down to the bottom of the planet. So that's how we got here, you know? We're all at loose ends, and here we are together. I remember when I first got down here, I sort of enjoyed the sensation of recognizing people with my travel markings. I was like, hey, these are my people. PhDs washing dishes and linguists on a continent with no languages. Mars is the step beyond the Antarctic, and perhaps we all need to take it in our imaginations. Our civilization feels untethered to me. We're at a loose end, huddled in a tiny corner of our system. We watch the wandering planets and the wheeling stars and the cycles of day and night, and wonder what the hell we're doing. We're all linguists on a continent with no languages. As a consequence, we scrabble around, eking out the ever more precious resources on Earth, trying to expand and build more stuff and grow in a thin shell of air on the two-dimensional surface of a small rock, giving little thought for the three-dimensional path marked by the lights in the night. Robert Zubrin, the visionary engineer whose work has inspired, amongst others, Elon Musk, likes to say that ideas have consequences, and the worst idea in the history of humanity is that we must compete for limited resources. This is false. The solar system contains raw materials beyond our needs or desires, and they will become resources when we choose to access them. The international tensions created by the competition for earthbound resources are based on the entirely false and dangerous idea that resources are limited. False, false, false. We have the technology, and perhaps as we drift ever more aimlessly, we may discover the will to unlock the unlimited treasures in the vast solar system of which we are a part. We need to shift our collective consciousness. We burn too bright for this world alone, but that does not mean we should extinguish the flame. We must forge a new path that transcends competition between nations, that requires the wholesale rejection of the mindset that mistakenly compels us to retreat or fight over dwindling resources on a single groaning planet. We must transform ourselves into a multi-planetary, spacefaring civilization, and this begins with the colonization of Mars, an achievable goal forged from the human desire to explore and expand without pushing up against someone else's border fence or damaging our planet beyond repair. Imagine the magnificent intellectual and physical vistas, the new technologies, the opportunities, the excitement of creating a new society. The joy of extending our collective experience and hopes and dreams to a new world and worlds beyond. Mars has a pivotal role to play in our future. If we don't go there, we'll never go anywhere. And if we go nowhere, we'll die here. Breathing new life into the old red planet will breathe new life into us. It will be our first step beyond the cradle and onwards to the stars. The age of planetary surfaces. Earth before life, 4.5 billion years ago, was no nascent Eden, closer to the realm of Hades than the Garden of God. Molten and smouldering, cloaked in toxic clouds through which the young sun could barely break to signal the coming dawn. The planet still trembled from the aftermath of a glancing collision with Mars-sized Theia, now fragmented into a ring of debris that, given time, coalesced with the ejected rubble of Earth to form the Moon. 4 billion years later, two people who owed their existence to the energetic geology of Hadean Earth stepped onto the surface of the coalesced rubble and considered their position in the firmament. From their vantage point, Armstrong and Aldrin
viewed a peaceful, pristine planet that has been many different worlds since its formation. How do we know? How can we speak with any authority of events that happened billions of years ago, beyond not only memory, but also life on Earth itself? How is such a timeline calibrated? The answer lies in the rocks. Apollo delivered many treasures, countless engineering breakthroughs, a generation inspired, Earthrise from Apollo 8, the simple joy of exploration. But scientifically speaking, the treasure was rock. 382 kilograms of rock collected from 6 landing sites. On the Moon, as on Earth, rocks can be dated with great accuracy, using the natural clocks provided by the radioactive decay of certain atoms. The chemical element rubidium, for example, occurs naturally and quite commonly in a form known as rubidium-87, which is found in many potassium-rich minerals. It is unstable, with a half-life of 48 billion years. This means that over a period of 48 billion years, half of the rubidium-87 atoms that were present in a rock when it formed will have decayed away, transmuting into another sort of atom, strontium-87. An older rock will have fewer rubidium-87 atoms and more strontium-87 atoms. There is a little more to it than that, of course. How do we know how many rubidium and strontium atoms were present when the rock formed? The clever part of the dating procedure is that we don't need to know. The method, called the isochron method, relies on the fact that there is another naturally occurring form of strontium, which is not produced by radioactive decay, known as strontium-86. Strontium-86 is stable and chemically identical to strontium-87. The only difference is that it has one more neutron inside its nucleus. This means that any strontium-86 atoms inside a rock today were present when the rock originally formed. By counting the number of rubidium-87, strontium-87 and strontium-86 atoms in a selection of samples taken from a rock, it is possible to calculate the absolute time elapsed since the rock formed. On Earth, some of the oldest crustal rocks are found off the southwest coast of Greenland at a place called Ishwa. Using rubidium-strontium dating, we know these rocks were formed 3.66 billion years ago, with an uncertainty of 0.06 billion years. The oldest known rock on Earth was found in Jack Hills, Western Australia. It formed 4.404 billion years ago, with an uncertainty of 0.008 billion years. All known samples from Earth's crust are younger than 4 billion years old, because the seething surface of the Hadean Earth meant that rocks were constantly being melted and reformed, resetting the radiometric clocks. The same analysis can be carried out on meteorites that have fallen to the surface of Earth from space. The majority, over 1,000 known, formed between 4.4 and 4.6 billion years ago, which is consistent with independent estimates for the age of the solar system, using, for example, helioseismology measurements of the amount of helium in the Sun's core. The youngest of the moon rocks returned by the Apollo astronauts were 3.2 billion years old, and the oldest were 4.5 billion years old. 12 of the samples were over 4.2 billion years old. The variation in age of the moon rocks at the Apollo landing site is extremely interesting and important, and it forms the basis of the most accurate technique for dating areas of the Moon from which we have no rock samples. We can make a graph showing the age of the rocks collected from each Apollo landing site, and also the Russian Luna 24 robotic sample return mission, plotted against the number of craters per square kilometre at the site. The dark blobs around the labels of the various missions will represent the uncertainty of the measurements of the ages of the rocks and the crater counts. 2 very low and uncertain points from the craters Copernicus and Tycho are from rocks collected by Apollo that are thought to have been thrown into the landing sites by the impacts that created these 2 distinctive lunar craters in the much more recent past. 2 solid lines curve up across the plot, bounding the measured points. Older sites have more craters, which is easy to understand because there's been more time for meteorite impacts to build up. Surfaces that were created in the more recent past, such as the Copernicus crater, have experienced many fewer subsequent impacts. Imagine now that there's an area of the Moon from which we have no samples, but we do have photographs of that location from space. We count the number of craters per square kilometre. Let's say we get an average of 0.0002 craters above a diameter of 4 kilometres per square kilometre. This allows us to say that the surface formed somewhere between around 3.2 and 4 billion years ago, similar in age to the Apollo 17 landing site. This is one of the simplest uses of the graph. More importantly for our purposes, we can extrapolate the graph from the Moon to Mars. We have to make some model-dependent estimates of how the number of impacts changes because Mars is a larger planet with a stronger gravitational pull, and to account for Mars's different place in the solar system closer to the asteroid belt, the source of most of the impacting objects. We can do this with some confidence, and this is the primary way we estimate the absolute age of the different regions of Mars. The Noachian terrain is the oldest and has the highest density of craters, followed by the Hesperian and the Amazonian. The northern lowlands have been resurfaced by volcanic activity in the more recent past, which we know because they're relatively devoid of craters, much like the lunar seas. In this way, the absolute dates we quote for events on Mars are all ultimately tied to the radioactive dating of moon rocks. And this is one of the main reasons why the Apollo rock samples from different landing sites are so valuable scientifically. There's another key line on the graph, a dashed line we'll call constant production rate. The number of craters plotted against age would follow this line if the Moon had been subjected to a constant rate of impacts throughout its history. The measurements follow this line until we get to the surfaces around 3.8 to 4 billion years old, when the number of craters increases dramatically, implying that in the early history of the solar system, there was a time when the rate of impacts was much greater than today. That's not surprising. We might expect that the young solar system would have been filled with leftover rubble from the formation of planets, and so a more violent place. But there is a complication. If we assume that the impact rates seen on the oldest lunar terrains, such as the Apollo 16 landing site in the Descartes Highlands, were sustained all the way back to the Moon's formation, then the impact rate would have been impossibly high. The amount of mass falling on the surface of the Moon would have been similar to the mass of the Moon itself. We know that didn't happen, so the assumption is that the rise of the impact rate curve on the graph is in fact a spike that peaked around 3.9 billion years ago, and then returned to the much lower impact rate from earlier times. This violent spike in the rate of impacts from space is known as the late heavy bombardment. The cause of the late heavy bombardment is not known, but a leading theory is that Neptune changed its orbit from inside to outside that of Uranus, and the resulting gravitational disturbance deflected a maelstrom of icy objects in the distant Kuiper belt towards the planets of the inner solar system. We might reflect on the interconnected nature of knowledge and of the solar system. Exploration of the Moon provided us with the intellectual tools to date the surface of Mars. Using the scars delivered by objects deflected into the inner solar system by events that occurred far away in space and time, beyond the orbit of either world.
On the 24th of June 1947, Ken Arnold, an amateur pilot from Scobie, Montana, was flying over Mount Rainier, one of the most dangerous volcanoes in the world. Arnold was an experienced pilot with thousands of flying hours, and this implied he was a trustworthy observer. On returning to the airfield, he claimed to have seen 9 objects flying in the mountain skies, describing them as flat like a pie pan and like a big flat disk. He estimated that the disks were flying in formation at speeds of up to 1,920 kilometers per hour. The press jumped on the story, coining the term flying saucer, and within weeks, hundreds of similar sightings were reported from all over the world. On the 4th of July, a United Airlines crew reported seeing another formation of 9 disks over the skies of Idaho, and 4 days later, the mother of all UFO stories exploded at Roswell, New Mexico.
with the confirmation and then rapid retraction by the United States Air Force of a recovered flying disc. An alien craft crash-landed on Earth. I'll put my cards on the table here. I believe in UFOs. That is to say, I believe that there have been sightings of flying things in the sky that the observers were unable to identify, some of which were objects. But I do not believe for a moment that these were spacecraft flown by aliens. Occam's razor is an important tool in science. It shouldn't be oversold. Nature can be complex and bizarre. But as a rule of thumb, it is most sensible to adopt the simplest explanation for an observation until the evidence overwhelms it. My favourite response to the criticism that dismissing the possibility of alien visitations to Earth is unscientific was provided by physicist and Nobel laureate Richard Feynman in his Messenger lectures at Cornell University in 1964. Some years ago, I had a conversation with a layman about flying saucers. Because I am scientific, I know all about flying saucers. I said, I don't think there are flying saucers. So my antagonist said, is it impossible that there are flying saucers? Can you prove that it's impossible? No, I said, I can't prove it's impossible. It's just very unlikely. At that he said, you are very unscientific. If you can't prove it impossible, then how can you say that it's unlikely? But that is the way that is scientific. It is scientific only to say what is more likely and what less likely, and not to be proving all the time the possible and impossible. To define what I mean, I might have said to him, listen, I mean that from my knowledge of the world that I see around me, I think that it is much more likely that the reports of flying saucers are the results of the known irrational characteristics of terrestrial intelligence than of the unknown rational efforts of extraterrestrial intelligence. It is just more likely. That is all. Irrespective of the veracity of the stories of mutilated cows, crop circles, and violated Midwesterners at the hands of these alien visitors, the cultural impact of these early sightings was very real. America quickly entered into a media-fueled love affair with alien invaders in shiny discs, brandishing anal probes. Why didn't they use MRI scanners, a non-Freudian would surely ask. Of all the hundreds of thousands of references to flying saucers that began to appear in the media, a cartoon by Alan Dunn, published in the New Yorker magazine on the 20th of May 1950, found its way into the lunchtime conversation of a group of scientists at the Los Alamos National Laboratory in New Mexico. Enrico Fermi was one of the greatest 20th century physicists. Italian by birth, he conducted his most acclaimed work in the United States, having left his native country with his Jewish wife Laura in 1938 as Mussolini's grip tightened. Fermi worked on the Manhattan Project throughout World War II, first at Los Alamos and then at the University of Chicago, where he was responsible for Chicago Pile 1, the world's first nuclear reactor. In a squash court underneath a disused sports stadium in December 1942, Fermi oversaw the first man-made nuclear chain reaction, paving the way for the Hiroshima and Nagasaki bombs. After the war, Fermi settled as a professor in Chicago, but he often visited Los Alamos. During one of these visits in the summer of 1950, Fermi settled down for lunch with a group of colleagues including Edward Teller, the architect of the hydrogen bomb, and fellow Manhattan Project alumni Herbert York and Emil Konopinski. At some point, talk turned to the recent reports of UFO sightings and the New Yorker cartoon, stimulating Fermi to ask a simple question that turned a trivial conversation into a serious discussion. Where are they? Fermi's question is a powerful and challenging one that deserves an answer. It has become known as the Fermi paradox. There are hundreds of billions of star systems in the Milky Way galaxy. Our solar system is around 4.6 billion years old, but the galaxy is almost as old as the universe. If we assume life is relatively common, and on at least some of these planets intelligent civilizations arose, it follows that there should exist civilizations far in advance of our own, somewhere in the galaxy. Why? Our civilization has existed for around 10,000 years, and we've had access to modern technology for a few hundred. Our species, Homo sapiens, has existed for 250,000 years or so. This is a blink of an eye in comparison to the age of the Milky Way. So if we assume we are not the only civilization in the galaxy, then at least a few others must have arisen billions of years ahead of us. But where are they? The distances are not so vast that we cannot imagine traveling between star systems in principle. It took us less than a single human lifetime to go from the Wright brothers to the moon. What might we imagine doing in the next 100 years, or 1,000 years, or 10,000 years, or 10 million years? Even with rocketry technology as currently imagined, we could colonize the entire galaxy on million-year timescales. The Fermi paradox simply boils down to the question of why nobody has done this, given so many billions of worlds and so many billions of years. It is a very good question.
In far-off galaxies, galactic invaders are at work. Galactic invaders are at work. 3 times daily, a strange flash pulsates across our sky. It is hundreds of times stronger than all of the world's nuclear weapons put together. But it wasn't made by people, and if one happens close enough to Earth, it could wipe out all life there. Most people on Earth don't know about the possible dangers in space. Imagine this. A huge star explodes in our galaxy, the Milky Way, sending a deadly burst of energy hurtling toward our planet. This is a gamma-ray burst, which is the biggest blast since the Big Bang. There are no signs that something bad is about to happen, and then it strikes. The radiation that is pumped up heats up the high atmosphere. Our layer of ozone heats up. Across the atmosphere, human beings burns to death from radiation 100 times the fatal dose. When the ozone layer gets thinner, temperatures rise all over the world. This makes storms, tsunamis, and hurricanes happen. Most life on the surfaces of land and water incinerates. This may sound like science fiction, but if a gamma ray burst from 100 light years away hit Earth, it could happen. Gamma ray bursts are the most bright blasts in the universe. They must have a huge amount of power because they're so far away and yet still so bright. As much energy as the sun will give off in its full 10 billion year life. We know there are many planets and many stars in the universe, so gamma ray burst could have wiped out a lot of different cultures. In the 1960s, this strange blast of radiation was first seen. At first, because these gamma-ray bursts are so bright, most scientists thought they came from our own galaxy, the Milky Way. There are a few reasons for that. One of them is that if they are outside the galaxy, the energy is almost too much to believe. But back then, even the most powerful telescopes couldn't figure out where they were or how far away they were, because the burst only lasted a few seconds and then went away. But then, scientists started to wonder about their afterglow. Most blasts in space leave a glowing trail behind that can last for days or even weeks. In the late 1990s, satellites with better optics and X-ray monitors were finally able to catch the afterglow of a gamma-ray burst. It became clear that gamma-ray bursts actually came from outside our galaxy, millions and billions of light years away. So, their power had to be really out of this world. The brightness of the gamma-ray burst is the same as that of 1,000,000 trillion suns. This huge explosion could wipe out all life on Earth. But why do they happen? We are very sure that a common gamma-ray burst is caused by the death of a star that is at least 10 times the mass of the Sun. And these kinds of stars aren't very common. When a very big star dies, it falls apart and forms a black hole. Black holes are made when a mass of matter shrinks to a point where it is so dense that light can't get out. But experts think that some of the star resists getting sucked into the center of the black hole. As a result, a high-speed spinning disk of matter forms around it. In a matter of seconds, plasma jets shoot out from the poles where it spins. These beams of energy unleash dangerous gamma rays into space. At the same time, the gamma ray bursts are ejected, the collapsing star explodes or goes supernova to the extreme. Gamma ray bursts are so bright because they take a huge amount of power and focus it on a very small area of the sky. Only one of every 300 gamma ray bursts is directed toward us, so we only see one of those 300. Even if a gamma ray burst happened not 100 but 1,000 light years away, the Earth could still be destroyed in a way that is similar to the end of the world. If a gamma ray burst happens within 100 light years off the Earth, then it would be approximately 500 times brighter than the Sun and made in gamma rays. The energy sent to the high atmosphere of Earth would be the same as if 100,000 megatons of nuclear bombs went off. The ozone would be depleted, we'd have acid rain, but we'd also have flash burns, incineration of vegetation, perhaps something resembling nuclear weather. So many species could go extinct all over the world. Now, the other side of the Earth would be a special place to be, because gamma rays don't go through the Earth, so you wouldn't get flash burned if you were there. However, the repercussions of altering the atmospheric composition and ozone depletion would ultimately come to the other side, and there, nobody knows what will happen. This nightmare scenario has a 1 in a trillion probability of occurring once in Earth's history. It's going to be a nasty day if you get caught in the beam, for the reason that this is extremely powerful radiation. You don't want to be in the vicinity of this sort of energy, since it has the potential to break down your own molecules. Currently, there is no way to protect humanity against gamma ray bursts that occur in close proximity to Earth. They move at the rate of 186,000 miles per second, or the speed of light. By the time we detected them, they would have already struck our planet. Gamma rays bursts could pose a hazard to the Earth or to anything living that came within their born sight. Astronomers think that gamma ray bursts could be the cause of some mass extinctions on Earth. The one that happened 450 million years ago and killed off the Ordovician and Silurian species was probably the worst. Creatures that lived near the surface of the ocean were hit much harder than those that lived deep in the ocean. This is consistent with what would happen during a strong gamma ray burst. In a galaxy the size of the Milky Way, gamma ray bursts happen about once every few 100,000 years, according to astronomers. Even though they can be very bad, you have to be pretty close to be hurt by one. A gamma ray burst happens about once every 5 million years, which is close enough to affect life on Earth. In other words, since the Earth was made 4.6 billion years ago, there have been about 1,000 events. So the chances of a close gamma ray burst aren't zero, but they're low enough that you don't need to worry about them, unless you want to live for about 5 million years. Humanity obviously made it through the gamma ray explosion unharmed, but this still demonstrates how far their effects may travel. Don't fret. Threats to Earth from gamma ray bursts are extremely low. All of the closest contenders for gamma ray bursts have been studied by astronomers, and none of them are either close enough or orientated in a way that would cause them to strike Earth. Therefore, what do you think? In our solar system, Earth shines like a sapphire jewel. We go about our daily lives without knowing the trouble could be coming from deep space. The routes that Earth and most other things take around the sun can be predicted. Most of the time, things are quiet and easy, but sometimes they get crazy and violent. Earth can be hit by space rocks, zapped by dangerous space weather, jolted, jostled, and threatened by the object's energy and cosmic forces. The Earth is on a wild ride through space that is often very dangerous. When you're moving fast in on a predetermined path, you hope nothing crosses because there's nothing you can do. Rusty Schweikert used to be an astronaut. so he knows how dangerous things in space can be. During the Apollo 9 flight in 1969, he was in charge of the lunar module. He is sending out warnings about the risks of an asteroid named Apophis that is getting too close to be safe. Everyone noticed him right away because the probability of impact was quite high. In fact, it was significantly greater than any effect probability we had seen before. Schweikart has a scary example from real life that shows how bad an asteroid, even one smaller than Apophis, can be when it hits. June 30th, 1908, 7:15 a.m. A half-football field-sized object came hurtling down from space at about 34,000 miles per hour and made a stream of fiery gas behind it. Within minutes, the fireball hit Earth's atmosphere and burst violently near the Tunguska forest in Siberia. As a result, the explosion was the greatest ever recorded in the history of the planet. The explosion split the waves, which then set fire to 8 million trees in an area that was bigger than half of Rhode Island. Because the explosion happened in a place with few people, no one died directly from it. If that asteroid had hit just a few hours later, it would not have hit Siberia, but Europe. And if it had exploded in the air over one of Europe's biggest cities, 1 million people would have died. For the last 100 years, the Tunguska explosion has been shrouded in controversy. Many researchers now think an asteroid was the explosive trigger. Incredibly, it never even impacted the ground. Rather, it exploded 5 miles above Siberia's frozen ground. When it smacks into the lower atmosphere, doing about 50,000 miles an hour, it's like an egg smashing on the concrete. Energy equivalent to 15 megatons of TNT was released in the Siberian explosion, making it 1,000 times greater than Hiroshima. Over a huge city, this would be catastrophic. NEOs, or near-Earth objects, were the name given by scientists to these trespassers. They are comets and asteroids, leftover debris from when the planets formed. The Oort cloud is a part of the Kuiper belt that extends past Neptune and is where comets travel. Between Jupiter and Mars, asteroids take a curved path, but their orbital trip isn't always routine. We don't have to worry too much about asteroids because they circle in a somewhat orderly belt between Mars and Jupiter. But when one gets away and all that mass and energy is going toward Earth, that's when the astronomers start to worry. It's not uncommon for cosmic debris to be jolted out of orbit and headed for Earth. The majority of it is evaporated by our planet's dense atmosphere. A larger object, however, is able to break through Earth's atmosphere and crash to the surface. Asteroids are a real and dangerous threat if you wish to look to the cosmos for the powers that would have us dead. Just like it did previously, it will happen again. 65 million years ago, an asteroid the size of a small city plummeted down from the sky. It exploded in the Yucatan Peninsula, near the town of Chicxulub in Mexico, with a force of 100 million megatons of TNT. Here we see Earth hurling billions of tons of its crust into space, creating a blanket that blocks out sunlight, destroying the food web at its roots, and killing off countless species. The ferocious impact is thought to have been a factor in the extinction of the dinosaurs. We can think of asteroids as being bad things, but if it were not for an asteroid, we wouldn't be here today. Our mammal ancestors were running on their foot trying to avoid being appetizer for T-Rex. T-Rex gets taken out. Well, this opened up an ecological niche that allowed our mammal ancestors to evolve to something more ambitious than a route and outcomes the primates, and among the primates, we have people. But it's strange that the same kind of cosmic boulder that made it possible for humans to live could one day wipe us out. In 1998, Congress asked NASA to find all near-Earth objects that were at least half a mile across, and what they found was unsettling. There are more than 850 NEOs near our vicinity. These asteroids are our nearest and most dangerous space friends. Finding these near-Earth objects is a bit like keeping an eye on storms. As you watch it day after day, you get a better idea of its path and can figure out where it's going, how big it is, and how fast it would hit the Earth if it did. By using telescopic technologies, NASA's Space Guard survey has detected over 90% of all near-Earth objects deemed harmful. These scary things could hit Earth with more power than all of the nuclear weapons on the world right now. Such an impact could trigger mass extinction. We wouldn't expect one to hit every few hundred, thousand, or millions of years, but if one did, it could wipe out different parts of the population. So there are events that happen very rarely but have big effects when they do. If they hit Earth, they would have impacts all over the world. They would not only wipe out a continent with very strong shock waves, but the debris would also be thrown into the air and land all over the planet, heating the air to 1,000 degrees. And all the vegetation all over the world where that happens would flash into flames. Smaller objects could also cause disasters, so Congress has asked NASA to find all NEOs with a diameter of 500 feet, which is as big as the Colosseum in Rome. A big object like that could wipe out a city or even a small state. Scientists are most worried about the asteroids they haven't found yet, not the ones they have found. Well, at the moment, there are about 2,000 objects that we can't say for sure won't hit Earth. We now have the technology to keep near-Earth objects from ever hitting Earth again. We can now literally start to change the local solar system to make it better for our life. The question is whether or not we will end up like the dinosaurs. It's hard to believe that the Earth has been around for more than 4.5 billion years, because it's been through a lot since it was born. Asteroids that come into our orbit every year keep hitting our world, like a boxer, but one day Earth could be knocked out. We've learned that near-Earth objects fly by us all the time, and we're getting more and more able to change our surroundings to help us stay alive. A rock in space named Apophis. In 2004, this pockmarked rock about 750 feet across came close to Earth. Now, it's scheduled to pass dangerously close to our planet again on Friday the 13th in April 2029. So, in 2029, Apophis will get closer to us than our Rome communication satellites that circle the Earth. If you are in the right place, you will be able to see Apophis pass by the Earth with your own eyes. That's how close that rock is going to get. You won't even need binoculars. Over 99% of the time, Apophis will miss the Earth in 2029. However, if it passes the Earth at an exact distance of 18,893 miles, it may pass through a gravitational keyhole, a small area in space that is only a half-mile wide. If this happens, Apophis could be thrown off by the Earth's gravity, which could change its path. It could make Apophis come back and hit Earth on April 13, 2036, 7 years later. The gravitational effect of the Earth would cause it to bend, cause the Apophis's orbit to enlarge to precisely the size, which 7 years later it will come around and hit the Earth. At the present time, Apophis has 1 in 45,000 chance of delivering a deadly blow in 2036. It's one thing to say that there's a 1 in 45,000 chance that it will hit the Earth, but what you really want to know is if there's a 1 in 100, 1 in 10, or 1 in 1 chance that it will hit the Earth. We have to look at Apophis the same way we look at any natural disaster. You know the date of the hit, when it happened, and the angle of the orbit, so you can make a map. It starts in western Siberia, cuts across and down the Pacific Ocean near California, goes through Central America, and ends in Western Africa. Scientists have come up with a scary idea about where Apophis could strike. With a force of more than 1 million megatons of TNT, the asteroid could hit the Pacific Ocean off the coast of California. Such an impact would make a hole in the water 5 miles wide and 9,000 feet deep. This would cause tsunamis with waves up to 50 feet high to hit the coast, resulting in unimaginable human loss. If a rock 1,000 feet across hits the ocean, that's not a good thing. For that kind of thing, scientists are working on ways to stop such a cosmic strike from happening right now. A possible plan is to blow up an asteroid. But some people worry that this could make the problem worse by sending more pieces of the asteroid our way instead of just one. So, the new goal for experts is to change the path of asteroids that could hit Earth. Change its velocity by a 10,000th of a mile per hour so that it will miss the Earth instead of hitting it. If we know about an asteroid far enough in advance, we can change its path. Although a space probe has landed on an asteroid in the past, the most challenging idea is launching a manned mission. Once landing on the rock, astronauts could mount a radio transponder to track its whereabouts. Now the United Nations plans to draft a treaty which will include who will be responsible for deflecting killer asteroids. If we are so careless that we keep doing nothing even though we know this is going to happen, that will be a real crime. Any asteroid hitting the Earth will require international disaster response. In addition, training is required in disaster and emergency management institutions and the public regarding the asteroid threat. It is important that everyone is aware of the level of threats and the potential to eliminate this threat. Apart from all these, amateur astronomers can work together with scientists to defend our planet. Amateur astronomers can help identify smaller and potentially destructive asteroids hidden in the universe. So would you like to be an amateur astronomer? Who knows? Maybe you can be one of the guards of our home. On a night in early September 1859, people all over America could see the aurora. It was blood red and so bright that when miners in the Rockies came out of their tunnels, they thought the sun was coming up. So bright, in fact, that even at midnight you could read a newspaper. It didn't just happen in the U.S. People all over the world saw these auroras. No one knew why they had happened. But earlier that same day, an astronomer had seen something on the sun's surface that he called a white light flare. Back then, the flare and the aurora seemed to have nothing to do with each other. But we now know that the spectacular aurora was caused by that flare, which was a coronal mass ejection. And if this violent event happens again, it could destroy our modern technological world. The sun is the most familiar thing in the sky. It gives all life on Earth heat and light. It is so big that it's hard to imagine, and it makes up 99% of the mass of the solar system. This nearly perfect sphere has a diameter of 1.4 million kilometers and was made by the burning of hydrogen and helium for the last 5 billion years. But from an astronomical point of view, it's nothing special. A G main sequence star, also known as a yellow dwarf. But looks don't always tell the whole story. Solar flares and explosions of plasma, particles, and radiation from its surface travel far into space. We call this process the solar wind. Solar storms, on the other hand, are very violent eruptions. And a coronal mass ejection, or CME, is the most dangerous because it has the potential to bring our high-tech society to its knees. Today, We'll find out how bad ACME could be and what astronomers are doing to keep an eye on our star to try to predict when they might happen. Step back in time to 1859. First, in Victorian Britain, it was okay for a gentleman to be interested in solar astronomy. And one man did it in a very good way. Carrington, Richard Christopher. We don't know what he looked like, though, because there are no known portraits of him. Carrington learned many important things from what he saw. He saw that different latitudes rotated at slightly different speeds, which meant the sun wasn't a solid body, but a fluid one. But he also saw that sunspots could be the start of a solar storm. On Thursday, September 1, 1859, there were no clouds in the sky in the morning. So Carrington was doing what he always did, which was to look for sunspots. He was using his telescope to project an image onto a screen. At 11:18, he saw two brilliant beads of blinding white light appear in what Carrington calls a kind of conflagration. Stranger still, they were gone after 5 minutes for no clear reason. Carrington had seen a coronal mass ejection, which was a huge magnetic explosion. A huge cloud of charged particles that are thrown off the sun's surface. After 18 hours, the Earth was hit by an electromagnetic storm. People started calling it the Carrington event. At the time, everyone was talking about the beautiful aurora, which could be seen all over the world. Even though a few telegraph systems went a little crazy because of power surges, it didn't have much of an effect on everyday life. Don't forget, though, that this was 20 years before the light bulb was made. That was in the past. Things would be very different right now. Coronal mass ejections are common, but they can be different sizes and move in different directions. So, the question is, what are the chances that something like what happened in Carrington will happen today? And how would it change things? So, what is going on at the sun, on the surface of the sun, when we talk about the solar wind and space weather? The sun is made of magnetic fluid, and when that magnetic fluid rotates, it twists and distorts the magnetic field. A twisted magnetic field stores energy, which can lead to eruptions, which are called mass ejections. And these explosions are huge, sending out 1 billion tons of material at 1 million miles per hour. So, we want to know where these things are going, because if they move toward Earth, they could affect the technologies we use. There's a very famous event in Quebec in 1989, where some power systems were disrupted for many hours in October. We've heard about the Carrington event, which happened in the 1800s. What would happen if it happened today, and how would it affect us? If we think about what we use satellites for now, we have GPS spacecraft that help us find our way, communication satellites, weather satellites, and even the stock markets are linked in some way. But we also have bigger power grids and a lot of wireless technology, and we don't know how they will react. How likely is it that something like the Carrington event could happen again? We know that the sun can still make these things happen. In 2012, there was an event that luckily didn't come toward Earth, but it did pass over one of the spacecraft we use to watch the solar wind. And it pushed all the sensors on that spaceship to their limits. So from what we've learned, we think that was at least as powerful as the Carrington event, and maybe even more so. It's just a coincidence that a big CME and one that's headed toward Earth both happened at the same time. And that's mostly just a matter of luck. We either get one or we don't. And how do we do with making predictions? Can we predict what the sun will do in a week, a month, or a year? Once ACME is up and running, we can start making predictions so that we can figure out how big it is, how fast it's moving, and most importantly, where it's going. All of this sounds very scary. Space weather is a problem, and the UK government knows this. The National Risk Register lists it. It's about as bad as a pandemic of flu. So, the people who make spacecraft are trying to find out what the most extreme conditions are in space, so they can make them so that they can handle those conditions to a certain degree. Both NASA and ESA are getting ready to send satellites into space that will get closer to the sun than ever before. The MET office's Space Weather Operations Center opened in 2014. It is one of only 3 places in the world that can predict the sun's effects on Earth around the clock. So far, the sun has had almost no sunspots, and the side that faces Earth is not expected to have any more sunspots or CMEs that are important. So luckily, there isn't much going on right now, and things don't look too different in the long run. So, spacecraft, satellites' power supplies should be safe for the foreseeable future. Trouble is, the foreseeable future in space weather forecast is, at most, just a few days. We still don't know a lot about CMEs, like where they're going, how big they are, or when they might happen in the future. 2 new solar probes will get closer to the sun than any other spacecraft has ever done. The Parker Solar Probe was supposed to be sent into space, and its destination will be close enough to the sun's surface to fly through the source of the most energetic solar particles. The Parker Solar Probe is an exploration mission that will measure the gas and magnetic field near the sun to figure out why this stuff is spreading out into the rest of the solar system. And this, the Solar Orbiter from ESA. Solar Orbiter might find out how sunspots, flares, and coronal mass ejections on the sun's surface are related to the solar wind. Solar Orbiter's success will be very important for our understanding of how the sun works. We think that the sun's magnetic field is made in a way similar to how Earth's is, but it is much more dynamic and changes all the time. We have an 11-year sunspot cycle, during which the sun's magnetic fields move towards the poles and the polarity changes. On top of that, the magnetic field goes out into the solar system and flows over all of the planets. Solar Orbiter will measure these magnetic fields for the first time, and it will also give us the chance to watch the magnetic fields move to the sun's poles. To do this, Solar Orbiter will take pictures of the sun's atmosphere and measure the number, speed, and temperature of the particles moving across the space between the sun and Earth. But the magnetometer, which is made to measure the tiny magnetic fields in space that are carried by the solar wind, could be one of the most important and sensitive instruments. The sun is ever present in our lives. It gives us light, warmth, and even life itself. For Richard Carrington, who was the first person to record ACME, it was just a strange event. But now we know that these things can do a lot of damage to the world we live in. With new satellites and more observations, we might be able to learn more about these events and predict when the next coronal mass ejection will happen. Nothing existed at the outset. After then, the cosmos began to take shape some 13.7 billion years ago. How this came to be, or if there was ever a time before, time is still a mystery. Yet, physicists have pieced together an approximate timeline of significant events in the cosmos's existence using telescope data and models of particle physics. From its beginning to its inevitable demise, we examine key points in the evolution of our universe here. Welcome to the endless universe. If you're interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. The Big Bang. The Big Bang is a moment in time, not a location in space, from whence all else unfolded. To be more precise, it's the first second of time, the point in history from which all other seconds have been measured. The Big Bang, despite its common name, was not an explosion, but rather a time when the universe was incredibly hot and dense before space began to expand outward in all directions simultaneously. The Big Bang scenario suggests that the universe was an infinitesimally small point of infinite density. However, this is merely a convenient way of expressing that we don't know for sure what happened at that time. We now understand the cosmos to break down at the Big Bang because mathematical infinities don't make sense in physics equations. Cosmic inflation era. The next cosmic confab was to rapidly expand in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but it has gained favor among cosmologists as a possible explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014. Nevertheless, further investigation revealed that the true culprit was nothing more than interplanetary dust causing interference. Quark-gluon plasma. The temperature of the early cosmos was between 7 trillion and 10 trillion degrees Fahrenheit, or 4 trillion and 6 trillion degrees Celsius, just a few milliseconds after the Big Bang. Quarks, elementary particles ordinarily contained within protons and neutrons, were free to move about at these temperatures. These quarks were combined with gluons, carriers of the basic force known as the strong force, in a primordial that pervaded the whole universe. In particle accelerators on Earth, scientists have replicated these circumstances. In both terrestrial atom smashers and the early cosmos, the challenging to achieve condition only lasted for a few fractions of a second. The early epoch. The subsequent period of time, beginning perhaps in the neighborhood of a few thousandths of a second following the Big Bang, was a period of intense activity. The universe chilled as it expanded, creating an environment conducive to the merger of quarks into protons and neutrons. The cosmic neutrino background, which has not yet been detected by scientists, was created 1 second after the Big Bang, when the density of the cosmos decreased sufficiently for neutrinos to sail across space without interacting with anything. The first atoms, protons and neutrons, fused together during the first 3 minutes of the universe's existence, creating the isotope of hydrogen known as deuterium, along with helium and a trace quantity of the next lightest element, lithium. Yet, this procedure ceased as the temperature dropped. As temperatures settled down 380,000 years after the Big Bang, hydrogen and helium atoms could join with free electrons to form the first neutral atoms. The cosmic microwave background, a remnant of this epoch first identified in 1965, was created when photons that had previously collided with electrons were able to flow without being disrupted. The Dark Ages. There was a lengthy period of time when nothing in the cosmos emitted any light. The cosmic dark ages refer to this time frame of around 100 million years. Because practically all of what astronomers know about the cosmos can be gleaned by studying starlight, this era remains exceptionally challenging to study. It's hard to piece together what happened if there are no stars to guide us. The first stars. The first stars were formed when hydrogen and helium began to compress into massive spheres, some 180 million years after the Big Bang, creating hellish temperatures at their centers. After the neutral hydrogen atoms in interstellar space were broken apart into protons and electrons by the intense photons generated by early stars and galaxies, the cosmos entered a period known as cosmic dawn or reionization. It's hard to put a time limit on reionization. As it happened so soon after the Big Bang, its signals have been masked by subsequent gas and dust. Thus, the most that scientists can determine is that it was finished by around 500 million years after the Great Bang. Large-scale structure. Almost 1 billion years after the Big Bang, supermassive black holes developed at the cores of merging early galaxies. Intense quasars, visible from 12 billion light-years away, switched on and began emitting their bright beams of light. The universe's middle years. Throughout the subsequent few billion years, the cosmos underwent more evolution. Denser regions in the early cosmos drew more material due to gravity. A gorgeous filamentary cosmic web is the result of them slowly expanding into galaxy clusters and lengthy strands of gas and dust. Birth of the solar system. A yellow star with rings around it formed from a cloud of gas around 4.5 billion years ago in one galaxy. These accreted rings eventually became the 8 planets of our solar system, as well as numerous comets, asteroids, dwarf planets, and moons. Either the third planet out from the sun retained a lot of water via this process, or it received a deluge of ice and water from comets later on. Earth and humanity. Little primitive bacteria appeared on that third watery world between 3.8 and 3.5 billion years ago. These organisms arose and progressed into amazing marine monsters and enormous dinosaurs that fed on leaves. Some 200,000 years ago, upright beings emerged, capable of contemplating the vastness of space and learning about the universe's origins. The end, or not. It isn't the final chapter, of course. The future of the cosmos is still a mystery to physicists. It is dependent on our ability to accurately quantify the characteristics of dark energy, the unknown factor thought to be accelerating the expansion of the universe. All the stars in all the galaxies will have burned out, and even black holes will evaporate into nothing if the universe continues to expand forever, leaving behind a lifeless cosmos saturated with inert energy if this scenario comes to pass. Alternatively, the Great Crunch, a reversal of the Big Bang in which gravity triumphs over dark energy's expansionary force, will occur. The Great Rip, in which the cosmos rips itself apart, is another possibility if dark energy accelerates everything apart to greater and greater distances. Thanks for watching, and don't forget to hit the like button, subscribe, and turn on notifications for more content like this in the future. Our solar system is a harsh environment. Volcanoes are destructive everywhere, from the ice volcanoes of Saturn's moon, Enceladus, to the immense lava fields of Jupiter's moon Io to our own planet Earth. It is truly true that we would not be here if there were no volcanoes. Volcanoes influence and alter our climate. Volcanoes are both the creators and destroyers of existence. Today's spacecraft and observatories have revealed volcanoes on planets we once believed to be dead. The discovery of volcanoes on an object smaller than the moon was a major surprise. If there are volcanoes on other worlds, could there also be life? Volcanoes are among the most potent natural occurrences on Earth. They create new land, destroy the old. They emit gases that alter the atmosphere we breathe. Deep in our oceans, volcanic heat fuels bizarre new forms of life. Volcanoes help sustain life on Earth. Now we look for signs of life on other planets. We understand that life requires water. We are aware that it requires energy. And this is where volcanoes come in, as they generate tremendous quantities of energy. If we locate volcanoes on other planets, we may discover life. The search begins with this planet, which orbits the Earth closest. Venus, a planet that closely resembles our own. Venus and Earth have similar masses. Earth and Venus were very similar 3 billion years ago, with new land, new oceans, and an atmosphere. Both planets was conducive to life. On Venus, however, something went awry. Something caused the history of Venus to diverge drastically from that of Earth. Venus took a definite turn to the dark side a long time ago. Venus is Hell, our malevolent twin planet. Today, the surface of Venus is like a furnace. The surface is 900 degrees Fahrenheit hot. It is actually heated enough to melt some metals, so you have no chance. Venus is a greenhouse world. Its atmosphere contains a high concentration of carbon dioxide. It absorbs solar heat like a blanket. Actual images of Venus's surface reveal a desolate, extremely hot desolation. The planet was annihilated by dense CO2 atmosphere. The CO2 was produced by volcanoes. Spacecraft in orbit provided the initial clues. Radar broke through Venus's thick clouds and showed volcanic formations all over the planet. These formations look a lot like the shield volcanoes on Earth. Round and flat, shield volcanoes derive their name from their shape. These volcanoes ooze, but they ooze for thousands of years. Once we were able to map the entire surface of Venus using cloud-penetrating radar, we began to examine its landforms and discovered that many of them were quite familiar. In particular, we observed enormous shield volcanoes that resembled the shield volcanoes in Hawaii. The radar images of Venus were identical to those of Hawaii's shield volcanoes. In the past, Venus was home to volcanoes. We were astounded to see a picture of Venus for the first time. We discovered a cratered volcanic surface. There are at least 1,000 large volcanoes,